we talked about who I am. My office is right up by the tutoring center. And you should know where the tutoring center is because they cover this class and they cover a lot of those big service classes you have to take, like chemistry and physics and that kind of thing. So make sure you know where the Textiles Tutoring Center is. And all that information and the hours will be posted in Moodle when I figure out what's going on. Okay, so you already should have gotten an email via me sharing the syllabus with you because the syllabus that's in Moodle is not the right one. This is the right one. So you have my email. I'm bad at email, okay? Whenever I get in a state of overwhelm, I quit looking at my inbox, which does not help, right? It's not a good coping skill, but I'm bad with email, okay? Put T200 in the subject line because I flag those as important because I like to hear from. Someone asking me to serve on some committee or write some report or do an assessment is not who I want to hear from when I'm overwhelmed. You guys are why I'm here and why I like my job. There's a lot of people up there that are not why I like my job, okay? So make sure you put T200 in the subject line. And if you don't get a response in one business day, send it again, okay? Send it again. Because if it scrolls off the first 50 messages, it's gone forever, okay? And I get more than 50 messages a day. I try and delete all the junky ones so that I as soon as I see them, so that I'm not having, I'm not losing things right away. Okay, so we've got a technology statement, which is right here. This is going to give you all of the software and web clients and stuff that we plan to use this semester. Expectations, netiquette, stuff you guys should know, right? Be kind to one another. There's the takeaway of netiquette for me. But that is all there for your resources. So if you want to know the privacy statement for something, it's all linked through there. This course overview is, please read it. This is, I wrote this to try and get you to think about what do I need to do to be successful in this class and that kind of thing. And we're going to talk a little bit about metacognition, thinking in terms of study cycles and how to study. And Sandra McGuire was a professor in chemistry, and she worked with students to teach them the study cycle, and it was a game changer for her chemistry students and students who applied this. Like, she has a lot of published data. There's research that backs this up, showing that students who were failing, D's and F's, who adopted this could study less than they were before and be way more successful. So interacting with the content more often, actively engaging with it. If you just sit there and read it, sometimes you can read the same paragraph over and over, you still don't know what it says, right? We've all done that. So try and think about how you can actively engage with the content. When we get Moodle up and running, there is a lot of interactive H5P things that I've really created for the online version, but they're all there for you guys too. So there's a lot of times that stuff where it's like you watch a short video, it pops up a question, or you're having to sort things or do different things. It helps you stay engaged and focused on what you're actually doing. But McGuire's study cycle is like, look ahead. What are we doing? Be active and engage. Review. So one of her big takeaways is to try and review after class. As you know, a lot of times you've got to go to another class right away. But if you don't and you have a few minutes to sort of sit down and think about, what did we cover today? What do I understand? What do I not understand? And make those notes to yourself so that when you go to study, you can quickly review what you understood and focus on what you didn't understand. And then, you know, assess your learning. She goes on and really talks about how can you teach the content to someone else? You're going to study harder for an exam or to teach your peers something, right? Usually it's to teach. That's what most people answer. And so one of her strategies in her books are available through the library online for free. She talks a lot about if you can teach a topic, if you can explain it, that's really a powerful way of assessing whether you know it or not, as opposed to just rereading the chapter again. I've seen her speak a few times, and she talks about one of her students used to teach chemistry to his goldfish, right? Just, you know, people use stuffed animals or whatever, you know, so however you want to think about that. So that's our course overview. I'm trying to follow the syllabus regulation, and so you have to have the course catalog description exactly as it is, but we don't cover the things I've crossed out. And these are our official student learning outcomes, and we will cover them all except for the last one. We rarely have time. If we have time, we'll spend a lecture on it, but usually we don't have time to go over that. Health and well-being resources for your reference. Here is our course schedule. So you see no class on the 24th. Your super hard homework is due a week from today, which is you're going to have to submit 2 questions you have about polymers through Moodle. So I will get that once I get Moodle figured out. Okay, so yeah. And then, so a week from today, I'm going to have you guys ask me the questions you came up with. Okay, see how many times you can stump me, because I know that you can. And we'll learn a lot of nomenclature, a lot of vocabulary in the beginning, so that we're all on the same page with words that we use for polymers and macromolecules and all that kind of stuff. And we've got Wellness Day on the 12th. And then go over homework and review for exam 1. So you see that. You notice there's no exams on this schedule. So as long as I'm feeling pretty good that people aren't cheating, because I know that you can, we will do the exams asynchronously online. The one thing I noticed during COVID, during the, all of a sudden we're all online, was that test anxiety sort of came down when I could give you a window of several days to take the exam, and that people were like, well, I can take the exam in a space that I'm comfortable in. And I really liked that aspect of it, and it's nice to have a little more flexibility in our schedule, and so I don't feel bad that I can't come to class on Thursday, and I'm not really making you watch a video or do anything else, because now we're doing the exams outside of time, outside of class. We have some flexibility. We will do them in grade scope. I refuse to spy on you through web cameras. So I think it's totally inappropriate to spy on someone in their own home or their own dorm room or wherever it is. So I will not do that. I am aware it is possible to cheat on this style of exam. And as long as we have trust for one another and that type of thing, we'll keep doing it. We'll do it the whole semester, and I will have the final open almost all of finals week. Okay? So, cheating on an exam is using outside resources. These are going to be, anything besides calculator and paper, right? So the exam is supposed to be no notes and no talking with one another, just like an in-class exam would be. But we'll go over that in a lot more detail as we get close to it. I'll have a practice grade scope exam so you can practice uploading your work. So you're going to have to take an image of your work, however you want to do it, and upload it. Okay. So there'll be a practice one. I try and give you a lot of information so there's no surprises as to what's on the exam. Okay. So, So there, exams will be scheduled 1 to 3 days after the review, and they'll be open for several days. Okay, so we will have at least 3 days, and I try and do 5. That's what I usually try and do. So ungraded assignments are readings, watching videos, dealing with the interactive content. You guys are going to be coming to class, so I'm not going to be like monitoring that as much, because you'll be here in class. So like you're here, you don't necessarily need to watch a video, right? But all of that stuff from the online section will be available to you in Moodle. Graded assignments. I'm going to give you lots of pop quizzes in class. Okay? You should always be happy that you get a pop quiz, because if you're here, you get full credit. Okay? It's sort of a reality check for both of us. You can do it? Great. Can't do it? Then we both need to really think about that. Okay? So if you're here, you get a pop quiz, you get full credit. You're gonna grade it yourself and take a picture of it and upload it into Moodle. And by grade it, I mean correct it, because everybody's going to get full credit. If you miss class, you'll have an opportunity to do it in Moodle. Homework, we will theoretically grade on a 4-point scale, right? Essentially check plus, check minus. We will go over all homework in class, or if we're running short on time, there will be videos of every homework problem. So you will see every homework problem solved if you choose to. And I highly encourage you to make sure you have watched every solution video for homework. Okay? All of our assignments have posted due dates. I will accept late assignments without penalty until the final. Final's cumulative, so even if you didn't do the assignment in the beginning when you were supposed to, it's still good for you to do it up until the final. So we will take them late without penalty, but you will dig yourself in a hole if you don't do them close to when they're supposed to be done. Okay? The exception for that is when you work with a partner. We have one assignment that you're going to do with a partner, and that's coming up shortly. So aside from that, if you do it late, you do it late. Don't dig yourself in a hole, okay? It's going to make, when the exam comes around, it's going to make for a lot of stress and that kind of thing. If you put in a little bit of time every day, you're going to put in less time overall. And that's true for any of your classes. And this is very much a do as I say, not as I do. When I was a student, I was a huge procrastinator. I still am. If I don't have a deadline, and I'm not interested, it's really hard for me to do things, to get things done. So I fully understand that. So I used to not really talk about that I would take homework at any point up to the final. But then, because that would have helped a student like me, but students with anxiety and that kind of thing, it doesn't help them in any way. So if you're a procrastinator, get it done by the deadline.
I will back that up because I had that issue with my math class last year, where last semester you could do it. I will say I probably did a lot worse than otherwise because the homework reinforces it. Yeah. And then also when you go doing the homework, you're wondering, what is this again? We talked about it. It was 3 months ago.
Yeah, makes it hard. So staying on track with the class as best you can is really helpful. Okay, so we already talked about the exams. This is my plan for the first exam. The other 2 exams, so I like to do exams after we finish content. So even if we finish content early, we can still have the exam when I scheduled it. But if we haven't finished the content, then we might push it back. So the exams will not be earlier than this. They only might get pushed back a little bit. Okay? Our exam, the final is scheduled. It's the first day, I think, of finals. And again, assuming we don't have a lot of cheating going on, then the final will be open most of finals week, not just the first day. Okay. We've got homework and quizzes. The first exam is worth the least. Get used to my style and that kind of thing. The next 2 exams used to be 1 exam. And then the other nice thing about doing them online is we can break them up and have less higher stakes exams. So exams 2 and 3, when they were put into 1 exam, it was by far the hardest exam of the semester, by far. Now we have just synthesis in exam 2 and just kinetics in exam 3. Typically, students find synthesis really hard or kinetics really hard. So it's nice that they're not together. So I don't know which one of you will find exam 2 really hard and which one of you will find exam 3 really hard, but probably one of those 2 will be the hardest of the semester. And then the final is cumulative. So if you bomb one of those exams and do well on the final, I always look to see if the final is like done, like if you've gone up, and if you're anywhere close to a grade cutoff, I'm going to bump you up, because if you know it at the final, why should I really penalize that you didn't know it the first time? That's my philosophy. If usually the average of an exam is not 60, but I often have class averages that are in, between like 68 and 76. It's pretty typical. That doesn't mean everybody's like down there, okay? So I'll figure out where the average is. So a lot of times my grade cutoffs are going to be shifted lower. I don't give points or give extra credit. I just shift where the cutoff is. So the standard cutoffs, if you get that, it's not like a curve where I'm going to say this percentage gets A's and B's, right? It's not a hard curve. If you get, what's in that grading scale, you've earned it. You'll get that score, but typically it's 4 or 5 points lower, except for A+. I don't change that one. Don't change the A+. Okay. So come to class, whether you're prepared or not, come to class. But if you can come to class prepared, you'll get a lot more out of the lectures. So if you can look at what the Moodle section, if you can look at the textbook. I skipped the textbook, didn't I? I didn't talk about it. Yeah. Okay, textbook. Okay, so there is a $20 electronic textbook. in the fall semester, sometimes the payment and that kind of stuff doesn't work great, but I know Professor Painter who wrote it, and we'll get the kinks worked out if things are not going well. So the hard copy of his book was like $200 or something, and that's not really in his control. So now he just publishes it electronically, and he can charge. He can set the price and that kind of thing. So, but the downside is he's self-publishing it, and he's not great. He's retired, and websites and web maintenance and that kind of thing is, but once you get in, once you've paid and get in, it always works. But anyway, maybe it'll go great this fall. Okay, so the hard copy is Essentials of Polymer Science and Engineering by Painter and Coleman. It originally came out in 2009. It is still in print. It's been updated a little bit. Any edition is fine. It's a nice book because it's full color. It's a nice book. And then the older, it used to be Coleman and Painter instead of Painter and Coleman. Their older book is called Fundamentals of Polymer Science and Engineering. And a lot of times you can get that really cheap because it's older. But the core content is all fine. For an intro class, all these books are great. So if you want a hard copy, try and find a used one. If you don't mind using digital, the $20 is the way to go. And then the hard copy of this one, the Essentials of Polymer Science and Engineering, will be on reserve in the library. Okay. All right. So we were way down past exams, attendance policy. You can look at that. You know about the academic integrity. Okay. I try and run my classroom as equitably as possible, right? We are all equally important. We are going to be kind and respectful to all of our peers in here. We will call people whatever they want to be called. We will use their whatever pronouns they want to use. I appreciate that it can be difficult to remember and adapt to pronouns that we're not used to, but we will do our best. Okay. And it is really important that we affirm and respect the identities of any transgender and non-binary students that are in this class or any other class that you have. Supporting students with distress. This is really important. So you guys have heard of these CARES reports. This is not going to get anyone in trouble. It's essentially going to get somebody to check on them, to do a welfare check. And this is hugely important because if somebody's not coming to class and I'm not seeing them, there can be all kinds of reasons why. And I'm not going to know if they're in trouble or they don't like my class or they're watching the videos on, it's not going to, I'm not going to be able to make that type of report. But maybe you see someone down the hall who it's like, oh, they barely come out of their room. Or you see someone that's now who used to just drink socially and is now really drinking to excess. That's a sign of a mental health issue, a dramatic change in drinking or marijuana use or whatever it is. That's a sign of self-medication and that kind of thing. And using these CARES reports, again, it's not going to get them in trouble. It's only going to get somebody from the counseling office, from a rapid response team to try and reach out and make contact and make sure they're okay. And it'll put them in touch with resources that could be really helpful to them. It is absolutely okay to submit an anonymous CARES report, but they ask that you put your contact information so they can get more information if they need it. But if putting your name in is going to make you not do it, don't put your name in. Okay? I think probably all of you are aware of the number of suicides we had last year. Right? It was pretty scary, and you can help somebody just by submitting a web form. And again, they are not going to get in trouble. We had the people who respond to these CARES reports come to our faculty meeting, and I specifically asked them, I said, if someone reports they're concerned because their suite mate is drinking to excess in the dorms, are they going to get in trouble? And they said, no. They're not going to get in trouble from the CARES report. That those are separate, the people who get them in trouble are not the people who come with the CARES reports. Okay? So if you are worried about someone, this is a reasonable action to take. Okay? The other really cool thing is we have a counselor embedded in the College of Textiles now. I don't know where his office is. I believe it's up on the 4th floor where the design labs are. And that's going to be, I think, a really great resource. And I will make sure I get you his name and website. I have it because I reached out to him about a student last spring. Okay. And then, have you guys heard about this new thing that everybody in the College of Textiles gets? What is it? I'm looking for the app. Task Human. Have you guys heard about that yet? Okay, you will. It's rolling out. I know the graduate students got it, but you guys will get some messages about this. It's an app called Task Human, and it is a coaching app. It is not for mental health issues. It's not for counseling and that kind of thing. But let's say you there's like all kinds of there's entrepreneurship, so here I'll read it. The main categories that are across the top are professional development, physical fitness. Dr. Joines said the chair yoga class he did was really fun. I have not tried any of it. I just found out about this on Friday. Healthy eating and food choices, mental and emotional support, not counseling, it's just support. Anyway. Spiritual practice and guidance, financial literacy and coaching. That's the first one I think I'm going to reach out to. I found you can click different things. So I was looking at retirement planning, and then I was looking at the coaches, and one of them I'm like, oh, I sort of like how she's talking. And you can look at their LinkedIn profiles. Home and family coaching, personal growth and development. I think there's people who will help you with resumes and that kind of coaching, career coaching. So the college has paid for absolutely everyone who's part of the college to have unlimited time on this app. And the way it works is, so the first one I'm seeing is cross-cultural communication, and then it's got a bunch of people who do that, and then there's people who are online right now. If I wanted to talk to one of them right now, I could just click on them and talk to them. There's people that are available later today, tomorrow. You can chat with them in the app to see if you want to talk to them or not, and then everything is done by video chat within the app. And so the idea behind this was I think the founder has ADHD like I do, because the act of like, okay, well, I want to talk to someone about financial planning. Well, that means I've got to like find someone that either does it online or is local, which means I got to do some Google searches and I got to talk to them, and and I don't like to talk on the phone, and it's like all these steps before you ever like get to chat. And so they're taking all of that out, and you can just, if someone's got a green circle, you can just hit the button and be on a video call with them and ask them questions. So again, I have not used it. I was impressed with the guy who came and gave the presentation on Friday. You will get a code for unlimited hours or credits or whatever they call it. So watch for that. So don't just delete the Task Human email when you get it. I would guess it's going to come from Jeff Stockroff. Guess, not sure. But anyway, keep an eye out for that, because that might be something that's really useful to you. Especially, the career planning and stuff seems like a great idea. Okay, I've already gotten a couple DRO letters. I have not opened them or looked at them. But the really cool thing about doing exams in Gradescope is like we get your accommodations set up in Gradescope and they're there for the whole semester. So for sure I will honor all of those. We have electronically, this university's diversity policy. Nobody is doing SU or auditing. Incomplete grades, if that ends up, go back and read that later. Class evals. Thank a teacher. So you can thank a teacher, which could be me, but it also could be the TA. So the TA will offer people who struggle in any of the earlier exams, he'll offer one-on-one sessions. I do the same thing, but sometimes Zimu's just done a fabulous job, and it's really really nice to thank a TA. And you might have TAs in other classes and not think that you can use that, but you can use that for any TA. And it's a big deal for the TAs to get that. It's something that if they're wanting to become a professor and that kind of thing, that's something they can include in their packages and stuff. So, and so if you're in one of those big classes like physics and your TA is awesome, do one of those for that person. Okay, and there's all your policy, rules, and regulations. Keep learning, protect the pack, and then all the pandemic stuff that I think doesn't have to be in the syllabus anymore, but there's a new variant going around that may or may not be good with the vaccine. So who knows? So I left it in there. I didn't pull it out yet. Okay, so where are we? We are still at 1:45. Okay, 12:20. Okay, so that's enough syllabus, right? All right. Tell me a polymer, like, who knows the name of a polymer? Polyethylene. Okay, you guys can shout them out. Polytetra what? Fluorine?
Yeah.
PTFE. What else is that known as? What's its trade name? Anybody know? Teflon. What else? Polyvinyl. So we need something else. So we're going to say PVC, polyvinyl chloride. How about that one? What else? Silk. Yeah. I can't draw that one. There's lots more. What else?
Cotton.
Cotton. Oh, we're on a natural polymer kick. Rayon. Rayon and cotton are the same polymer, actually. Nylon. DuPont forgot to trademark the word nylon. Big mistake. That's nylon 6/6. That's a specific one. What else? Nitrocellulose, yeah. That's very much like cotton, but it's got nitro groups on it. And it's soluble. And it'll go boom. It's called gun cotton. What are your soda bottles made out of?
Also, I don't know how to say it. It's
PET. Yeah, that's how you say it. Polyethylene terephthalate. PET is totally acceptable. You guys will quickly learn that my handwriting is terrible. Somebody say something?
Cellulose.
Yeah, I got cellulose. Oh, I have cotton. Cotton and cellulose. Cotton is cellulose. Well, it's plant-based cellulose. We'll put cellulose here too. My graduate student makes nanocellulose from bacteria instead of getting it from plants. Then it doesn't have any lignin, which is also a polymer. If somebody says polyester, what do they mean? They mean PET. What else? Kevlar, yeah. Nomex is almost the same thing. You guys heard of Nomex? So for now, I'm going to draw the bends. Right? Oops. So all that's different is this one's straight across the ring, and this one is there's only one CH in between, right? So it's bent. Sorry, I'm getting too low. Yep. Any others? What are some applications of polymers? What? Clothing. Yeah, we hit a lot of those. Polyester, silk, cotton, nylon.
There's PFAS and whatnot, which is used as, if I remember correctly.
Right, but PFAS actually isn't a polymer. It's got lots of fluorines, but they're smaller molecules. That's why they can get all over. Rubber, yeah. Natural rubber is usually cis polyisoprene. Cis 1,4-butadiene. Is that right? No, that's not. Anyway, we're not going to be overly worried about names. Construction, there's lots of polymers in construction.
Most water bottles are some form of polymer. The ones aren't metal, at least.
Right. They're mostly PET and polycarbonates, except for then we got afraid of bisphenol A, BPA, and so now there's like water bottles are typically some form of polyester or polycarbonate, but they're not usually this one anymore. But if somebody says polycarbonate, this is usually what they mean. Styrofoam. That is the foamed version of polystyrene. That's why it's sty.
Is it styrofoam? No, it's not styrofoam. I'm trying to remember what the polymer is that you can't take to a certain temperature when it's TG and used in drinks or used to hold under.
Yeah, that's polystyrene. It's the foamed version of polystyrene. Okay, so I drew these polymers on two sides. There's the dividing line. We missed polyurethanes and some other ones.
Chain versus step growth.
Yeah, that's what it is. But before we get there, what does someone notice? Look at the structures on the two sides. What's something different?
You have more simplistic ones versus like more compound ones.
These are simpler, yeah, right?
Like isn't PE in PET?
Polyethylene? No, it's just you. So polyethylene, the repeat unit is CH2CH2. So polyethylene terephthalate has a CH2CH2, but it's not made from an ethylene monomer. It's really, the naming's confusing. Now let's do C. Do you see a pattern on this side?
They only have poly. Except for
Right. It has a poly name too, but so here, polyethylene, polystyrene. This is made from the ethylene monomer, the styrene monomer, the tetrafluoroethylene from vinyl chloride. So their names are poly and the name of a monomer. Over here we say polycarbonate, polyamide, I didn't write it down. Polyester, these are also polyamides. It's poly in the name of a linkage. So there's some difference in the names. What about if if I take a pencil and I run it through the backbone, so if we ignore all the side groups, right? So the hydrogens, I can take those off, right? And have them go, they're really sticking up, right?
So they're all carbon?
So carbon-carbon wraps around, carbon-carbon wraps around, carbon-carbon. So what did you say?
Carbon-based?
Yeah, they're all carbon-based. We can draw some siloxanes and stuff that aren't carbon-based or phosphazines. There are some that aren't, but all, you want to narrow that a little bit. It's an all-carbon backbone, right? What's going through the the actual backbone? It's always carbon. Over here, I've got carbon, 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 carbon. You're going along. Oxygen, carbonyl, carbon. That's an organic functional group, right? And it's got an atom that's not carbon. This organic functional group essentially has two hands, right? So like if I look at an alcohol, it only has one hand. But an ester, right, or a carbonate has two hands. So when they have two hands, we call them linkages, or I call them linkages in terms of polymers, because I can link two groups together, right? Does that make sense? So an alcohol is a functional group, but it's not a linkage, where a carbonate is a functional group and a linkage. So we've got that. Here, we've got a carbonyl and an NH. You guys remember the word carbonyl? Means C double bonded O. C double bond O is a carbonyl. So this is an amide. This is an ester. This is what? NH carbonyl. An amide. Mm-hmm. This is a carbonate. NH, carbonyl, NH, NH, carbonyl, oxygen. This one you've probably heard of, urethane. This one is a urea. You ever heard of a polyurea? You have? Not commercially.
No, it's so indigo dye, like the scientific name, like indigo dye. I think it has urea in it. I don't remember the full name of it though, but it does have urea.
Urea, right. But it's not going to be an indigo dye. A dye is not going to be a polymer, right? So polyureas, nobody calls them that. Why?
Humans tend to make assumptions based on names of things. Nobody would take it seriously.
Sounds like pee, right? Polyurea, it sounds like something you don't want to wear. Any polyurea that's commercially made is called a polyurethane, whether it is one or not. But often when you're making a urethane or a polymer that's urethane or urea based, often they are polyurethane ureas, meaning you have both types of linkages. They're more complicated. So your lycra, spandex, probably the seat cushions are a foamed polyurethane. And again, I'm saying foamed polyurethane. I don't know if it's urethane or urea. But you're never going to hear somebody saying, oh yeah, it's a urethane, it's a urea foam. They say urethane. Don't want it to sound icky to the consumers. So, these polymers are typically, but not always, made from a, I'll do out the whole. Made from a monomer that has a double bond attached to something. That R group is a hydrogen, we have polyethylene. If that R group is a ring, we have polystyrene. If that R group is a chlorine, we have PVC. This, right, CH2 double bond CH with attached to something, we call, when we think of this as a group, we call it vinyl, right? So that's why this is vinyl chloride. And why you've heard of vinyl. Not all of this class of polymers are made from this type of monomer. There might be a methyl group there. And then, of course, it could be 4 fluorines. We've got Teflon. But they tend to have this kind of, this is what we're starting from. It's a monomer with a double bond. And this is what we call chain growth polymers. Okay, so these are chain growth polymers. We're going to learn about chain growth polymerization. Over here, we have step growth. Very, very different polymerization mechanisms. The chemistry on how you make these two are very different. Which one do you think is typically more expensive to produce? Yeah. We'll learn a lot of reasons why that's true, but why do you intuitively know that?
It's much more complicated.
More complicated. Yeah, probably the monomers are a lot more expensive, right? Most cases that's true. The mechanism to get these to polymerize is they polymerize step by step. It's not a chain reaction, it's a step by step. So you have to push these really hard to get a high molecular weight. So a lot of things about these polymers make them more expensive to produce. What's the most recycled polymer? Post-consumer waste. Oh, I don't know. What's the most recycled synthetic polymer? Post-consumer waste. I don't know where cotton falls in.
Is it PET?
It's PET. It's PET. People will say that polystyrene is not recyclable. It is recyclable. You can melt it and reprocess it. It will cost more than it does to make it new. So will it be recycled? No. PET is it more expensive. So the economics make sense to recycle it. So in Maine, they have a bottle law. So you pay 5 cents for every can and bottle, more for glass, which is weird, but yeah, every plastic bottle, they're returnables. You have to return them and you get your deposit back. Now, there's some really great things about this. There's never any bottles or cans laying around. People pick them up, right? It adds up pretty quick. You get you take your bag of bottles back, you might get $20. And you've paid that money, so you want it back. So all of the aluminum in PET, the vast majority of aluminum in PET is being recycled through returning bottles and cans. So our little towns dump doesn't recycle any plastics because there's none of the valuable plastic. They can't get anybody to take it. None of the valuable plastic. There's very little of this in the waste stream. So if you are recycling, you are returning your returnable soda bottles, that PET is going out in a different waste stream. It's not going to the dump into the recycling. So they can't get anybody to buy any plastics. So they recycle cardboard. And they used to recycle glass, but I'm not sure that they're still recycling glass. Glass is very energy intensive. You can melt and reprocess glass an infinite number of times. It doesn't break down. Polymers break down every time you process them. But the energy to produce, to melt and reprocess glass is very high. And if it's not sorted, it's an issue. So if you're not sorting green, clear, and brown, it's a big problem. And it breaks and it can cut people and, anyway. So it's gotten harder and harder to recycle glass, which is too bad because it used to be we washed and recycled. But we washed and reused, which is even better, right? Washed and reused. But all of this stuff, and we'll talk more about this throughout the semester, all this stuff, it's way more complicated than it is at first blush, right? Because I'm like, oh yeah, it's better to wash and reuse those bottles. But if you factor in the carbon footprint to get the clean water and the energy required to wash and sterilize a bottle, its carbon footprint might be bigger than a plastic bottle, a single-use plastic bottle.
Are you washing when you wash all the dishes from dinner?
Right, but I'm talking on an industrial scale, right? Like a brewery or that kind of thing. So it used to be you returned your glass soda bottles to the bottling plant and they reused them. That's, and it used to be small breweries would take their bottles and wash them and reuse them. And that just does not happen to the same extent anymore. And just the gut reaction, reusing it is better, is not necessarily true. Because of the washing and sterilization. If you factor that in, it might be, I don't know. And then, as we move to renewable energies, it definitely will be, right? Because the carbon footprint will come down as we're producing electricity from more renewable sources. So it's very complicated. I read a really cool study on getting ethylene, the monomer, from an agricultural source as opposed to from petroleum. What do you think? I immediately was like, oh, that's cool.
Yeah.
That would be very, very, very helpful.
Except for its carbon footprint is way higher. Way higher. Agriculture, carbon footprint is food. One of the best things you can do for the environment is reduce your food waste. Because the way we do agriculture produces so much carbon. And so if you wanted to factor in the carbon impact, it made the ethylene from the renewable source less desirable.
Do you know what is like the biggest pollutant in the farming? Is it like the machines that we use to harvest the crops, or?
I don't think so. I think it's more related to fertilizers, the energy to produce the fertilizers, the energy for the machines, and and all of that. So, and if I remembered more of the details from that paper, I would be able to tell you. But it was really an interesting case study. I was like, oh, this is really not what I would have expected. Now, do I think that research is, research into renewable monomers and renewable, Hey, you looking for T200?
No.
Oh, then you're early. I'm like, oh, I have 15 minutes, but no, I don't. I have 12. So I totally lost my train of thought.
Something
Oh.
if you knew where the article was.
Yeah, no, so like, as we move to more renewable energy sources, a lot of these things will shift, right? As far as, from my perspective, because a lot of people are really upset about the plastic trash in the ocean. Very big problem. Not denying that. But for me, my number one environmental concern is the amount of carbon we're putting into the atmosphere that's driving climate change. That's my number one concern. Now, knowing how to make plastics and monomers from renewable sources and plastics that break down and that type of thing, so that when we are using energy sources that are renewable, that are not carbon producing, it's going to shift everything. And then but we've got to get, anyway, it's a complicated question. We're going to talk about it in a few weeks when we talk about paper or plastic. And we're going to get into the weeds on paper or plastic. Okay? Who's got some questions? So since I don't have Moodle going and I don't have the first assignment up, I can just email it to you. But one of the examples, you're going to have to turn in 2 questions you have about polymers. And so one I used to get all of the time every semester, and I haven't gotten in a few semesters, is about why can't I put my styrofoam container in the microwave?
GG.
And it's about the foam, but yeah. Another one is like the dentist is making a polymer filling in my mouth, and he or she put a blue light, shined a blue light. Well, why? So they can be silly. We'll get acrylic nail questions sometimes. That I'm not saying that's silly, but I'm just trying to give some examples. They can be medically related, bone cement, that kind of thing. So whatever you're interested in. Why is my boat float? Here's a good one for you. I still whitewater kayak some, but before my daughter, I used to whitewater kayak a lot. Throw ropes, piece of safety equipment, they're not made from nylon. Even though nylon rope is better than a basic polyethylene rope. Why don't you make them from nylon? You're on the right track. Polyethylene's density is 0.9. Water's is 1 gram per centimeter squared.
Float.
Polyethylene ropes float. So, that kind of thing. Okay? So on Tuesday, you're going to come with your questions. Okay? Whether you've entered them into Moodle or not, you've got to come to class with at least 2 questions you have about polymers. It's one of my favorite days of the semester, so make sure you come with your questions. That's our saga. So, who's got a question they want to share? Go ahead.
What sort of, don't know the best way to phrase it, but like what properties are we really looking for in the things dentists use to make things like Invisalign?
Okay.
Like the stuff they're going to shove in your mouth and leave, and
So,
be left there for days or months. Or
yeah,
years.
so it totally depends on what the application is. But dentistry is like all about personalized medicine, right? And they do a lot of personalized stuff. They use a lot of 3D printers at the upper levels. But Invisalign, one of the most important things is that it's very moldable. So you got to be able to get it to fit just the way, but not be a mold to your teeth, right? Otherwise it wouldn't move them. So the mechanical properties are very important on the Invisalign, but then it's also got to be safe
I guess.
in your mouth, right? It's got to be comfortable.
Be durable enough that you're not gonna start dissolving it. It's like
Yeah.
I have retainers I wear overnight, and it's like, yeah, after like a year, it has to make sure you don't start adjusting it or not adjusting.
Yeah. Your mouth is a pretty hostile environment, so it's. But plastics are fairly inert, right? They just sit there. It's one of the problems if they get disposed of improperly. So and then there's all kinds of other polymers used in dentistry as well, and those properties have to be very tailored to the specific application. Who else has a question? Go ahead.
I know that when you recycle plastics, the polymer chain gets shorter and shorter and shorter, and that's why we can't recycle them forever. But like, why do they get shorter? And like glass doesn't. Well, glass is different, but
Glass is very different. Glass is a three-dimensional network, and so those bonds break and reform and break and reform. Polymer chains break all the time, but they're so big it doesn't matter. But when you reprocess them and reprocess them and reprocess them, each time they break, you get to the point where it's going to impact their mechanical properties. Mechanical properties are very sensitive to the length of the chain. Okay. And then they also, we as consumers, we don't like things that aren't pretty, right? So if it gets a little bit of a yellow tint, we don't want it. So that also is a big reason why you can only recycle it so many times, because often you get little burnt pieces, like a little, some molecules become small and just a few of them can change the tint of the whole batch. And so you gotta be, that's why they only ever use so much post-consumer waste. Because they don't, and that's why soda bottles are not from recycled material. We like them to be pretty and clear, unless it's 7-Up for some reason. But so we recycle soda bottles into fleece, right? We take soda bottles and make fiber, but we never take fiber and make a soda bottle because you can't get it as crystal clear as consumers want. You had one, didn't you?
Oh, yeah, I was just gonna ask, is it okay to microwave plastic wrap?
Yes. That's the short answer. Yes. It doesn't even melt in the microwave, usually. So, here, you can go home and do an experiment. Ball up some plastic wrap, put it in the microwave with no food. Just put it in the microwave, see what happens. It's not gonna warm. It is not going to warm up. Who knows how a microwave works? Yeah. The microwave is the right frequency to make water vibrate. Right? Did you want to add something? Somebody? Same thing? Yeah. So it makes OH bonds, which water has an oxygen and 2 hydrogens, so it has lots of them. It makes those bonds vibrate. It makes NH bonds vibrate, so those are in proteins, and it makes a few others, but it doesn't make carbon-carbon and carbon-hydrogen bonds vibrate. So if you take something if you take polystyrene that has no food in it and put it in the microwave, a nice clamshell that's clean, it's not going to melt because it's not going to get hot. Who's put the clamshell, the polystyrene clamshell, the white styrofoam container, who's put that in the microwave and they've melted it? Yeah? Did you eat the food? Yeah, me too. I ate it. Usually there's very few additives, and the polymer is just melted. It's not getting in your food. And the styrofoam is mostly air. That's why it's so light. So when you melt it, it's like nothing's there. So we used to do an outreach project with like high school kids and younger kids, where you have just a little bit of solvent in the bottom of a beaker. And you're like, how many packing peanuts can you put in the beaker? It'll be like 10 or whatever. And you start putting them in, you can put hundreds in because they dissolve and there's like no volume to them. They're all air. So, yeah. Because usually they don't notice that there's a little solvent in the bottom. But, I have to tell you the story about my friend's wife. So, he and I worked together. Another scientist. His wife was a social studies teacher, and we teased her more than we should have. But so she was dealing with 3 PhDs in chemistry and material science, and and then she was the only social scientist, social humanities, however I want to say that. And Thanksgiving, and she wanted to put this candle that went in the glass. She wanted to put this candle on the table, but the wick, the last time she had used it, the wick had fallen down and the wax cooled over the wick. So she's like, I'll just heat it up in the microwave. And she's like losing her mind because she thought the microwave was broken. And it was like a built-in one, and it would have been a big deal if the microwave was broken. And we're like, it won't work on a candle, like how do you, and it's like most people don't know that. We just would be not very kind. So we boiled some water and then set it in the hot water to get the wick out. But you can't microwave something that doesn't have NH and OH bonds. They don't vibrate, doesn't heat up. Because you can think of heat just as molecular motion. It's one way of thinking about it.
So we would heat up in the microwave?
Hmm?
We would heat up?
Oh, yes.
Yeah.
Yes. Yep, for sure. Because you are polymers, water, and a little salt. That's it.
I'm probably a lot of salt. I eat a lot.
There's some bone and stuff, but the bone is still a polymer composite. Go ahead.
Are carbon nanotubes polymers?
Depends who you want to ask.
Okay.
Usually, all carbon, this is funny, right? How do you define an organic molecule? Forget the BS version of organic that the general public thinks, because I'll get on my soapbox. It's meaningless. But organic in chemistry means what? Who knows?
Carbon-based.
It's carbon, right? It has carbon in it. Except for if it's only carbon, it's usually considered inorganic. Isn't that weird? Because it behaves like inorganic materials. So graphite, diamond, carbon nanotubes, buckyballs are often thought more of being more like an inorganic material. So a nanotube is one of those things that's hard to classify. Most people would not call it a polymer, but it's also, in my mind, it's not really wrong either. But usually it's not called that. And we'll talk a little bit about different words and vocabulary when we actually start looking at some PowerPoint slides and stuff. But polymer, right? Poly means many. Ruining my slides. Mer, anybody know what mer means?
The same. The same.
Unit means unit. So it's many units. And then sometimes I have people who take French and they're like, the sea. No. I don't know if it's Greek or Latin, but another word that we use is macromolecule. Macro, big, molecule, we know. And so then, do we want to call a nanotube a macromolecule? Do we want to call it a molecule? If it is, then it is a macromolecule, but is it more of a particle? It's like there's a lot of semantics, and I don't know what people who study in that area how they class it right now. But usually it's just like nanotechnology, right? They're carving out their own sort of in between, because that's not really a molecule and it's not really a particle. Go ahead.
I know that like for cotton, cellulose is the base unit or like material, but can you take just like pure cellulose and make a fiber?
And make what?
Like a polymer or a fiber?
So pure cellulose is a polymer.
Okay.
To make it into a fiber, you have to get it into solution, which is, if you start with cotton, is super hard. If you are a little bacteria that we have up in the lab, you can produce these nano fibers that are almost pure cellulose easily. They just make it. And then they live on it. You guys ever, seen a big scummy thing on water? Or kombucha? Anybody made kombucha? The scum on the top? That's almost pure nanocellulose made by the bacteria that are fermenting whatever it is you're going to drink. Not my favorite. But we can make nanocellulose scaffolds. We call it the kitchen method, where we just buy SCOBY that's used for fermentation, kombucha and other fermentations. You can buy them on Amazon and make nanocellulose that we use chemicals that are harder to buy, off of Amazon and that kind of thing. But you can go to Lowe's, right, or whatever, and get KOH, potassium hydroxide. I'm like losing my words. And then that strips all the bacteria off and all of that, and you get this white, really nice material and because it's cellulose, it has all these OH groups hanging off of it. So you can do all kinds of chemistry, and we've used it for filters, and people have used it for scaffolds for different medical applications and stuff like that. So if you want to start with a solid form of cellulose and spin it into a fiber, it's challenging, but we do it all the time. It's called rayon. But if you're a little bacteria, you can make it pure from the start without doing a whole lot of chemistry. And that's all because, cellulose is, if you look at the molecule of cellulose, it looks like it should be super hydrophilic. You guys remember that word? Mm-hmm. Okay, everybody? So it's got all these alcohol groups. It should be super hydrophilic. And if you can get it into water, it's happy. But it's so crystalline and it's so hydrogen bonded to itself that you can't get it to dissolve in the water. And you can't melt it. It'll just burn. So in order to process it, you have to break those hydrogen bonds, and you do that by changing the chemistry. You nitrate those hydrogens, those alcohol groups, and make it into something else that disrupts the hydrogen bonding, disrupts the crystallinity, and then you can dissolve it. Then you can spin it or extrude it into a film or do whatever it is you want to do. Excuse me. And then you convert it back to cellulose. So it's nice and stable and doesn't dissolve and doesn't do, it's got all these good properties, but it's really hard to process. You have to do this chemistry. That's why we talk about regenerated cellulose, which is rayon and cellophane. We can also talk about gun cotton. That's always fun. It goes boom.
What triggers it to go boom?
You know, like nitrate, right? We've all heard about like fertilizer and like, oh, it's dangerous and that kind of stuff. Yeah. So if you attach an NO2 group, and there's lots of them, it'll go boom, right? Trinitrotoluene, TNT, right? So gun cotton it's pretty stable. I mean, it's highly flammable, but it's pretty stable. You can store it and that kind of thing. It doesn't just combust in the atmosphere, but if you like hit it with a hammer, it's gonna go off and that kind of thing. And if you light it, it burns really fast. Go ahead.
What's really funny about like gun cotton is that like the person who found it was literally like unknowingly did it, but he literally actually dropped like a cotton dishcloth into like a bunch of nitrate like solution.
Yeah.
And he like let it off to dry. The moment it completely dried, it set on fire and exploded in his kitchen. And then later on, he figured out like, oh wait, we can use this for photography. And so we actually use it for films that way, and that's why a bunch of fires happen in films, and like a bunch of like there's like a special building just for putting films in, and even like in museums and stuff where you have like what is it called, authentic films from that time period are like literally sheltered in like a bunch of glass and everything, because if they get contact into the air, they will literally explode. And it's really funny of like how long the history is, but it's also like the fact of how dangerous it is now. And it's also used in nail polish actually, not just cellulose.
Yeah, because you can get it to be soluble. Yeah. So it's and the story is apocryphal. So like it's told many different ways. Usually it's the scientist, and they know who did it, but I forget his name. I have it. We'll do a history of polymer science, but often it's like they say he cleaned up a nitric acid spill with a cotton swab and then set it by the burner to dry, because back then you didn't just throw them away. You made them for your lab, so if you're like, oh, it's not dirty, I can use it again, you just let it dry, and it went poof. But yeah, there's lots of different versions of that same story. And no one knows if any of them are true. Who else? Go ahead.
Okay, so this is like a pretty broad question, but like microplastics, right? They're like awful for like our health and like the environment in general. So is there like any like solution to those like long term, other than making like just polymers in general like more biodegradable, or is it just something we're gonna have to like just live with going forward? Yeah.
I think that's an open research question. It's one of those things. We're on the upper end of the food chain. I don't know how bad they are for us, but like the little tiny organisms and stuff is not good, right? Because of size and quantity and that kind of thing. People are actively studying the shed off of polyester fleece, because initially it was like, oh, microplastics, it's from their breaking down and their and that kind of thing, and we need to, but a lot of it is shed off of fibers and clothing and that kind of thing. And there also used to be, and I don't know if there's any that are still on the market, but it used to be that you could get a lot of facial scrubs that had microbeads. And that was not a good idea. So some of the microbeads weren't so micro, but they were still really small, and they like caused problems in wastewater treatment plants because they could clog things up, the filters and stuff. And then the ones that truly were like actually micro, would pass through the filters and then are in the environment. And we also, before it was like oatmeal, ground up apricot pits, and just like it was natural things that you used in scrubs. And it seems like that we've gone back. I haven't seen any beads in a scrub, face or body scrubs in a long time. But yeah, if you see that, if you see microbeads and that kind of thing in a personal care item, I would encourage you to buy something different. Just because there's no need to use a plastic bead for that application. There might be some allergy reasons, but that could be, a special order or whatever. Yeah.
So like, what? I'm trying to think of how to like phrase this. I just am curious. What is the like most common way that like polymers are formed in nature, and like what do they like share in common?
Okay, so there's two huge classes of natural polymers: proteins, polysaccharides. And so proteins are amide bonds, the same as nylon. So proteins are polyamides, and your RNA makes proteins. And makes enzymes, and and if a mistake is made in a protein or an enzyme, it can be really devastating. Could be disease causing, could be life threatening. So so that our bodies have, that RNA has the sequence of the amino acids, and it's more controlled. The polysaccharides, they're much more messy, and they're made through a different system, and I don't know the biochemistry behind that. But like amylose has sort of random branches and that kind of thing, and if you have a extra branch, or it doesn't matter. It's not nearly as regular. And I'm sure there's other natural polymers, but I can't think of. Those are the two primary classes for sure. There's glycoaminoglycans, but they're essentially polysaccharides.
What was the first synthetically made polymer, and what was its impact on society?
The first one that was commercially successful was called Bakelite, and it was fully synthetic. It was a phenolic resin, and Bakelite is still made. When you touch it, it feels nice. One of the reasons it's still made, and it was marketed as the material with 1,000 uses, and it was everywhere, and and you have certainly seen Bakelite items in the past. Bakelite jewelry to this day is still highly collectible. My great-grandmother had tons of it, and Mom and I got rid of almost all of it when I was young, and I'm still a little mad about that now. I have a Bakelite necklace that was hers that I will wear when I do the history of polymer science lecture for sure. And I have it on in some of the videos, but it's like below the cutoff, like the beads are like way down. You only see the colored string. You don't see the actual Bakelite in most of the videos. The little short videos that are in Moodle and stuff. But did I get your question? Leo Baekeland was the guy who made it. None of the early polymer scientists had small egos. They almost all named their polymers after themselves. So,
when was that created?
Late 1800s, early 1900s. People didn't believe polymers existed. they thought that they were just, I'm really struggling with words today. What is the word? Colloids. They thought they were colloids well into the 1920s. So a colloid is a collection of molecules that acts more like a single molecule. So, like, you can have colloidal metals where they're, like, suspended and sort of similar to emulsions. Yeah, so we celebrated 100 years of polymer science in 2020 because Hermann Staudinger put forth the macromolecular hypothesis in 1920, which essentially was polymers exist. Long chain-like molecules exist.
The same year, someone got the right to vote.
Hmm.
Not so much, no.
What else?
Is PFAS a polymer?
When people are talking about PFAS, it's usually not a polymer. And the ones that are all over in the environment and doing bad things are not polymers. Because highly fluorinated polymers are not soluble. So, Teflon, you can make a vascular graft out of Teflon. You can make Teflon sutures. You can use Teflon for catheters, right? I mean, we can implant it in us, and it's no problem. But it's getting folded into this whole PFAS, where if it's a high molecular weight polymer, it's not soluble. It's very stable, and cooking on a Teflon pan, a nonstick pan, is no problem until you see it flaking, right? Because you're cooking on it, especially if you like take your pan and then put it in the broil to get broiler at 500 Fahrenheit, then you can start to be actually breaking down the polymer a little bit. But in general, that Teflon is hugely stable. It's not gonna hurt anything.
Would you say most polymers are relatively safe in terms of like consumption and use?
It's additives you have to worry about. Most polymers, like if you had some little kid that was in the factory, or like where they're, and there's all the pellets and they're all pretty colors and they start eating them, they're just going to come out the other ends. It's not the vast, vast majority. Now, are there highly toxic, deadly polymers? Yes, there's neurotoxins and stuff, but they're proteins, right? I can't think of a synthetic polymer. The polymer, I'm not talking about any of the additives they might put in there, that you couldn't eat and it wouldn't be a problem.
What are examples of the additives that they would put in that make them unsafe?
So, you can have, sometimes leftover monomer can be a problem. Some of the plasticizers, which are used to make them softer at room temperature, at the operating temperature. These molecules, and if you ate them, it'd probably be just fine. But what happens is, if they're, as a one-time thing, if you did it every day, a lot of these molecules mimic hormones and can be estrogen mimics and and have other endocrine disruptors and stuff. And I just pretend at biology. I'm not biochemistry. I'm not an expert by any means in that area. So like we as Americans, this country got all bent out of shape about BPA, right? You guys are too young to even remember when BPA was this big thing. And so, like, you'd get a nice new water bottle and be like, BPA free. And now we all want the keep cold metal ones, so the plastic ones are out of favor anyway. But, right, so it would be BPA free, and BPA is bisphenol A. It's really hydrophobic. It's not very soluble in water. It was never going to leach out of your water bottle in any amount that would cause you any harm. Now, in the infant bottles that you heated milk in, I would want it to be BPA free, right? Because they're tiny and they're eating out of, if you're bottle feeding and they're eating out of bottles all of their meals, then even a little can be a problem.
Dosage depends on who you are.
Yeah.
I mean,
But water
6'5"
bottles.
bodybuilder is not going to be messed with the same as.
Right. 5 pound infant. Yeah. So so they're essentially, you can't buy a water bottle that might have BPA in it and all this and that. But we don't care about the phthalates that we use as plasticizers. Now, the phthalates are endocrine disruptors, I believe, and they've been banned by Europe. So there's commercially viable alternatives, but we don't care about those because that's not been in the pop culture, right? So we are unconcerned about that.
Where do you find phthalates? Like, in what products are they normally in?
There's so they're in the plastic lining that's inside of metal cans with food, and they're in a lot of things, but that's really where you would end up consuming it, because you might not know, but canned food is usually cooked directly in the can, and that's why it's so safe, right, from bacteria and fungus and all of that, because it was cooked and then sealed. It wasn't like cooked and put in the can. It was right in there. And so that you don't taste metal. All those cans are lined with plastic. So.
Are the commercial alternatives more expensive, and is that why, like, they haven't been replaced, or is it just?
I don't know. But Europe, the EU they're more scientifically minded with their regulations.
Yeah.
How's that for a diplomatic way of saying it?
Yeah, it's like half of their. We don't eat bread according to the EU. In a lot of our restaurants, we eat pastries.
Yeah, there's way too much sugar and not enough fiber for it to be classified as bread.
Depends on which kind of bread you buy, I guess. Like, what kind of bread are you used to eating?
Yeah, the vast majority of
Yeah, we put sugar in everything.
yes.
When I was in Italy, like the hostel I was in, they provide us as breakfast and stuff, and so they often always put like butter and stuff, like spreads and stuff, because the bread itself was like not that great, and even then they didn't have bread. They had like croissants and everything else but bread, because we couldn't handle their bread, because they just knew like, oh yeah, there's gonna be a lot of people that are from America coming in. They're just, you can't handle it. It was really funny because I was like, whoa, this is a weird bread.
Good.
Do you have a favorite polymer?
Oh, I used to always say synovial fluid, or say hyaluronic acid, which is in synovial fluid, but I haven't studied that in a very long time. So, yeah, I really like. I like molecules that, or I like, one of the reasons why I enjoy polymer science is how the structure builds up. So like you can have a simple polymer and it folds into a crystal, and that crystal, like, so you have this hierarchical structure. So like spider silk is super cool because these spiders can spin the silk, and then it has this awesome mechanical properties, but how they spin it really matters, so they can make a really strong and tough thread that they would drop down on, the dragline thread or the spokes of the web. And then they also can make capture threads. So they're taking a water-soluble protein and processing it in different ways. And they're going from a really tough and strong fiber to one that's super stretchy and stick. And then the like sticky part that's on the outside is the same protein. And they're just processing it a different way. So like, I think molecules that you can do stuff like that with, and we can't do any of that with the spider silk, even though we can make the protein. We can't tailor the properties the way it does.
Do we just not have the technology to do it? Is there active research going into that right now?
Yeah, so Paul McCartney's daughter, that's the fashion designer. Linda, no, that's, what? Stella McCartney, yeah, Stella McCartney. She has made some things out of spider silk that's made using recombinant DNA technology. So I think they have a yeast so they have these engineered yeast that are in these big fermentation reactors, and they isolate the protein and they spin it, and they can spin it into a fiber. And the company that's doing that, they started with Black Widow silk because they knew the marketing would be really good. And they're doing that to like finance, because they want to eventually they want to use it for medical applications, but they thought they would be regulatory wise and that kind of thing. They'd be able to make a product faster. And so like she's made hats and different things. But yeah, we can't tweak it the way the spider can. Yeah. They've been trying for a long time.
When did this might be out of your ballpark, but now I'm just curious, when did like us genetically modifying yeast to produce different things, when did that start? Because it's kind of popping up.
I don't know when it's started, when they started using it in polymer science. And then it was, I think, bacteria. But they were able to, or E. coli. So maybe 25 years ago, they started making certain types of proteins, but they couldn't make spider silk because it was the spider silk protein, because it would kill as soon as the bacteria started making it. I think it was an E. coli is what they started with, so it would kill it. Like the protein was incompatible with the host. So they could never do it recombinantly. And then until this one company solved the problem. Their name might be Bolt. Professor Hudson, who's retired from here, he used to consult with that company, and that's why I know a lot of the stuff. I think he had a tie out of they gave him a tie eventually out of the spider silk, but he got to meet Stella, and his daughter is a fashion designer, so it was really like. So she was super. And now I can't remember. She got to meet her too. Anyway, it was like he has some connections in fashion, and so he was super excited that he got to meet Stella. What else? You guys can stall me and then we won't do any slides today. Go ahead.
What's the difference, like, on a molecular level between nylon 6 and nylon 6,6, and why do they, like, behave differently?
It's pretty cool, actually. So, and it's so subtle. All right, so if I do NHCH2 6 times NH carbonyl CH2 4 times carbonyl NH CH2 6 times NH. All right. And it just keeps going, right? So that's 6,6. Because there's 6 carbons and 6 carbons. If I developed the naming system, I'd call it nylon 6,4, but I did not. So you count the carbonyl carbons, which is irritating, right? Okay, so nylon 6, NH, CH2, 5 times, carbonyl, NH, CH2, 5 times, carbonyl. So this would be carbonyl NH, carbonyl NH, carbonyl NH, carbonyl NH, bunch of CH2s, carbonyl NH, NH carbonyl. So you're just flipping them more or less. There's a little carbons off by one. You're just flipping them over. This is made from a ring opening polymerization. This is made from a step growth polymerization. So very different on their synthesis, but yeah, they pretty similar.
And how does that translate into different properties?
They have different crystal structures because the crystal structures are going to be dominated by how the NH can hydrogen bond to the carbonyl, and since they're a little bit different, you're going to have some different crystal structures. I don't know how big the property differences are. I've never looked it up, but I can tell you, if we take all of these and make them into oxygens. Oops, not that one. We do the same thing here. So if we go from the amide to the ester, properties are dramatically different. What can the amide do that the ester can't do? Polyamide can do something, think about freshman chemistry, this polyamide can do something that I just was talking about that an ester cannot do. Hydrogen bond, exactly right. So hydrogen bonding is the strongest of the intermolecular interactions, right? So if we have a polyester with no rings in the backbone, this is just CH2 groups, this would spin into nice fibers and all of that, just like nylon does. But it's going to dissolve in common solvents easily. It's going to degrade. Esters are not super stable, so like this is going to degrade. So I don't know if this particular one, if I converted all of these to esters, right? If the whole chain was a polyester, I don't know if that would degrade on the time scale of months or years or weeks, but it would degrade slowly over time. So yeah, it's not a useful fiber, you know. It can be certain types of what we call aliphatic, just meaning there's no double bonds, no rings. Polyesters are used in sutures. Go ahead.
What's going to be the difference between like a PE and a UHNW PE and like how they're made? Is it just more like repeat units or?
UHMW PE versus PE. And then we can talk about LL, D, PE. We can talk about HD, PE. And we can talk about LD, PE. Talk about spectra. They all have the same repeat unit, right? So polyethylene, CH2, CH2. UHMW. Ultra high molecular weight. We can make a hip implant out of ultra high molecular weight polyethylene. And it'll last 10 years, something like that. What's the difference between HDPE and LDPE? High density and low density. And they have different recycle codes. They have essentially the same repeat unit, and polymers are weird. You can't mix them together. You can't mix LD and HDPE together. So the low density polyethylene has a lot of branching. And that branching helps prevent crystallization. So we're going to make sandwich baggies, cling wrap, out of low density polyethylene. Maybe garbage bags. But we might be trying to control that density for the garbage bag a little more. So maybe we'll want to control it. So then we're going to use what we call linear low density polyethylene. So it's not branches. It's got a comonomer. It's actually a copolymer. So they've got a copolymer, a second monomer that they polymerize with the ethylene monomer, not the poly, right? That has a little squiggly branch off the side, so it's more controllable. HDPE is going to be your milk jug, your laundry soap container. This is going to be your hip implant. It is a machinable plastic. There's not a lot of plastics that you can machine like metal, right? You can process plastics in a lot of different ways, but most of them you can't like put on a lathe, okay? Ultra high molecular weight polyethylene is one, Teflon is another. And then we could add Spectra to this list, which is, again, same repeat unit, but you're processing it into this fiber, and the chains are all lined up in the fiber. It's hard to do, but it makes it really strong. So with the same CH2, and we write this repeat unit as CH2, CH2, even though we could write it CH2, right? Put the parentheses around, because the monomer is CH double bond CH2 double bond CH2, right? But there's absolutely no reason why you couldn't write it. Like these would be the same, N versus 2N, but nobody does the bottom one. It's just convention. We like to see the monomer. Okay. So this is another, when I'm in this class, this is one of my favorite polymers because it can do everything. It's pretty neat.
Is there a reason that the ultra high molecular weight polyethylene is used sometimes instead of like a titanium joint?
The what goes into the femur. If you guys ever watch, there's all kinds of videos available. If you ever watch a hip implant surgery, it's nasty, and it's like they're like ripping things apart. I mean, it's tough to watch. So they saw off the head of the femur, and then they put they've got the ball part of the ball and socket, and then it's got a stem that comes down that goes inside the top of the femur. That part is almost always metal. The cup that it snaps into can be ceramic or plastic, and I'm not sure that they do metal on metal.
I saw a documentary. It leads to metal shavings. It'll get in your blood.
There was problems with, so they made a mistake with the early hip implants. They did all the wear testing on unsterilized polyethylene cups. They did the wear testing. They sterilized them, and it reduced the molecular weight at the surface where the reactive gas sterilized and broke down the molecular weight. So then when it was in people, there were these little tiny wear particles. And they were sort of the same size as bacteria, so it caused chronic inflammation, which leads to a cascade of bad events. So, so in this country, we still use a lot of polyethylene cups for hip implants. In other countries, ceramic hips are more common. If you ever need a hip implant, or you have a loved one, that your friend, whatever, that needs a hip implant, just tell them no nickel. Bad outcomes with nickel. Watch The Bleeding Edge.
Yeah, I did. Yeah.
I show The Bleeding Edge every semester in TE 566, which is polymeric biomaterials, which is in the spring, and it's a fun class. Not everything we talk about is gross.
I also know somebody who had the hysterectomy with the machine that was in the
Yeah.
and had some stitches pop.
Mm.
Yeah, it's very scary. Your organs can just fall.
It's a Netflix documentary, and it is, yeah,
Like real life?
yeah,
Oh god.
yeah, The Bleeding Edge.
There's also the
It's sensationalized a bit, but I mean, they're also not out and out lying about anything. But yeah. So anyway, be in the right frame of mind when you watch that, if you ever choose to watch it. So.
they don't show anything gross.
No, they don't. But if you know somebody that's getting a new heart valve or something, it might not be the best time to watch it. Or it might be the absolute best time to watch it. It all depends on your perspective. So this documentary is talking about medical devices and how little they are actually regulated, and the loopholes, and the major loopholes that are in our regulatory system. And people knock the FDA. It's so underfunded. I think it's amazing what the FDA is able to accomplish when it is so underfunded and understaffed. It's, you can't really blame them when they don't have the money to do what they need to do. And so then we can go back to Congress and blame them, because that's where the real problem is. Go ahead.
Sorry, it's about this again. So is Spectra just UHMW in a fiber? Is it just a line?
I don't know how high. I know it's a high molecular weight. I don't know if it's UH.
Okay.
Okay, I don't know. And I tried to, I used to teach this class where we talked about crystallinity and crystal types and all that stuff. And I'm like, I want to talk about spectra. And I really couldn't, I think a lot of it is still trade secret.
Mm-hmm.
And so I was not, but I haven't looked lately, so. And then it gets, the stuff that was there was like over my head. It's like too deep in the weeds of the crystal structures and stuff like that for me. I wasn't that invested. I could have sat down and figured it out, but I wasn't going to spend hours on it. So. I wanted the cartoon version. I couldn't find it. So, waiting for Dr. Shang to get it to do something. Or Dr. Ford. Should ask her, actually. What else do you guys have? I keep looking at, I don't trust that clock isn't moving, is it? It's moved since last week, but it's not moving. Second hand, it's not moving.
Do we use any polymers in our brains?
Oh, yeah, well, your brain would be liquid if it wasn't for polymers, right? The cells have to grow on something. So your extracellular matrix is polymer based. Your bones are a fiber based composite.
When did we, like, as humans start figuring out how good of like a structure to build things on polymers was?
To start using polymers as structural materials.
Yeah, like I think I heard from like a friend who's like a BME student that they're learning that it's like one of the easiest way to like print organs is like with like a polymer fiber spun structure.
Yeah, so since the term tissue engineering was coined by Professor Langer in the 90s, or it might have been earlier than that, but anyway, they've been using polymers as the scaffolds for the cells. So it's intricate and just totally entwined with all of tissue engineering. But for like construction, like actual structural materials, I don't know how far we've certainly used fiberglass and composites for a very, very long time. But there's more and more polymers and structural items that are plastic. Airplanes used to be mostly aluminum. Cars used to be mostly steel. And that, you want to make them more fuel efficient, you make them lighter and lighter. And so cars are more and more composite material, and aircraft, especially military aircraft, are composites. They're polymer composites. One of the big problems with polymer so like metals, it's a lot easier to know if it's gonna if it's fatigued and gonna fail. They can do ultrasounds on metals, and I don't know how they read the ultrasound, but they do ultrasounds and they can see the micro cracks and stuff. It's way harder in composites, and that's been an active area of research for a long time. I have a friend whose whole career he's a civilian that works at Cherry Point, and has been on studying fatigue in composites. And that's why the submersible guy was not smart. The submarine over the summer that imploded, right? It didn't implode the first time, didn't implode the second time, but yeah.
You mix 4 materials together.
Yeah.
So many.
I studied fatigue this summer here.
Oh, okay.
And I read so much about composite fatigue, and there's just so little about it because it's so hard to understand.
Yes, and I think
there is.
Yeah. I think there's a lot. I think the military knows a lot, but I don't think that they've unclassified.
Yeah, that's the fun thing. Like the military, they come up with all these cool toys, and you eventually get them, but then once they come with the better stuff.
Yeah. So the composites, I'm sure, like the composite failure is a definite military advantage to like know how long you can safely fly that plane and different things, and how you can assess damage. So I think that a lot of the work that's been done there is not available to industry and to us. I don't know that, but that's my suspicion. Because I know they have been studying it for decades.
You can kind of guess, like, I expect kids to be able to put together, the more you put together, the more weaknesses it has.
The more different types?
The more different types of things you put together, the more weaknesses it has. If nothing less, just from video games.
Yeah, well, so I don't know if you like in the actual composite, like if you're making a composite part and I think you can have many components to the composite, but the more you every time you have a joint or you're putting something else together, different parts together, that's a site for failure. So yeah. I'm a little claustrophobic, and like the sub stuff, I'm like, I couldn't, before they knew they were dead, I'm like, no, I can't listen. I can't even listen to this on the radio. I can't, just would change the channel. I'm like, oh man, being in the dark in that little tube, I'm just like, oh no. And then months later, when they started releasing more information about what they think actually happened, I was like, oh, hell no. They had all these sensors embedded in the composites, and all of the sensors started going off, and they tried to surface. They aborted the mission and tried to surface. They knew. And the sub wouldn't rise. And they don't know why it wouldn't go up. But it wasn't. Think of that dad with his son. I'm just like, ugh. But just looking at the thing, like above the water, and looking at them get, like the diagram of how they were, I'm like, oh, you couldn't pay me millions of dollars to go on that thing, let alone have to pay money to do it.
I've been in submarines. Yeah, they're cramped. Admittedly, this is a beach submarine in a museum.
Yeah, no.
I think it was, I don't remember which one it is, the one in Illinois.
Mm-hmm.
U-505?
Yeah, I'm not going in that museum.
It's crazy to me how, like, sunken ships are usually, like, essentially mass graves, and they're, like, that's, like, one of the least respectful mass graves that we, like, as humans treat, because we're like, oh my god, it's a ship, it's at the bottom.
Well, that's because, all of the whole human is gone, right? So even the bones and all of that, it's gone. What's left are shoes. Leather shoes and stuff. So I don't know what happens now now, like most of our shoes would float away. But the Titanic, those old leather shoes are still sitting there. But there's no bones or anything. Because but the bones will eventually dissolve in the ocean. So I think that's why, it's like, but it is, yeah, I know there's people who had lots of problems with the Titanic tourism or whatever you want to call it. What else? We've hit lots of topics today. Anybody else got some? Stitches are usually made of polylactic co-glycolic acid. They are polyesters, and they are made of a copolymer because polyglycolic acid would degrade too fast, and polylactic acid degrades too slow. So they make a copolymer. And can I do it correctly? I don't know. I think that's glycolic acid. It could have another CH2. And I think that lactic acid is that one. So if water can get here, this bond can break. Having a methyl group near it makes it harder. Like the water's not going to come from this side. It'd have to come from an actual single water molecule, right? And this makes it harder for the water to get there. It makes the whole thing a little more hydrophobic, and so it doesn't degrade. And then if we look at PT, you got this big hydrophobic ring. So you got that big ring. It's really hydrophobic. It keeps the water away from the ester groups. So this doesn't degrade in water at an appreciable rate, where this will degrade in weeks and this will degrade in years. You can make, instead of doing, if you need a bone screw, screw in your ankle or something like that. You can make it out of polylactic acid and it will degrade slowly over the course of a year or more. So obviously you don't want sutures that do that. Non-degradable sutures are often nylon, and often they, especially in veterinary medicine, I'm not so sure in people, but often they're really brightly colored, so you can find them.
Is it more common to be thinking about nylon 6/6 or nylon 6?
I don't know which one. And then there's 610. There's others that are commercially produced. Often when people just say nylon, they mean 6/6, but not always. And often when people say polyester, this is what they mean, and that's probably almost always. Mm-hmm.
Will you go over what we need to do kind of this week in terms of like Moodle wise?
We're easing into the semester. Put your questions into the forum, even though it's due last January. I'll change the date eventually. I'm going to try. So a lot of the Moodle assignments are set up for the online group, and so I'll get those changed. So like the quiz, we'll do quizzes in here. Remember, I told you if you're here, you get full credit, so nothing to stress about. They're a reality check for both of us. Okay? So those you'll just take a picture of and stick them into Moodle. But the way it's set up right now is, I tell you, take the quiz, watch the correction video, correct your quiz, and so you like have to upload it so these things unlock. And so I got to take away bunches of that stuff.
Are we supposed to do like the introducing ourselves?
That's optional. But it's nice if you do it. Okay, yeah. All right, so who is TE? About half. Who is PCC? Who is TT? And you are chemistry? So TE is textile engineering, PCC is polymer and color chemistry, and TT is textile technology. They are required to take this class. You're taking it as an elective. So who has or is currently taking organic chemistry? So put your hands up higher. Everybody else look around. It's good to make friends with them.
Debatable how much.
It is, so when we start doing polymer synthesis, yeah, they can be a good resource for you. If you really, I will say, if you really struggle with, if you felt really uncomfortable in freshman chemistry, you don't remember, if you really, really hate it when I do structures like this, right, where I don't write the carbons and the hydrogens, there is the first section of Moodle is chemistry review. Look at the skeletal structures. Look at the skeletal structures. That one has too many. Oh, that was supposed to be an oxygen. That's why. Okay, so skeletal structures. We'll talk a little bit about them, but that is that's a great thing if to review intermolecular bonding, like hydrogen bonding, van der Waals forces, dipole, reviewing that, and reviewing skeletal structures. The organic chemistry will teach you what you need to know. You don't have to review that.
Mm-hmm. So, are we gonna be doing are we gonna be learning a lot about measurements and stuff, or is that more like in polymers? Cause like, I'm
Yeah.
99 ortho student, so I'm doing like benzene, aldehyde, benzene,
Yeah.
like, acid pheno.
Yeah, none of that.
Okay, cool.
Yeah, none of that.
I hate it.
Polymer, the organic chemistry you need for polymers is really simple.
Yay.
Because it has to be simple and it has to really work, or you can't do it enough times in one molecule to make a polymer. Okay, so,
I like that. They're gonna be a bunch of
all right, so we'll see you on Thursday. And hopefully I'll be like, oh, Moodle's all up to date to my best of my ability on Thursday. That's the goal.
I want to do everything. Like, I want to do like,
Okay, so announcements, that's usually like, I will more frequently email you through the Google group, and then they won't be copied there. But things that are really important, I try and make sure I do through Moodle so that it's there for you can always find it. So like exam announcements and that kind of thing, I try and remember to do it this way. But it is a whole lot easier to just be in your email and do the Google group. I didn't update the quick links, but I will get those. So this is, all the basic course stuff that we have. This is old, but it's useful if you want to look at it. You can, all the documents we talked about on the first day, the introductions forum. It's fun for me to read them if you want to do it, but I'm not going to require it since we are not. I force the online students to do it, but you guys, it's optional. And then I'm super happy they put this navigation back. That drove me nuts that they took it away when they first switched to Moodle 4, which might have been before you guys started here. But anyway, okay. So the next section is the chemistry review, and then we are in Module 1, Intro to Polymers. And if you look, the first thing in every module is this study guide. Okay? If you can do these things before the exam, you're going to do great. Okay? I tried to make them as detailed as possible, and if it's not on that study guide, it should not be on the exam. But I'm human, so sometimes I make mistakes, but it shouldn't be there. Okay? For the modules that are covered in the exam. Then we have instructional materials and learning activities. This tells you what to read in the ebook. And then there's a lot of H5P activities. And then materials for review, for your reference and for review. So like PDF of the slides, stuff like that. And then some extra videos. Okay. And then this was what we did on Tuesday. And what you are going to do 1 week from today is this assignment. So remind me towards the end of class, I'll give you some time to try and find a partner or two. What I want you to do is make a Google slide. I used to have everybody print them and we would just put them on the document camera. I'm not going to make you come down to the front of the classroom. You'll just talk from your seats and explain one of your questions. Okay? Somebody from your group, you can create a new question. I don't care. Right? And it can be something that you can answer very readily. It might be your question is a known thing. And you can answer it. Your question might be an active research topic. That's also cool, right? Both of those are totally fine. If it's not something that you can just answer in a slide, then you just want to tell us more about it. Did you learn something interesting? Why are you interested? Whatever. So you can I used to be like 1 slide, but you guys can have 2. So there is a link right here to this Google folder, which you should all have access to. You should have gotten an email about it this morning, right? Most of you? Yeah, okay. So put your slides in there. And we'll just click through them. And yeah, it's a really fun day for me, and it's not meant to be stressful. This is not a polished presentation. We're just talking, right, with our almost 30 new friends, right? Okay, so this is not meant to be stressful. This is just a good, why polymers are important and where they are, because they're everywhere. Okay, so that's module 1, and I try all of the modules are set up with these same topics. Okay, so hopefully you can start to find what you need. Okay. Okay, so I talked about the assignment. Let's do a week from today, because I'm not going to ask you to do it the day after Labor Day. Okay. I'm all discombobulated today because Wake County canceled school. It's a beautiful day. So I was racing. I was working from home in the morning because my daughter's at home, and so then I came, and then I'm just anyway. So I don't have my list of things of what I wanted to hit, except in my head, and then it's like garbled. So the assignment is due. The presentation assignment 1 week from today. I'm going to try and remember. Help remind me that give you 5 or 10 minutes at the end of class to meet somebody. And we're going to start the slides. And I'm thinking there, and I showed you Moodle, and I'm thinking there was something else I was supposed to do, and I can't come. It's not coming to me. Okay. So I didn't double check the hours, but they almost never change. So the tutoring center, you guys know where the tutoring center is? Right up there? Nope. It's above the atrium. We are under the departmental office. Okay. So yeah, it's right over there, and then my office is just a few doors down. But I haven't been in there a whole lot because, well, first of all, we started a week before Wake County started, and then I'm trying to get my daughter situated in middle school, and the buses are sort of a mess. And anyway, so I'm working at home a lot right now, but that will shift, and you'll be more likely to be able to find me in my office, especially in the mornings. But the tutoring center, they will have people for sure that can tutor for T200. Okay. Has anyone purchased access to the ebook? Did it go smoothly? Yeah, great. Okay. Sometimes Dr. Painter's not the most tech savvy, but anyway. Okay, wonderful. It's a good value. You get to keep access to it, I think, indefinitely. And compared to what textbooks normally cost, this is a nice value. There is the hardback version is available at the library. Okay, that was from the. I forgot we were going to do this. Okay, well, I think that we've sort of already done this. I'm going to make you do it anyway. Okay, your chairs move so you can talk to one another. We're going to do a CI exercise. Thinking that everybody can get the initial definition. But anyway, so S is for state your definition. E is for elaborate. The second E is for exemplify. What's an example? And that doesn't have to be literally PVC or whatever, right? You can think about how you can exemplify what a polymer is. And I is for illustrate. And the illustrate is my favorite part, so don't skip that one. So let's take 3 or 4 minutes, get with at least one other person, and then we're going to look at them on the document camera. And if you write this and you don't want to tear it out of your notebook, I will just take your notebook and give it back to you. Okay? So. All right, so there was our CI exercise. And I've got what is a polymer video. I made this during the pandemic, and it took me an inordinate amount of time, so now I inflict it on you, okay? And now I could do this so much faster, but it was like one of the first things I did. So, what is a polymer? Poly means many, mer means unit. So polymer is a molecule made from many units. Polymers are very large molecules, otherwise known as macromolecules. They are made from monomers, like ethylene. Monomers polymerize into long chain-like molecules, like polyethylene. If 1,000 monomers polymerize, we get a polymer with 1,000 repeat units. The repeat unit is what's enclosed in the brackets in the polymer structure. The number in the lower right-hand corner of the brackets is the number of repeat units, or the degree of polymerization. Oh, ads go away. Okay, so how many repeat units? N. What's the degree of polymerization? Yeah. N. N and N. Yeah. Okay. Oh! Didn't hit stop fast enough. Yeah, there we go. Okay. So, how many monomers? N. So, a number in front tells you how many you have. A number on the lower right-hand side of the brackets tells you how many repeat units. Okay? I'm making a specific point out of this because every semester somebody messes that up. Okay? So if you give me an answer, that tells me you have N butane molecules, and those are a gas. Okay? That is not polyethylene. I don't know why you have the brackets, but you have N of them. Okay? So this is something that people make a mistake about. So just remember, a number in front, just like you learned in high school chemistry, that's how many you have. And a number in the lower right-hand side of the bracket is how many times what's in the bracket repeats. And usually for polymers, it's N, meaning a big number, or it's a given big number. But it doesn't have to be. You can do this in organic chemistry, not inorganic, anytime. So, like, you've seen me do that when I've done CH2 6 times when I've been writing out nylon 6. So that tells me this repeats 6 times, okay, inside a structure. Okay. What was the other thing we had there? Oh, how many polymers did we make?
1.
1. Yeah. And then we touched on this when we did the CI exercise. What's the difference between the monomer and the repeat unit? But now that you're looking at this chemical structure, what is the difference?
They're linked together.
They're linked together. So what's missing?
The double bond.
Right. So in the repeat unit, there's no double bond. In the monomer, there's, I guess I'm pointing at my screen, but so in the monomer, there's a double bond. Most double bonds are pretty reactive. That is a very reactive molecule, and it's a gas. That is a very inert molecule. That's a solid. Okay. So again, so we've covered this polymer, many units, right? Poly means many, mer means units. So polymer science and engineering, we can think of this as the science and engineering of large molecules, of macromolecules. Lord Todd was the former president of the Royal Society of London. That's sort of like the president of the National Academies of Sciences here in the U.S. He said, I am inclined, this was in the 80s, I think, I am inclined to think that the development of polymerization is perhaps the biggest thing that chemistry has done where it has the biggest effect on everyday life. It's a pretty major statement for a chemist to say. I don't even think he was a polymer chemist. And if we stop and think about where we use polymers, where polymers are, that we're made of polymers. I said this on Tuesday. We are polymers, water, and salt. A few extra things. But that's, that's it, right? This chair is a chair, the cushion, the clothes we're wearing. Pretty much any photo I can put up, there's going to be polymers in it, any day-to-day photo, right? So we can talk about synthesis, which we will do the basics of synthesis in this class. We will talk about structure-property relationships, which is really important in the engineering side and the chemistry side. We won't get into processing very much, but I'll try and mention it here and there. We'll talk a bit about polymer physics and physical chemistry, and I know that you guys have not had physical chemistry or thermodynamics, but so we won't talk about it like with equations and that kind of thing. But at the end of the semester, we will talk a little bit. We'll talk about thermal transitions and the little bit of physical chemistry you need to know to really understand those and make predictions, getting back into that structure-property relationships. And then characterization is not something we'll cover in this class. And last fall, people did the introductions forums, and they had so many pictures of their pets that I put these in, and then I was like, oh, I can't take it out. That's Valentine. She was 15 and blind and deaf, and we had to let her go last spring. She had one last really good Christmas, but it was past time. And that's Sandy Sue, and she's, for us, I've done a lot of elderly dog rescue, so she seems super young. She's only 7 or 8, but she's spunky and full of energy. And my daughter just got a kitten who's 10 weeks old, and I should have had a picture. Sky. So she is super cute, and she is going to be the boss of the house. So she's like this big, and she's already bossing the dog around. All right. So It was stuck in there weirdly, but that was the end of. I showed that many slides, and then came into class and the next day and started here. That's why the dogs were there, and I looked at it and I'm like, oh, I should take them out. And I'm like, nah. Everybody likes to see puppy pictures. Okay, so what are polymers and why are they important? We've really covered a lot of this already, right? Because a lot of the questions you had on Tuesday sort of showed the breadth of where polymers are. So why are they everywhere? Why have they had such an impact on our daily life? It's not the first bullet, right? We know they're long, typically chain-like molecules, but they have an extraordinary range of properties. Even just polyethylene, remember we talked about its range of properties going from cling film to spectra and hip implants, but they have just a huge variety of properties. We can make a bullet-resistant glass. We can make goo. They're all polymers. Okay? Most are very inexpensive. Most are very expensive to process. Okay? So, a lot of times, as consumers, the general public tends to get really fixated on post-consumer, like what happens after. And plastics don't do well once you throw them away, right? They sit, they're inert, if they are not disposed of properly, they can cause huge problems, right? We've all heard about the giant dead zone in the ocean where there's the plastic island and that kind of thing. Substituting a paper straw for a plastic straw, in my opinion, is not good. It is not good. It is only good if you are considering the second half of the straw's life cycle. Paper tends to take at least 30 times more energy to process than the equivalent thing in plastic. It also takes a lot of water in its processing and production. Plastics don't. So if you want to factor in the total life cycle and the carbon footprint, and personally, my biggest concern is carbon, and the amount of carbon we are putting into the atmosphere. Not to say that the plastic island in the Pacific isn't bad and isn't a big deal. It is. But to me, I think we've got to stop the carbon production. That's number one. And the other things are sort of downstream. Now, as we shift to renewable energies that are not they don't have the same carbon emissions as even a natural gas powered electric plant, then a lot of this stuff will shift. But right now, I'm happy to say single-use items are not ideal. They're not always bad, but they're not ideal, single-use items. And we should reduce single-use items. But singling out plastic single-use items and using more paper is not a sustainable answer. Okay, so there's my tirade for today, okay? And personally, I think they're really fascinating. I think it's really amazing that polymers are used so many different places, that they have you can tailor their properties so much. They're easy to process and all of that. So, okay. So hopefully I've thoroughly convinced you that polymers are important. And this was covered in the video, but very quickly we can look at it again, right? What's inside the brackets is the repeat unit. The number in the lower right-hand side, that tells us how many repeat units we have. And we can call it, this is also called, if it's the average, it's the degree of polymerization. The degree of polymerization is abbreviated as capital X or as DP. Our books and I will typically use capital X. But it is also very standard to see DP. Mhm.
Will these slides be posted if we
Yes, they're already in Moodle. They're in the review section. Okay. So almost always, I just leave this blank. Right? What's sticking out, we leave it blank. It doesn't matter. If N is large, what's hanging out on the end, it doesn't matter. It's such a small part of the molecule, it's just sort of irrelevant. So there are N groups, but normally we don't care what they are, and when often we don't know what they are, so we just leave it blank.
How do we not know what they are?
Because if you don't know why the reaction stopped, especially in chain growth, in step growth, you know what they are. If you're reacting an A and a B to polymerize, there's going to be an A and a B on the end, unless it's too reactive and then it reacts with something, some contaminant or something like that. So. But if you're buying a commercial polymer, you're not going to know what it is because you're not going to know what initiator they used, that kind of thing. So what we're going to do now is think about how big polymers are. Oh no. I usually have my little polymer visual aid bag in my work bag, but I switched and it's not in here. Okay. It's all right. So how big are polymers? So let's think of it in terms of measurements we can more readily understand, more familiar to us. So let's think about polyethylene. So if the CH2, if that is about 2.5 centimeters long, it's about an inch, it's about the size of a super ball. You know, those little bouncy rubber balls, right? Okay, instead of a few angstroms. If we have 20,000, how long is our stretched out polymer chain? What do I need to do? All right, 1,000 times 2.5. So 2 times 2.5 is 5. So I've got a lot of centimeters. How many centimeters in a meter? 100. How many meters in a kilometer? 1,000. So I'm going to end up with half a kilometer. So think about that. Water is the size of a super ball. Polyethylene, not even a really super high molecular weight polyethylene, is half a kilometer long. 0.3 of a mile. Do you think those molecules are going to behave differently? Does it make sense, right? A little solvent molecule that's the size of one of those super balls, or the size of a couple of those super balls, if we had them in here, right, they'd bounce all over, it'd be no problem. If we had one polyethylene molecule, we might not fit in the room. I didn't calculate the volume, but I mean, it's huge. It's huge. These polymers, macromolecules, are so big. They're just so big and so different. And that's why people didn't think they existed. They just didn't think molecules could get that big. Okay. If the number of repeat units is 20,000, the mass of one repeat unit is 28 grams per mole. What is the mass of the chain? What do I need to do? What did you say? Multiply. Exactly right. I got to multiply 20,000 by 28 grams per mole, and I'm going to get 560,000 grams per mole. Water is 18 grams per mole. Very different. Very, very different. You instinctively knew how to do this, right? Because you know, if you know the mass of one repeat unit, you can figure out the mass of the chain if you know how many repeat units there are. It's not hard, right? I want you to remember that when we get to module 4 and we're using all the weird statistics notations and stuff, and it's like, oh, I don't know what those variables are. You do know how to do it, okay? Just remember that. You know how to do it. All right, we're going to skip this one. So, homopolymer, copolymer, polymer blend, or monomer. So we've already covered polymer really well. The monomers are the building blocks, right? Monomers are molecules that polymerize. Typically, they're small, but there are some exceptions. We can talk about macromonomers. Those are really important in polyurethanes. Homopolymer. What do you think?
It's all the same type, or like you said, it was.
Yeah. So homo means same, right? So it's the official definition is it's made from one monomer. But then we have this exception where if we can imagine a monomer that it was made from, so if it's perfectly alternating AB, 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 we can draw a monomer that was AB instead of A and B. So there's some exceptions there. A copolymer is a polymer made up of two or more monomers. A blend is a mixture of two or more polymers. So just remember, copolymer, homopolymer, that's like a single polymer. A blend is two or more polymers. Sometimes people confuse copolymer and blend. We won't be spending much time at all on blends. To really understand polymer blends and why they're super weird, you need to have taken physical chemistry or thermodynamics. But think about this. High molecular weight polyethylene will not mix with low molecular weight polyethylene. That's weird. It's the same thing. It's just different molecular weight. It won't mix together. Polyethylene and polypropylene. All you did was add a CH3. They won't mix together. They won't blend. You can't make a homogeneous blend. Okay. But, again, polymers don't mix because of their thermodynamics. There's not enough thermodynamic driving force for them to mix unless they're really, really similar. Mostly if they can hydrogen bond to one another. Okay, so we started talking about this a little, but now we're going to really do this little mental exercise. Where do we find polymers? Okay, take a few seconds. Think about when you first get up. How many polymers do you use and come in contact with before you actually leave your house? So many.
I can't even count.
Okay, so let's start shouting some out. Let's start shouting some out. Sheets, your sheets, yep.
Yeah, my pillows.
Your pillows. Even if you have a down feather pillow, right? The feathers, it's keratin. It's a natural polymer. Yep. Pillows. What else?
My plastic lamp.
Your plastic lamp. Yep.
My plastic alarm clock.
Yep.
Phone case.
What? Your phone case. Mm-hmm.
My phone.
Shoes.
You can't make electronics without plastics, even if they're not plastic.
My laptop.
Yeah.
My
The,
backpack.
the chips require polymers in the processing.
What polymers are used in your chips?
Hmm?
What polymers are used in your chips?
They're photosensitive. They are used as masks to make the micro features that, you know.
Myself.
Yourself. Yep. Yep. Why? Yeah, your toothbrush, the bristles on the toothbrush.
Plastic on the toothbrush.
Yeah.
Toothpaste.
Toothpaste more than likely has polymers in it so that it like makes it stays there, right? To get the viscosity the way you want it, probably has polymers in it. Your shampoo doesn't run through your fingers. It has a viscosity modifier that's a polymer. I love it when water bottles say they're plastic, like plastic free. I'm like, it's got a, what do you mean? You got a silicone O-ring, you got, it's like, or when it's plastic free and it's a silicone bag or siloxane bag, I'm like, what do you think siloxane is?
Yeah.
Whatever.
There's
What
polymers in.
about like my wooden cabinets?
Oh yeah, wood is a polymer composite. And the polyurethane is polyurethane. It's right. So the finish, linseed oil would not be if it's you got a natural. That would be a lower molecular weight. Paint has polymers in it. I had a friend whose master's thesis was watching paint dry.
Oh, that's so good.
What else?
Cereal bowls.
Could be cereal bowls. Could be, but if they're ceramic, no polymer.
Where do ceramics fall in the classification of like materials?
They're ceramics.
Or like what's the breakdown?
So the main classes of materials are polymers, ceramics, metals. So
Is glass a ceramic?
I think so, but glass is weird.
It's the outlier.
So bad.
Yeah. So
People make such delicate things and then they're here with their like smash and then they're like beating it of it and I'm like, I don't know. I've watched a lot of people make glass. Is that not?
there's a reality show, the Glass Masters. That was awesome. It was on Netflix.
I
Amazing.
don't watch that. I just go to the Henry Ford and watch people make glass.
What else? Let's move on from like personal care and early morning.
Car, like this.
Lots of things in cars. What about transportation? Let's go to the second one.
So
Tires,
tires,
seats,
the plastic lining,
Like the stuff.
Steering wheel.
bumpers,
bumpers.
the windshield
Hmm?
wiper pump.
Yeah, the outside parts of the radio for sure. How about the what coats the wires, right?
No, 'cause I replaced it.
I don't have any gear heads this year.
Oh,
A little bit,
the windshield wiper
right?
pump.
Belts,
Belts. You have the
brake pads used to be. I don't know if they still are.
You have the seal between when you put the oil in your car.
Mhm.
The seal so that it
Yep.
doesn't leak.
Your oil more than likely has dendrimers, which some people call polymers, and some people say no, they're not polymers because they're not chain link. They're just macromolecules. But synthetic oil.
Magic.
There's definitely a polymer coating on the outside, and I would guess that it's Teflon based, or the good ones. And then the some are just metal with a metal coating. What about a Ducati? Motorcycle? Almost everything. It has the carbon fiber frame. Any mountain bikers? A lot of high-end bikes are polymer composite. I used to whitewater kayak a lot. That's the most expensive piece of polyethylene I've ever bought. Okay. Yeah, and a lot of this stuff that we don't ever think of has a lot of technology behind it. Paint is high tech. I was told years ago, and I assume it's still true, that 5 to 10% of the cost of a new car is in the paint, which is weird to think about, but it's the highest failure rate. So that's what's most likely to it has to go back and be redone or have to be touched up or that kind of thing. So there's a lot of cost in the paint. And let me tell you, when I was growing up in Maine as a kid in the 80s, well, yeah, they salt the roads and cars. I mean, pretty much every car in my childhood, you could see the ground through the floorboards, right? There were rusty holes, and it didn't pass inspection if the hole got bigger than a quarter.
My parents in their first cars, because we also grew up where it's like, they grew up in Toledo, where it's also cold and salty. They used to be like, yeah, all of our first cars, you'd go through a puddle and you'd be like, lift your feet up, or like the seat would rock back, and they'd be like, it's fine.
So cars don't rust like that anymore, right? They don't rust the same way, and that is thanks to paint and coatings and all of that stuff. And yeah, there's so much technology that goes into paint, and it's like something that we don't even think about. So polymers are everywhere. We could start up on medicine. We could do all kinds of things. So we covered everyday household stuff. Oh, we missed packaging and films. We talked about paint, adhesives. There's a lot more structural materials. Fibers. There is no microelectronics. There is no cell phone because you can't make the chips without a polymer. You need a photoresist to make the chips. Okay? So there is no cell phone without polymers. And elastomers are polymers. I can't think of an exception to that. They're all. So why? Why do we end at 1. Okay. I'm going to give you the last 6 minutes or so of class to find some partners to do your assignment that's due a week from today. Okay? And you can start if you've already got your 3, then you can start talking about when you're going to meet, or try and do it right now. Okay? We had talked about all the different places that polymers are used. And I'm just looking around this room, and, the majority of the things I'm seeing either are made from polymers, or polymers are part of the process of producing them. And then I'm looking at a big soundproof fabric wall up there, right behind you ladies, right? That's even textiles, right? So why are they everywhere? Why have they become such a crucial point of our daily lives? It's because they have so many different properties. They tend to be lightweight, especially in lieu of traditional materials. Okay? So, if we look at a hot air balloon, almost everything, except for like the burner where we got to have a lot of heat resistance, is made from a polymer, including the wicker basket, right? The wicker is a polymer composite. More and more of cars and airplanes are polymers and polymer composites. Less and less is made from metal. It's a big reason why cars have gotten more and more and more fuel efficient. Okay? Go ahead.
Can we circle back to wicker for a second?
Wicker?
Is it not wood?
It's like, it's a woody, fibrous, I don't know if it's technically wood, but it's like the twigs. It's like from a lot, you can make it out of the willow tree branches. So, yeah. We'd have to go to CNR and ask, is it wood or is it something else? Okay? We can make lots of things that are transparent. Most things that are transparent that aren't from polymers, this is where I might venture to say all things that are transparent that aren't polymers are brittle. Having toughness and transparency is pretty unique to polymers. I can't think of an exception, but I'm sure there is one. Okay? So shatter-resistant glass, bullet-resistant glass. That's supposed to be a jewelry store with bullets. The Louvre Pyramid, right? There's got to be a lot of security there. Right? So it's got to be shatter-resistant, bullet-resistant. Glues and sealants. I think I've got a fun video on the next slide. So there's a lot of natural adhesives. And nature can make adhesives better than we can that work in harsher environments. You think about barnacles and how harsh the ocean is and how they could really stick to stuff. We would like to be able to make adhesives like that, and we've mimicked the polymers and some of the structures, but yeah, it's not something that we've been able to commercialize very well. And I'll tell you a quick aside. Think about a Post-it note. It's sort of sticky, right? It's sticky, but not too sticky. So Post-it notes. They were developed by 3M, and they were trying to make, I think, super adhesives, like really strong adhesives, and they made this stuff that's only sort of sticky. And they were really fascinated by it, and it doesn't leave a residue, and it's got all these cool properties, and these scientists were like, product development, I'm sure there's engineers involved, right? They're like, this is cool stuff. And the bigwigs were like, nobody wants something that sort of sticks. Nobody wants that. No, stop working on it. But what they had done before they got the final, cut this out, you're not working on this anymore, is they had, in the pilot plant, made the first version of Post-it notes and had given them to the administrative staff in the executive suite. And then all the administrative staff was like, where are my sort of sticky notes? Where they're gone? I want them back. How do I get more? And the administrative staff is who convinced the bigwigs that, maybe this is useful. Maybe we should pursue this.
Maybe we should annoy our entire admin team.
Right. So, I love that story. Somewhere I've got some stuff about, we're going to look at some super glue commercials from back in the day. Heat transfer and flammability. Okay, so most polymers will burn, right? But you got to catch them on fire first. And so not all of them have they don't burn immediately. But let's start with heat transfer. You guys have all experienced this. So heat transfer, we really need some thermodynamics and all these horrible differential equations and that kind of thing. But just think about you're on a road trip, you go to a gas station. You need a cold drink. You reach in and you grab a soda bottle, plastic soda bottle, and you're like, it's not cold. If they happen to have the same soda or, they have something in a glass bottle, you reach in and grab it and you're like, oh, it's so nice and cold. Feels so good. But they're all the same temperature. The rate of heat transfer from your warm hand to the glass, heat always flows from warm to cold. The heat transfer from your hand to the glass is what makes it feel cold. The polymers don't transfer heat well. So even though it's cold, it doesn't feel cold because it's not. It's not pulling the heat out of your hand, right? So it doesn't feel cold. Where a can would feel nice and cold. Metal, glass are all better at heat transfer than polymers are. So what do we use as hot pads? We either use fabric, right? Even a folded up dish towel works pretty well. Or silicone, you can use a silicone mitt. What happens have you ever tried to use a wet dish towel to pull something out of the oven or grab the handle of a pan? Yeah, the water's really good. Water.
When you open a thing of boiling water, you open the lid away from you.
Yes, right? But if your dish towel is wet or if your hot pad is wet, you don't use it, right? Go get something dry because that changes the heat transfer, okay? So I tried to update all these slides last fall, and I'm expecting some of the ones that I had used for many years beforehand. So I don't have there's no good flammability one. Flexibility. If you take a piece of thin metal that you can flex, and you flex it back and forth and back and forth and back and forth, what happens at the fold? It breaks. Yeah. Most metals, most materials, if you flex like that, back and forth, even some plastics, if you flex like that, they're going to break where you're folding them. So some polymers have the ability to be flexible over and over and over. You can even make plastic hinges, right, that you can use over and over. But, a really good example is our running shoes, right? They're very flexible, and you can flex over and over in the same spots. Rubber elasticity. This is an old picture. This is from Coleman and Painter. Do you know before we had rubber tires, what the tires or wheels for the first automobiles were made out of?
I feel like
Somebody said it. Wood. Yeah, wood. Like a wagon wheel. They were wood. Horse-drawn carriages and wagons and stuff, animal-drawn, could be oxen or whatever, they only go so fast. The first cars were not very fast, but they could go faster than animals pulling a wagon. So you can imagine what the ride was like on the first wooden tires. Yeah. So,
No suspension.
Yeah, no. So when they were able to start making rubber tires, it was a major breakthrough. Polymers are hugely processable. And because they're easy to process, this is also one of the reasons why they're inexpensive. That's why we can make single-use plastics. The material's cheap and the processing is cheap. So I finally got a 3D printer. And I don't know what the octopus is actually doing, but it looks like a wolf pack sign to me, right? I used to have a CD, a read-write CD with the laser shining on it on here, and then I'm realizing you guys don't even barely know what those are. So I put a 3D printer on it. But it's you think about a CD. Almost everybody who had a desktop computer back in the day had a polymer processing plant inside their computer because the laser could encode the information by making ridges, making highs and lows in the CD that could be read with a different laser. So you had essentially a polymer processing plant in your computer. And back then, inkjet printers were thousands and thousands of dollars. 3D printers. They were available back then, but they were really hugely expensive. And now, a few $100s. You can get them for kids. There's just, it's amazing how the cost has gone down. So polymers are really everywhere. And it's because they have such a variety of properties, and they have properties that are really pretty unique. In one of the many sort of emails from the university that we all get, I don't know which one it was, but this one was one of those info ones where they were talking about in Tally, what is it, One Earth or something? So now all of the food containers are going to be compostable. And, and they're touting it as this really good environmental thing. And my first thought was, is it really? Because maybe it is, but it might not be. It's certainly better post-consumer. But if its carbon footprint is an order of magnitude higher or more, then what is it a good trade-off, kind of deal. So that was my first thought this morning when I was clearing out some of my inbox. So let's think about why polymers are so different from other materials. Oh, no. I left my visual aids. They're sitting on the dining room table. I know exactly where they are. Okay, 3 things that make polymers different. First one is molecular entanglements. You remember how we said think of solvent molecules as about the size of a super ball? And then we said a polymer might be a half a kilometer long, same diameter, but a half a kilometer long.
What's a super ball?
Like those little rubber super bouncy balls, like jacks and stuff.
I was picturing them as like the size of a baseball.
Yeah.
Yeah, no. They're like about an inch across.
We just call them rubber balls.
Rubber balls, yeah. So I think Super Ball was a brand name. So if you think of that as being a half-mile long rope, and then you've got 20 of them, and they're all in a room together, and somehow you can shake it and stir it, what's going to happen to those ropes? Yeah, they're going to all be tangled up, right? So polymers can tangle. They have molecular entanglements, and that is really going to change their properties a lot, right? The fact that they're tangled up means if I pull on them, they're tangled. They can't just slide. If I pull on it slowly enough, maybe they can slide past each other. But it's not going to be like a small molecule that, they're going to behave very differently because of that entanglement. So the summation of intermolecular forces, I call this one the Velcro effect. Okay? I usually have my little pieces of Velcro. They're stuck here, right? I got 2 pieces of Velcro. If they're stuck like this, I cannot pull them apart straight, right? I have to peel one off the other. Think of each little tiny hook and eye from the Velcro as one little intermolecular force. One little van der Waals force between one polymer chain and another polymer chain. Even if it's super weak, just to, van der Waals force. Induced dipole. Super weak. If you are summing them up over this half-mile long thing, it's going to be stuck together. You're going to have very strong cohesive forces, right? The polymer chains are going to want to stick together because these little forces add up to something large. Because the molecules are so big, they are not, there's not going to be, you need so much energy to try and get them apart. So, what does that mean in practical terms? It means that we can't get polymers into the vapor phase with just heat, right? If we heat a polymer high enough that it should vaporize, it's going to decompose before it vaporizes. It will break down and decompose before it vaporizes. Okay. All these things, these 3 things I'm telling you about, is really related to the length, how big these molecules are. The third one is time scale of motion. I call this the silly putty effect. Everybody know what silly putty is? Everybody? Usually somebody doesn't. So I guess now there's like all these thinking putties and stuff. Like, I don't know that my daughter would recognize the term silly putty, but she's like all into like thinking putty or fidget putty or whatever. So what happens if I take my silly putty, I roll it into a ball, and I set it here? Yep. Over the course of 5-10 minutes, it's going to flow into a puddle. So is it a liquid? No? Kind of. Yeah. Hedging your bets. Okay, if I take my silly putty and I roll it and I pull it really fast, what happens? It snaps. I roll it into the same size and I pull it really slowly, what happens? Stretches. So when I pull it really slowly or I leave it in a ball, the entangled chains are sliding past one another. If they have enough time to slide past each other, it's behaving more or less like a liquid. If I don't give it enough time, pull it really fast, it snaps. It's behaving like a solid. And we have a word for that. Viscoelastic. Viscoelastic. Visco is, that root means liquid-like, and the elastic is solid-like. So a polymer is going to act like a liquid or like a solid, depending on your time frame. The other thing you can do is change the temperature. Right? Temperature and time are very similar for molecular motions. Right? If I give the polymers enough time, they flow past each other. If I heat them up, the polymers move faster and they float. They can unentangle faster.
Okay, if that happens, if given enough time, they'll flow past each other. Why does that not happen if you have for example, the jewelry store window or the Louvre? Why hasn't it just
Yeah, because that polymer, it's glass okay, so we're going to learn about a temperature called the glass transition temperature. That's when it's not crystalline. It's when a polymer goes from a glassy material to a rubbery material. And so if the glass transition temperature is way below the operating temperature, well, then you're talking centuries for it to flow. if you're way above the glass transition temperature, you're in the melt, right? And so then it's going to flow more readily. So it depends where, essentially, if you wait long enough or you raise the temperature high enough, it will flow. So polymers are really unique in their properties because they're so big and because they entangle. Because if they're so big, if you add up all these little weak molecular forces, you've got something really strong. And then depending on your time frame, they can act as either a solid or a liquid. Makes them really, really unique. Macro Galleria is a website. 20-some years ago, it was a really cool website. It used frames, which were like new and special. Its user interface really hasn't changed in 20 years. Okay? So you guys will go to this website and be like, oh, this is retro. I'm thinking another 5 to 10 years it'll be cool again because it'll be so retro, it'll be cool. But it has great polymer information. And there have been some really great polymer education websites. And most of them have gone away for whatever reason. But this one hangs on. But you just got to deal with the weird and wacky. Wonderful. Interface. Let's take a look. So yeah, frames. Ooh, special. But okay, so there's 3 things that make polymers different. Here's the glass transition. What's a glass? So this is, the information in here is great. You can go to final polymers. Each level, there we go. Each level has a different theme. So polymers are everywhere. Some of this stuff is really funny because like the photos are pretty old. Oh, look, wooden shoes. Okay. So anyway, it's a useful website. It's the information is solid, but you gotta find what you want and deal with the sort of wacky interface. So, next question. How can polymers be so different from one another? Right? I think we sort of got some feel of why they're different from most other materials, but why are they so different from one another? And it really comes down to there's a lot of different types of polymers. So like the chemical structure can be very, very different. Kevlar and Nomex are very, very different in molecular structure than polypropylene or polyvinyl chloride or PET, that kind of thing. Very different. And then we can talk about the microstructure and crystallinity, and then if we have something that can phase separate, what's the phase structure, the molecular weight distribution can all change a lot of different things. And that's just sort of like the fundamental structure of things. How that we often talk about structure property relationships, that right-hand side, okay? And in this class, that's where we'll focus, structure property relationships. TE 466 will talk more about processing, so then you can start to complete this whole triangle, or however we want to think about it. So we can talk, and we will talk about how crystallinity impacts properties at a fundamental, sort of a foundational level. And then if you keep taking polymer classes, some of the, I used to teach a class, a graduate level class, and we would talk a lot about polymer crystallinity, how it crystallizes, and then how the size and shape and distribution of those crystals impact properties and stuff. We're just going to really think, in here, we're going to think about the amount. How you process the material can change the structure, which changes the properties. You know, like we can do a lot of different things. And the polymer I've talked about the most so far this semester has been polyethylene, probably, right? And that's a classic example of we have the same CH2 chemical structure. We can change the crystallinity and change the properties. How do we change the crystallinity? Well, that's how we processed it. We can change the molecular weight. We can go to different crystal types. So like getting polyethylene to be spectra and have that extended chain crystal, it's going to have dramatically different properties than other crystalline polyethylene, right? So all of this is tied together. So, questions? So, Painter's textbook and ebook don't talk about amorphous and semicrystalline until much later in the textbook. I find it really useful to think about that now from the very beginning. So polymers can be amorphous. You guys heard that word before? So amorphous has no long-range order. Long range at the molecular scale, right? There's no long-range order. The chains are randomly distributed. Okay? These materials tend to be transparent. You can put additives in, but they tend to be transparent. There's no crystallinity. If it's truly amorphous, there's no crystallinity. And then polymers are never 100% crystalline. Even what we call a polymer single crystal has some amorphous parts, like where the chains are folding over and the chain ends stick out of the crystal and stuff like that. So it's never 100% crystalline like sodium chloride or other things might be. So crystalline polymers are really semi-crystalline. They're partially crystalline. They are usually opaque because usually the crystalline domains, the actual polymer crystal versus the amorphous part, their refractive index is different enough and the size of the crystals are the right size that they scatter light, and so then your polymer material appears white. Okay. So a polymer that's white, like let's say this dry erase board, it could have something in it that's making it bright white. It might have an additive, but it might not. If a polymer has a nice bright color like our yellow chairs, it's got an additive, right? It's got a pigment. Okay, so polymers can be amorphous or semi-crystalline. Things that we think of as plastics are almost always semi-crystalline. These chairs are semi-crystalline. Polymers, plastics that have good mechanical properties, they are usually semi-crystalline. Okay. But not 100%. So if we have an amorphous polymer, it can either be glassy or rubbery. That's it. Glassy or rubbery. Does that make sense? Those two domains are separated by what we call the glass transition temperature. The glass transition temperature is not like a melting point or a boiling point. it is not that same kind of thermodynamic transition. Okay? Those are really well understood. Melting, freezing, melting, boiling, sublimation point. All of those are first order thermodynamic transitions that are really well understood. The glass transition temperature does not occur at a well-defined temperature. The rate at which you do the experiment to observe it can change the TG. Okay? So if you ever see somebody reporting the TG like out to tenths place, be suspicious of their research. Okay? There's very rare circumstances where that might be useful. For the most part, you're estimating the TG. If we have a semi-crystalline polymer, the crystals can melt. So now we can have an amorphous polymer, which could be an amorphous melt, which could be an amorphous polymer above its TG, or a semi-crystalline polymer that's above the TG and above the TM. Right? Oh, there's our amorphous polymers. Right? We've got rubbery or glassy. There we go. There's our silly putty. My blue ball of silly putty is sitting on my dining room table. I'm supposed to bring it in today. Cross-linked version would be rubber bands, right? You cross-link it so it has to snap back because you've got covalent bonds. So you can stretch it, but there's a restoring force because of those covalent bonds. Glassy polymers, like your tail lights. And the picture on top is an aquarium where you're like one of those giant aquariums where you're walking through the tunnel. So that plexiglass, glassy. Semi-crystalline polymers, we got to think about three things. So below TG, so TM and TG. So when we're down, it's going to be crystalline and glassy. That's going to make it's going to be more shatter resistant, right? Because the crystals are going to improve the mechanical properties, inhibit the brittleness. Okay. Then if we get into what a lot of times we're talking about the plastic, where it's crystalline and rubbery, and crystalline and glassy. So that's really things we think of as plastics are on either side of that TG line. Fibers, milk jugs, kayaks, garbage cans, these chairs. Okay. And then once you go above the melting temperature, you melt out all the crystals, and it's just an amorphous melt. Okay. Plastics versus polymers. We're going to start with the bottom one. I'm not asking about you guys. I'm asking about the general public. What do you think the general public thinks about the word chemical versus chemistry? The American Chemical Society, the ACS, actually studied this. Do you think chemical or chemistry have different connotations?
Yes.
Does one have a positive?
Yeah.
Yeah. Which one?
Chemistry.
Chemistry. Yes. Right. The general public thinks that chemicals are bad and that chemistry is good. Okay? That's what surveys from the American Chemical Society found this. That's what the general public thinks. I love it when stuff says it's chemical free. It's a big pet peeve. I'm like, is it a vacuum? Because if it's not a vacuum, there's chemical. Might be water, might be natural, might be nitrogen. If it's empty space, it might be air, which is made up of chemicals.
They're putting dangerous dihydrogen monoxide.
Yep, that's right. Yep. So yeah, chemical free. I'm like, yeah, it's not chemical free. What are you talking about? All right, so what about plastic versus polymer?
Plastic's bad.
Yeah, plastics are bad. Polymers,
Are not understood.
yeah. I think most of the general public doesn't necessarily know what a polymer is. Probably doesn't have an opinion. But yeah, plastics are bad. They're killing sea turtles, right? And the big thing is, it's more complicated. It's more complicated. All right, so do plastics have a really bad reputation? Right? So cheap and nasty, inferior, wasteful, bad for the environment. So are they inferior synthetic materials? So we got, sometimes they are, right? I mean, there's some cheap, nasty plastics out there, right? But what are the ladies in the right, what are their swimsuits made out of?
Isn't it like
Wool. They're made out of wool. You want to go swimming in a wool bathing suit? Can you imagine how itchy? I would have hives everywhere that wool. And then they're wearing wool socks. Okay? Do you know how much technology goes into bathing suits? A lot, especially at that level, the Olympic level. They have made rules. They got sick of all the world records being broken. So they have now made rules about how fast your swimsuit can go through the water.
That is standardized.
They did. Yeah.
Which makes sense, because otherwise the countries with much better material science programs would be basically laughing at
Yes.
some third world country doesn't stand a chance, because no matter how good of a swimmer you are,
Well, you still have to be able to swim really fast, but it adds up. It adds up. And then another place where you want to see really cool material science and engineering on display in the Olympics, any of the sliding events, bobsled, luge, skeleton, any of that.
yeah.
Hardcore material science and engineering on display. Yep, so there we go. There's that nice wool bathing suit. Pretty much everything we can see on this side, and that's with the surgeons. Aside from the metal pole that's holding up the infusion bag, it's plastic. Now, there's a reason why we move to single-use surgical gowns and masks and caps. The amount of waste the hospital produces is crazy. It's exorbitant, right? There's huge amounts of waste. Way back when, they used to just wash things. But to wash and sterilize, the amount of energy that's needed,
It's cheaper to not.
it is cheaper. It's also safer.
water.
Yeah.
It's also safer. Do you know that most surgical instruments are single use?
Yeah.
And that came from mad cow disease, prion diseases, because you can't sterilize those away. So most scalpels and surgical small surgical devices.
The electronics, they just.
Yeah, they're not actually touching you.
No.
Yeah. So I don't know about some of the bigger things that are used in orthopedics and stuff that, you see on hospital TV shows and stuff, like a rib spreader and stuff like that. I don't know if those are single use now, but most scalpels, needles for sure, all of that is single use. So it's not just plastics. There's other things as well.
I got a free pair of scissors and a whole bunch and like a free pair of stuff because one of my piercings got infected and I had to go to urgent care so they could take it out. And when she was done, she was like, "Yeah, you can take this whole kit with you because otherwise we're just gonna throw it away."
Yes. Yep. My daughter is full speed. She's had stitches and staples more than once. Yeah, she's always excited. Ooh, can I have that? She's got that figured out.
This is her injury stash.
Go ahead.
I know that you use a lot of like metal tools and like the surgical stuff, so are they like throwing away your metal tools as well?
Yeah, that's
Yeah, scissors, scalpels, all of that, single use. Yep. If it touches, once they open the pack.
What
Yep.
about dentists?
If you've been,
I don't
in the dentist
know.
office, they have like heads they put on like the toothbrushes and whatnot. That's what they stick in your mouth, and they take it off and throw it out when they're done.
Yeah, but they have like the scraper thing, and that's metal.
Yeah, I don't know.
Because they bring them out like packs,
Do they?
or they send them somewhere to be cleaned.
Yeah, so it used to be everybody had an autoclave and would sterilize in their own. Yeah. So hospitals, it's a lot of waste, but it's not an easy answer. It's not. It's just really not an easy answer, because you don't want to risk people's lives either. And but if you think about what did they used to transport IV fluids in? Glass bottles, right? They broke. All kinds of things happen, right? You can store important fluids a lot better and longer, especially like blood, plasma, certain drug formulations, because they're sealed in a plastic bag, right? People tend to, I think we see this a little less, but it used to be traditional materials, people would always be like, oh, it's better back then, right? So there we got the milkman, right? So back then, you left your bottles out, and the milkman picked them up and dropped the fresh milk off, and then the milk bottles were washed and reused. That also used to be true with soda and beer. That you would take your bottles back to the brewery or the bottling plant, and they would wash them and refill them. And as food safety standards increased, that really sort of stopped happening. But also, think about the transport, the loss due to breakage, the weight. Glass is theoretically reusable infinitely, but it's not. It's still. You still have a high energy cost to get it clean enough to reuse it. So it's still not the be all end all. And then I got this forest fire, right? Sort of timely. So people are like, oh, plastics, they're terrible in a fire. Yeah. So's wood. Right? Wood smoke will kill you too. Maybe plastic smoke will kill you a little faster. Maybe. But it's, all of this is, there's not a huge difference between the two. If they're on fire, it's bad and the smoke will kill you. Some people say it's a waste of resources. This is U.S. petroleum consumption by sector. So obviously, transportation is our big one. Industrial, residential, it's like home heating, fuels. Like people in New England use fuel oil. I think that would also be, electrical is separate. So, see that dark green sliver up on the top? Yeah, that's where all of our plastics and drugs and everything else is. So even though plastics and single-use plastics are everywhere, they're a fraction of this pie. Petrochemical free feedstocks, that's 0.317 out of 20 million barrels a day.
What's still gas? Did they run out of the naphtha?
Still gas. I don't remember what that is.
I was like, did they have gas? And they were like, still gas. Here's more.
No, it's a thing. It's a thing. Yeah. So, if it's 0.3 million barrels a day, it's 1.5% of the petroleum that we're using daily. That's going into petrochemical feedstocks. That's not just plastics. That's your pharmaceuticals, that's your dyes, that's, all that stuff, right? It's not a lot. So it's not a lot of, it is a lot, but it's not a lot of what we're using petroleum for. This is the same U.S. petroleum flow. Here's how much we produce. This is how much we import. So these are the inflows. These are other inflows. And then we go out. Crude oil exports. We actually export some. Refined products. Residential, commercial, industrial, transportation. Right? Electric power. Plastics in the environment. So we don't, it's not a big impact on our petroleum use, but the environment, it's a big impact, right? Of what's going into municipal solid waste, it's not necessarily as much as you think, right? Paper is still our biggest. Paper and that includes cardboard. Okay. So plastics, and we should probably, this is rubber, leather, and textiles, so we should probably add this together. So it's getting, 9 plus 13, 22. So it's not insubstantial, but it's not what's overwhelming our landfills. So look at how much from the 60s we were barely throwing any away plastics to now, right? It's amazing. So we have plateaued off. The gray is landfill. This is combustion with energy recovery. So this is burning. And then this is recycled. And there is a little yellow line. If you go to the website, you can see the composted, but it's like not there, essentially. So do we need to change this? Yeah. I am all for reducing single-use items across the board where it makes sense. All right, so we've got, oh, they fixed the clock. Yay, we have 20 minutes. Okay, so I want you to take a few minutes and think about paper or plastic. You're at the store. Do you want paper or plastic? Okay. Then we're going to put a bunch of stuff on the wall.
I just thought it's not plastic bags. I also don't know if it's true that much if it's more like. I don't know if that's true.
If you count the amount of paper that plastic bags.
Oh, dang, I didn't realize it.
Real answer is paper bags. Bring your own. It's a finite resource. Doesn't every family have a bag? I feel like we use those.
That's right.
I have seen a meme or video or something where someone has argued that you're not really an adult unless you have a bag full of bags. Bags.
I have a bag full of bags. I have a bag full of bags. And I achieve adult
Do you like keep your target?
I use them for like my
Yeah.
It's pretty useful actually. I don't think I've thrown away. Since the screen is because I keep one big
like if you
bag.
bring it home to someone.
Right? So it's like not.
You know what else? I have a gallon of water. Gallon jug. I just fill up. Yeah, I just refill it up because then I use it to fill up this one. Yeah, my parents always used to tell me about back in the day. And then if you go back to where you bought it from and you give them the glass bottles, they would and it's had to get
Also, they're recyclable all the time. I think things are recyclable. And if they find something in your pile that's like recyclable, they just don't think like yeah, you don't put it in.
Okay, so let's bring it together. All right. So we're gonna do pros and cons of both. Then decide. Who's got something they want to share? You guys are having a good discussion. It sounds like you're on topic, doesn't it?
Paper uses so much water.
Paper uses a lot of water.
Yeah.
Lots. To produce it. Go ahead. You're next.
Paper breaks down easier than plastic does.
But is it in a pro way or a con way?
In a pro. In
What?
terms of like,
Yeah, but then you have aerobic decomposition too, where it just produces methane gas.
So theoretically it does. It's like out in the woods or something, it's gonna decompose. You put it in a landfill. They do core samples of landfills like they do with ice, and they can read newspaper from the 30s. You know, so it breaks down. It's it's not a problem in the ocean, so we'll give it as a con.
Plastic bags are generally a lot more durable than paper bags are.
Mm-hmm.
Like paper bags, I know will tear very easily, whereas plastic, they're durable and they deal with moisture much better.
Yeah.
Like if you have a jug of milk in one of the bags, paper, you gotta carry that thing from the bottom because it's gonna sweat through and eventually tear if you don't.
Yeah. For sure, right? The wet properties of paper is a lot worse. Go ahead.
I would say plastic bags are more like economically friendly, like they're cheaper to produce.
I'm not sure in California, isn't there a tax now?
Go ahead.
Paper can, like trees can be grown. It's a renewable resource.
Mhm.
Plastic's easier to reuse.
For me, yeah. I dog poop, nasty trash. We just got a cat litter. I reuse plastic a lot. I don't reuse paper very often. But not everybody's gonna reuse it. I think it's a pro for the most part. What else, guys? You're definitely missing some negatives of polymers. Go ahead.
Plastic doesn't decompose easily.
Mm-hmm. Readily. Go ahead.
Plastic, it's like more expensive to recycle. Some places they even have taxes on it because of it.
So they're both recyclable. It's plastic with do the arrows. Okay, so it's recyclable, but it can be hard. Right? It can be hard to recycle because it has to be sorted. We got to give paper, right? It's also recyclable.
Oil's like a much more finite resource, and it also has competition between for transportation and its other uses.
Go ahead.
I'm not sure if it's correct or not. Like some plastic is bad for your health. Like, if you, I'm not sure if that's true or debatable.
Yeah, so it's
Like-
usually I'm going to say with, issues with, it's usually not the actual plastic, it's the additives.
Plastic is a choking hazard. Like if you have little kids.
Mm-hmm. Suffocation too. What else? What about transportation costs?
Wouldn't that be on both of them?
Per pound, paper is going to be, the number of bags per pound is going to be way lower on paper. So it's transportation costs to yeah.
Paper bags usually have like adhesives on the handles or branding or something on them that'll make it harder to recycle than if it was just paper.
Yeah, can be. So the more complicated it is, it can be more expensive to produce as well. Any other thoughts? What do you think the best answer to this question is?
Bring a reusable.
Bring a reusable bag? Isn't that what you guys were talking about? What kind?
Free ones that you get so you can just keep on.
Free ones.
Yeah.
Yeah, so I used to always say to people, get whatever you're going to reuse, right? If you don't bring your reusable bag, get paper or plastic based on what you'll reuse. So I'm against plastic bag bans. I have no problem with single-use bag bans. But to single out plastic bags and not all of them is not doing the environment any good. So when Wegmans went to just paper bags.
I think you need to pay for the paper bags.
If you have to pay, then that's
Yeah.
better. But I think I haven't been there lately. I went during the transition, and you didn't have to pay for the paper bags. So it's, yeah, if you have to. The state of Maine bans single-use bags. So they can sell you bags,
Yeah, I've seen some.
but they are not supposed to be single-use.
I love that.
Yeah, it's like for Aldi. A lot of Aldi's like.
Yeah.
They'll
yeah.
scan your stuff, and then they just toss it in a second cart, and it's like, okay, have fun.
Yeah.
You need to bring your own bags.
Yeah,
or-
Costco does the same thing. Aldi does that. Lidl.
Actually,
When did
Aldi's
plastic bags enter like the grocery stores?
You know, I don't know that.
It's like they're supposed paper originally.
They were paper.
You know, one thing Aldi does also. I'm curious as to how much it helps the environment. Is there? You need to pay a quarter to use a cart. You'll get it back.
Oh yeah, I don't think that probably doesn't help the environment very much. I think it. Yeah. You get your cart. They get the cart back. It saves them money because they don't have to go out in the parking lot and collect the carts. Right.
It was like you'll see sometimes carts 3 blocks away from the grocery store.
So. Do we? Oh, 5 minutes. Okay, so I don't think we really have enough time for me to pull up this video, but there is a TED Ed. So TED Talk does educational talks too. There's a TED Ed video. It's about paper or plastic. And part of that is they also talk about reusable bags. Cotton bags, not very good. So the amount of water and energy to produce a cotton bag is really high. And so their conclusion was like polyester reusable bags are the best way to go. Cotton bags to come out ahead, thinking about complete life cycle analysis, you had to use them like 1,000 times. It was a lot. And then a polyester bag was down in the hundreds. Go ahead.
Question. So that's like cotton bag, not even single-use cotton bags, just.
Yeah. Yep. So like all those cotton tote bags that you like when you go to conferences and stuff, and they give you those bags that you're like, I'm like, I'm never going to use this again. And it's like, give me a reusable grocery bag, you know, like give me something, you know, it's like, so that, yeah, definitely an issue when you start thinking about the whole picture. Another thing that I found really interesting was a article I had read about like so like the whole state of Maine said no more single-use bags. And so unless you're on the border with New Hampshire, everybody's got to deal with this, right? There have been different cities that have gone to say no single-use bags or new plastic bags or whatever. They put in these bag bans. And what the studies of those cities have shown is that the grocery stores just outside get more traffic. And inside the grocery stores and stuff inside the city limits end up selling way more trash bags.
Oh my God.
So they're not really, it's not doing what people want it to do.
Like the statistics do never lie, but you have to actually know to interpret them. It's like, yeah, sales of usage is going down. At the same time, overall attendance of those stores is also going down at about the same rate.
But this was showing that people need garbage bags, right? And if they're not reusing their grocery bags, they have to buy them, and they're thicker and more plastic. That was the point of this particular paper. But yeah.
In my house, like we've never bought a garbage bag for anything smaller than like the big kitchen ones.
Yeah.
Because we just use the plastic. And
Yeah.
we've never bought like Cooper bags either for the dog. We actually
Right.
We actually were using our reusable bags so much we had to be like, okay, once every like 6 weeks we gotta forget them. We're running out of plastic. We're running out of plastic. We gotta.
So when I'm really good and I'm running out of plastic bags, I will just grab them out of the recycle bin at the grocery store. Because reusing them is better than recycling them. So, anyway, I feel a little like sheepish when I do it, but I'm like, I need a bag full of bags. I'll just take this one, So, okay, so remember on Thursday, you need to have your slides in the shared folder, okay? Second choice, bring a hard copy, because I can put it on the document camera. First choice, slides in the shared folder. Second choice, hard copy. All right. No, the slideshow button should be the one that's highlighted. It drives me nuts. Okay, floor is yours.
So we did the degradation rates of the commonly used polymers. As you can see, that we found the 6 most commonly used polymers, and we have like what they're most common use for and their thickness. So, and we found out a lot of them do not degrade at all, or it's a very slow rate. That is, so I think it was like takes, what was it? There's a per year, so like it takes 500 years to 1,000 years for some of them to degrade at all, and some of them like PVC can't degrade at all. For the most part.
You guys know where PVC is used the most?
Pipes from the ground.
So we don't want it to degrade, right?
Yeah.
We want it to last and last and last. So usually we're talking about we got to get rid of this stuff. We got to break it down and degrade it. But sometimes we want things that are stable, long term, buried underground.
We thought it was interesting kind of looking at the difference between like something in like a landfill versus like when heat is applied versus in the water, and when water and heat is applied, and how that helps them break down.
Yeah, so landfills, and this is why paper doesn't degrade very well in landfills. Once it's buried, it's anaerobic. There's no oxygen, and so things don't decay the same way.
It becomes methane gas. Or if it does degrade at all.
Yeah. Yeah, but like you can pull papers out that are 70, 80, 100 years old from core samples of garbage dumps. One thing that's also really interesting is if you think about compostable polymers, if you put most compostable polymers, like silver, plasticware and stuff like that, in your home compost, they're not composting anytime soon. And this goes to the temperature effect you guys mentioned, right? So industrial composts operate at a much higher temperature, and they manage the microorganisms that are composting the materials. And so if they need to change something, they can dial that in, and they turn it over more often and that kind of thing. So you can compost a lot of things in an industrial composting facility that you cannot compost in a home facility. So, and it's not all plastics. It's also like bones and stuff like that. And then thickness, that should be sort of self-evident, right? It's thicker. So the thickness column is super important. In the spring, a class that guys might be interested in, I teach a polymeric biomaterials. It's TE 466, 566. And if you've had this class, you're good to go. The prereqs are out of whack, and it hasn't gotten changed. So anyway, thickness. We talk about thickness a lot for implants and things that might degrade because the inside of your body is a very hostile environment. It's like this column. And then you can think that there's some implants you want to degrade, like resorbable sutures, and there's some things that you don't want to degrade, like pacemaker lead, right? The coating that's insulating the wires. That's a bad one. Okay? So stuff like that. Anyway, we talk about that. Why is it telling me I'm signed into the drive? Why is it telling me I don't get it? Okay. Do you have? Oh, there we go. You got one more. They're looking at one another. Who's gonna talk?
These polymers take extremely long to degrade, and these statistics are in micrometers, which is a millionth of a millimeter. So even of those,
it's a millionth of a meter, 10 to the minus 6. So it's a thousandth of a millimeter.
That is 10 to the minus 9.
No, that would be a nanometer.
That would be a nanometer. Okay, well that's wrong. It's a millionth of a meter. Yeah, and the polymers do degrade faster in sunlight or UV exposure, but it's still so small that there's barely a difference. And like additives can be added to polymers to increase these rates, but the world must take steps to reduce these polymers because they'll practically be here forever. And inclusion, use reusable bags.
Cool. So, yeah, it's complicated. Reuse, reduce, reuse, recycle. Those first two don't get enough attention. Reduce, reuse, right, before you get to recycle. Yeah, very cool. Sunlight and UV exposure. Polymers need sunscreen just like we do. You guys have seen like kids' toys that sit out in the sun, how they fade and they become a lot more brittle over time. You ever seen like a kid slide or one of those plastic cars or something that just like fractures, has a catastrophic failure? It's usually all faded and everything like that. Well, that's because the sun is reducing the molecular weight. breaking the chains. And as that happens, and then the sun is hot, it can get more crystalline. Anyway, all of these things are leading to it, the plastic becoming more and more brittle. And so plastics that are made to be outside and made to be in the sun have a lot of UV stabilizers. That's one of the really important additives. They have to have sunscreen. So if you buy a cheap plastic chair, like for your porch, it's gonna eventually break, even though in the beginning it's sort of flexible and tough and that kind of thing. Over time, it's gonna change. But if you buy, a polywood, it's much more expensive and that kind of thing. It's also a lot thicker, but it's gonna have higher and more and probably better, i.e. more expensive UV stabilizers in it. Okay. Who's next? Okay, which one?
We're the polymer question, like the second
This one?
Yeah, that one.
And actually, wait a minute. So tell me, what are your names? Andrew.
Caden.
And Eli. And then before you guys start, tell me your names.
I'm Deanna.
I'm Michelle.
Okay. And it's the two. Oh. Cullen?
Yeah.
Oh, got it. All right. Oh, trying to hit the share button again.
Okay, so our question was how do temporary tattoos work essentially or attached to your skin? And so this is like an infographic of breaking down exactly what a temporary tattoo is composed of. So we have, it's technically 4 different main things, which is backing paper, silicone release coating, a transfer film, and a temporary tattoo. Which I believe everyone has used temporary tattoos, so they're really cool.
Sorry, you just caught me off guard. But yeah, you basically just stick it on your skin, and you know how you have to put water on it so it'll slide off. That's for the transfer film, so the ink will stick to your skin. So just putting it on there, and then nothing's happening. And
The tattoos that come off within a few days, or you just rub it with something. This is because the tattoo is only applied to the first layer of whatever substance you put it on. Unlike a more permanent tattoo where they inject the dyes into you. Here it's just, it's like putting on a sticker on a piece of paper and then turning the page. It's no longer there.
And most of the time when you rub that temporary tattoo, you're rubbing off that layer of dead skin cells. And that's what the tattoo's stuck to. A real tattoo is going many, many layers deeper into the skin. But yeah, look at this, okay? The paper's made from cellulose, and it probably has some kind of coating on it too. So that's probably a polymer. Cellulose is a polymer. The ink is probably not a polymer, but the adhesive is most likely a polymer. The release coating, that's a silicone or a siloxane synonym. So that's a polymer. And then the film is another polymer. So even though what's on your skin doesn't have much polymer in it, the whole thing is more or less a polymer device, huh? So. Somebody else want to volunteer? Okay.
That's the one you're on right now.
Oh, this one?
No.
This the cellulose.
Cellulose.
Gotcha. Okay, so introduce yourself.
My name is Tess Mulligan.
I'm Gray, Hensley Alford.
Bryson Proctor.
Cool.
We were wondering if cellulose could be used in its base form to create polymers. What we discovered was that cellulose is really difficult to retain in its raw form. But we do it. We use processes to make something like rayon, but that has a lot of chemicals and it takes a lot of water to make that.
We've learned how to get bacteria that will ferment cellulose, but we can't organize it like the polymer. We can't spin it the way that spiders do and make it as useful as they do. So we're still still needs a lot of work to become like as efficient as turning something with like turning like a fiber that has cellulose into it, utilizing that in like cotton or like wool or like other uses.
And then, like I said, it's not very much research has been done on it. So when that starts to happen, it can kind of open the floodgates for raw cellulose to be used, and then it could lead to more of some sustainable textile products.
So my grad student makes bacterial cellulose, or he makes the bacteria happy that make the bacterial cellulose. He keeps them alive. So a huge benefit to bacterial cellulose is in plant-based cellulose, so wood and cotton and other plants. You have a lot of lignin, which is really hard to remove from cellulose. So if you want to start with a pure form of cellulose, the bacterial cellulose is a better way to go because you don't have any lignin. The big issue with cellulose and processing cellulose is that it's not soluble in any normal solvents. Okay? So in order to make it soluble, we can go through a process like rayon, but it's complicated. You chemically modify it, you get it into solution, then you modify it back to cellulose. So it's like, because once you get it into solution, you can process it, you can wet spin it. But no matter what form of cellulose you have, it's nearly impossible to get it into solution. There's like some exotic solvents that are like liquid salts and stuff that can dissolve cellulose, but it's not something that you can do on an industrial scale. So, any other thoughts or questions?
We have our sources.
Oh, yeah. Go ahead. Which one? Oh, yeah. So I think that you can't make things white without getting rid of the lignin, but I'm not totally sure. I know it's really important in processing wood pulp for paper.
But more of like an aesthetic issue.
And it also makes things more complicated. So I think cotton, I'm not 100%. I'll just stop there. I don't know. I was going to say, I think cotton doesn't have the same amount of lignin that like wood does. And I'm like 90% that's true. But depending on what you want to use it for and why you need the purity and that kind of thing, it can be aesthetics. It could be an immune response. It could be, there's all kinds of different reasons. And cellulose is a very ancient molecule. Almost no one is allergic to ancient molecules, right? Because they've been part of our surroundings for so long that you usually have no immune response to these really ancient molecules.
What does ancient mean? Like is there like a time frame?
So like a lot of proteins were developed like when we were mammals, or whatever. But cellulose has been around longer than that. It's evolutionarily ancient. So.
I didn't know if there was like a block of time where you were like, is this many years old?
No, I'm sure it varies by whoever's considering what, kind of deal. But like keratin, so keratin's is our hair, our nails, rhinoceros horn, horns and antlers and a lot of that stuff is keratin. That's why the whole rhinoceros horn thing is so ridiculous. But it's another molecule that's super hard to process because it has covalent bonds. It has crosslinks. It has covalent crosslinks. But it doesn't elicit an immune response. So it could be a really great biomaterial, but processing it is super hard. And it's a renewable resource. We have essentially an unlimited supply from the shrimp and crab industry. There's a lot of it. Oh, wait a minute. That's chitin and chitosan. But the keratin, you get it from poultry feathers. So, wrong example, right statement. So it is, there's abundant keratin and also this other ancient molecule, chitin, but they're keratin, chitin, cellulose, all super hard to process. Different reasons, but super hard to process.
I remember I think last year I went to like a what is it called, a convention or something.
Mm-hmm.
And one of the researchers there were presenting their research on like making them from chicken feathers,
Mm-hmm.
making a polymer from the chicken feathers. And
Yep.
they were actually making like a lot of progress,
Mm-hmm.
but it wasn't like the amount of like machine processing they had to go through was like really intense. Like
Yeah.
it was far better compared to like previous years, but it was just like they're making more progress. And it was very interesting to sit in that panel and just sit through that panel and just watch them talk about it.
Yeah. Yeah, it's something because essentially your source material is nearly free. People have done a lot of research onto it, but it's never been economically viable on a major scale. So one day. That, and as we also energy costs, like if we're using renewable energy and solar and wind and that kind of thing, energy costs eventually are going to come down as we get that kind of stuff figured out. And then the trade-offs, the costs of different things will change. That economic balance will change. Somebody else want to go? Go ahead. Which one?
We have the twice one there, but it's the PDF one.
Oh, yeah.
Yeah, so we were looking into the first synthetically made polymer and its impact. So it was bakelite. It was made by a scientist called Leo Hendrik Bakelin, named after himself.
Yes.
It had a very quick molding process, and it had great heat resistant properties. So it was used in a lot of different industries, and it was marketed as material with 1,000 different uses or something.
Right.
Yeah.
Material of 1,000 uses. Oh, you got some good slides.
And some products that at the time that used it were like telephones, jewelry, and kitchenware. A lot of them are like collectibles now, and like I found like on eBay, like they had like dominoes, and they were like kind of like orangish and stuff, which is kind of cool. There's also some polymers that were inspired by bakelite. There was like I think it's Catalan. I think it was they created like the day that bakelite's patent expired, so it's probably kind of similar.
I think it's almost the same.
Almost the same.
Mm-hmm.
And also PVC and nylon. They used PVC for like records at the time.
Yep, that's why you call them vinyl. You guys know that? It's vinyl. And like old time cars was the vinyl dash. That was PVC. And then eventually it would like crack in the sun. Yeah, my mom has a lot of that big like kitchenware stuff. She's into antiques and collectibles, so there's a lot of that. Is that your, yeah, cool. Yeah, you essentially have very similar slides to what I'll show you when we do a history of polymer science lecture. So yeah, it wasn't just Leo that had a big ego. It's also Parks. He named his polymer Parkinson. There's a lot of them. Big egos. One of the cool things about bakelite is they were making bakelite before they believed polymers existed. So, pretty neat. Okay, who else? Yeah.
On the top left there.
This one?
Yeah. Alright, so our question was, what kind of polymers can be safely implanted in or on the human body, aka just like what are some medical grade polymers? So one of them we found was polyethylene. Some of its advantages being it was cost effective, impact and corrosion resistant, it has good structural integrity, it's biocompatible, all the things you want with a medical grade polymer. And a lot of times it's used in prosthetics. As you can see on the top right photo, it's used in femur implants.
See, the cup is right there.
Another one is polycarbonate, it's high strength, heat resistant, has biocompatibility. It's commonly used in blood filters and then just surgical instruments. Another being polyvinyl chloride. It's dense, flexible, and inexpensive. You can see the rib implant on the right there. Pretty cool. And then polyamide, known for its strength, high abrasion resistance, chemical resistance, all that good stuff. And it can be found in artificial hearts and feeding tubes. But honestly, that's just a few of the many.
Yeah.
There's like, I didn't expect there to be like so many compatible polymers. On the list we found, there were like upwards of like 10, 11 sometimes. So those were just a few that we thought were cool.
Yeah, and these are commodity plastics, right? So when people are talking about how bad PVC, oh, it's like Greenpeace used to be on a PVC, like PVC is horrible, it's like so bad for the environment. And you can make a solid argument that PVC has done more for global health than anything else in the world. Because what improves global health more than anything? It's the biggest bang for your buck. Yes. Sewage and clean water. How do we do that cost effectively? We use PVC pipes. So taking care of human waste and providing clean water does more than anything else can for global health outcomes. So, but Greenpeace thinks that it was like PVC is horrendous. It's like the monomer will kill you. The polymer, you can implant it in your body and it's fine. Now, the monomer is toxic, but lots of monomers are.
Why is it toxic? It's singular form, but then if you just put a ton together, it's not toxic.
So think a monomer is CH2, double bond, CH with a chlorine. Everything there is reactive, right? Chlorine, depending on how chlorine is bonded, it can be pretty reactive. The double bond is reactive. So it's those small vinyl monomers, that double bond is reactive. And if it's going to react with your mucous membranes and that's like your eyes, your nose, your lungs, it can cause chemical burns on the skin, depending on which monomer it is and that kind of thing. So yeah, they're gases. But yeah, the polymer is very safe. Teflon, PET, polyethylene tetrafluoroethylene. I was blending that with PET, polyethylene terephthalate. I'm not talking right today. So PTFE, Teflon, could easily have been on this list. It's used a lot in catheters, blood contacting catheters, and some vascular grafts and that kind of thing. So like your blood can be in contact with Teflon, no problem. Implanted inside of you, no problem. And that's why when people are lumping Teflon, the polymer, in with all the other PFAS chemicals, it's an issue because it's not like the small molecules. They're all very, very stable, right? They're all these, what they say, forever chemicals. But the polymer is not going to hurt anybody, right? It's that kind of thing. Yeah.
Have we seen, are there any problems with the polymer, like, because of bioaccumulation, just like clogging animals?
That would be more of a microplastics thing, and then it's not that the plastic is reacting or causing it, that kind of, it's you have little tiny animals and it accumulates and then it moves up the food chain. But it's a very different, it's not like, we know that some PFAS chemicals, well, I shouldn't say no. We suspect that some of the PFAS chemicals cause cancer, where the polymer form it's not. There's no evidence that it is. Yeah. Polyamide. We can also say nylon for a lot of them, and those are also removable sutures. It's another where they're used. So, very cool. If you like this, take TE466 someday. Oops. Okay, which one?
We're the one on the floor top right. So we answered 3 questions on accident.
That's okay. We can do 3 questions.
It's okay. We already answered one of them. So, yeah.
2 groups did temporary tattoos. Nice.
The temporary tattoo is a paper tattoo with a transfer film, which has stronger layer absorption and can absorb a variety of substances. So over time, the layer of skin is also shaped by the body.
And I did what defines something as a polymer, and then are there exceptions? Which we've talked about a lot, but basically a polymer is just a large molecule made up of a bunch of monomers in like a chain-like structure. And some of their characteristics are chemically bonded together by covalent bonds, and that's what like kind of forms the chain. And then repeating units, which are polymers. Covalent bonds, high molecular weight, those are all characteristics that typically are of polymers, but then there are some exceptions to like those characteristics, and like natural polymers sometimes have different characteristics than synthetic. And then there are low molecular weight polymers, and like that differs because most of them have like a very high molecular weight. And there's other exceptions. There's a whole list that I've seen.
Yeah. So you remember on Tuesday we talked about the 3 things that make polymers different? So some people use entanglements to sort of define whether it's a polymer or not, which works as long as the backbone is flexible. If the backbone is rigid, it doesn't work, right? But so if a molecule is starting to entangle, some people would use that to define a polymer, and so that could be some of the lower molecular weight. And then I can't remember if we talked in this group with this group or not about polymer and macromolecule, because you can have some people focus on the chain-like aspect of polymers, and then things that aren't chain-like they call macromolecules instead of polymers. But most polymer scientists just use those words interchangeably. If you make a material under a controlled synthesis where it's trifunctional, and you can keep adding and going, right? This is going to be in 3 dimensions. It's going to be what we call a dendrimer. It's like a little molecular ball. And so this is 100%, if you go out enough, a macromolecule. But it doesn't entangle. So some people are like, oh, it's not really a polymer. It doesn't behave like other polymers. But it's made from many units. It's just not shaped like a chain. So yeah, not everybody agrees. And then if you're talking to biochemists, what they call a monomer is like a whole protein. And then like 3 or 4 proteins or peptides, I guess the units form the whole thing. So then that's their protein or their enzyme. So yeah, even monomer. Doesn't mean the same thing to every discipline. Ooh, and we got Teflon too. Oh, yeah. Okay. That's even the brand of pan I like. I think. I've definitely had that pan in the past. Okay. Yeah, go ahead.
When it comes to the Teflon pans, I know there's a bunch of different things that are advertised as non-stick. I think it's like the ceramic coating. What is that? Is that still Teflon? Or I guess it's not because it's ceramic, but like how does that work as non-stick?
So, non-stick is hardcore surface chemistry, which is hard. It's like really hard. Like the math and the thermodynamics and the energy and all of that stuff is hard. So Teflon works because of the chemistry. I believe the ceramics work because of the actual topography. So like how it is, like what the surface shape actually is. And so processing it into such a way that it's nonstick is more challenging. So that's like a newer thing. So like a lotus leaf, water runs off a lotus leaf and it's not hydrophobic. It's got these little tiny hairs on it, or like little tiny things that are changing the surface energy. I'll be brave. We'll try to never Google in front of the classroom. Discourages surface wetting. To see like this kind of surface, these little bumpy surfaces, make it so things don't wet. So wetting is when the drop spreads out. And if the drop doesn't spread out, it stays like in a real sphere, it's going to roll off. So I think that, well, let's try. Yeah, we're not getting anything. Nope. It's not going to tell me. But I think it's because they've got the right kind of surface roughness to keep things from wetting and sticking the same way. But I'm not a ceramic scientist in any way, so don't hold me to that. So like this, I love stuff like this, right? Where you make it bumpy and nothing sticks. And then like gecko feet. You guys seen pictures of gecko feet? Yeah, it's like super sticky because they got these little hairs that van der Waals forced them to the wall and glass and they could climb upside down and everything. It's really neat. So, yeah, surface chemistry, I love to think about it at the like picture level, but like to actually have to do any of those calculations and stuff, oh man, this is way too hard for me. It's my brain does not like that stuff. Pretty neat. Okay. Who's next? Are you all together? No. Oh, and then you two. Okay. So let's do the four of you. The Teflon pans. Oh, perfect. Okay.
So we kind of split this question up into two parts. First being why it doesn't stick to food, and then the other part being why it's able to still stick to the pan. Because that was the part that we were kind of curious about. So we found that Teflon just basically really likes itself, kind of like water does, and so it's going to stick to itself really well, but it's going to repel a lot of other substances because of the structure, kind of like what we were just talking about, just less about the surface and more about the molecular of it all.
Yeah, it has really low surface energies. Or was I supposed to go to the next one? Yeah.
So we found like two ways they can make the Teflon stick to the pan. Like one is, I think the other group they have the same thing, like sintering.
Sintering.
Yeah. So they put it like high temperature, and then so basically they want it to be sticky. They need to break the fluorine apart from that polymer.
Yeah, so they're trying to rip off the fluorine atoms.
Yeah, and one way is use the high temperature, and then
Yeah, so the other one is like a reducing agent. So the main gist to the question, which I thought was an excellent question because I never thought about it, which is like, why does the Teflon not stick to the food, but they get it to stick to the pan? And so like on the other slide, we had the strong CF bonds, and then the natural repelling nature of the fluorine itself. And so with both of those methods, the main gist of it is just to break the CF bonds, and then the carbon will go and bond to maybe the oxygen, that's present on the pan, one layer, and then the other layer is nothing's done to it. So,
Another part of it is also mechanical, right? If the metal has the right sort of roughness and the Teflon is into all the little nooks and crannies, it makes it like it's sort of mechanically locked in too, and then you pop off some of these fluorines and it's going to stay pretty well.
In some processes, the surface of the pan is sanded first.
Yeah, to get the right sort of surface roughness of the pan. Yeah, exactly. But you want it to be, when you want it to be nonstick, you want it to be smooth. So, yeah, so you want to throw away Teflon pans if you see them start to flake. Because it's probably still fine, right? It's not going to be nonstick if you've got scratches and flaking Teflon. And it's probably still fine to use and you're eating little pieces of the Teflon. But because you use pans at higher temperature, there can be breakdown products. So it is better to just get rid of it. And then, better safe than sorry. But it's not a very big risk. And there's really no risk of an intact Teflon pan. Some people are like, no fluorine, no chlorine. It's like you're not understanding the chemistry very well. It's not a problem.
Probably the same people that love Splenda because they love their artificial zero calorie
yeah, so we moved to Maine, and my parents had always lived in states where they fluorinated the water, right? Which is a good health benefit. I think it probably is, but in Maine, yeah, no, they decided it was a communist plot. Mom. So, yeah. So anyway, that was a long time. It was like the 70s. So, but yeah, I think Maine still doesn't fluorinate water. I know that Raleigh water is fluorinated because my daughter's dentist, that was the first thing. Are you on well water or city water? Okay. Anything else? We good? Who's left? Oh, you guys. Are you the...
We're the top.
Yes, the PowerPoint. I'm going to download it. Ooh, more biocompatibility. Go ahead.
So our question is, what are biocompatible polymers used for, and what is an example of them? Our definition for biocompatible polymers is they can be synthetic or natural polymers that interact with living tissue and organs without causing damage.
Some of our uses that we found were medical and dental applications. They can be used in surgery as implants, drug delivery systems, tissue engineering scaffold, and biological grafting. And then we also have a list of some of the ones that can be used.
So we got a lot of overlap with the other list, but you've added silicone, Teflon, polymethyl methacrylate. Okay, I got a story about PMMA. So in the early days of biomaterials, doctors and surgeons, we didn't have an understanding. As scientists, nobody had an understanding of what was like compatible and not compatible, like implanting into the body. So they just tried things, and they thought they knew things. Like it was assumed that you could put nothing inside of an eye. That would be whatever you put in there would be rejected. So, World War II, polymethyl methacrylate is what made fighter planes possible, because you didn't need a big heavy glass canopy. You could make it out of PMMA, plexiglass. Well, what happened to those pilots? Some of them got shot out of the sky. Some of them had pieces of plexiglass shrapnel that were embedded in their eyes. And it was fine. If they didn't get an infection initially, they could see, it was totally fine. Their eye healed and the little piece of shard of plexiglass was inside. No problem. Yeah.
In their eyeball?
Yeah.
Like in it.
Yeah. Yeah. So this ophthalmologist had treated some of these pilots, and they believed that you couldn't put anything in an eye. And he's like, well, it looks like plexiglass is okay. And he made the first artificial lenses. And that's how we treat cataracts, right? They take out the clouded lens and put in a plastic lens. I thought that they were mostly like lasering off cataracts until I had a dog with cataract. And they're like, oh no, we just take it out and put a new lens in. She was a rescue dog, and the rescue group paid for the cataract surgery, and the doggy eye doctor gave the rescue group a big discount. But Valentine, I had her for years. You saw her picture. She was the black cocker. She had been blind a long time. So my mom had cataract surgery not long before the dog did. And she said, oh, it's gonna be magical. She's like, you open your eyes and you can see. It's amazing. She's like, it's just like, wow. She found this surgery so just, but she wasn't blind, and 2, she understood what was going on, right? So the dog only had one eye. One eye couldn't be saved, and so they just removed it. And then because people like their pets to look nice, they put a rubber ball on the inside, so it's not like a caved in socket. It just looked like her eye was just sewn shut. And I was teaching TE 466 this semester when this was happening, and I'm like, ooh, what's that ball made of? I'm going to talk about it in class, so she gave me some. But the cataract, so the dog, her reflexes came back immediately. The dog could see. The vet knew the dog could see. The dog did not know she could see. So the information was going to her brain, and her brain was just like, that's garbage information. I can't see, I'm blind. And so there was never this, she comes to and can see and like is a happy girl, No, it was gradual, and it took weeks. And then she was like, she's like walking around and no longer bumping into things. And it's like, oh, you've got it figured out. But it was really interesting. And the vet was just like, her reflexes are there. She can see. And I'm like, well, but I think that was because she had been blind for so long anyway, the brain does weird things, right? Because the information that's going into our brain is upside down, but our brain flips it over. Right? And that's like you don't see your own nose till you have like a scratch on it or something, right? It's in your field of view, but your brain's like, oh, I don't want to see that, and so you don't see it. Yeah, if you sort of watch it go in, you can start to see. But you get a little pimple or something like that, and you can see it. It drives you crazy. You know what I'm talking? You know what I'm talking about? Yeah. It's because your brain is super cool. Has everybody gone? Oh, you haven't. Which one? This one. Katie.
So our question was, how are polymers able to stop bleeding and aid in the
So we found that interactive synthetic polymer dressings are occlusive or semi-occlusive, which can provide a barrier against bacterial penetration to the wound. And then polymer films trap bleeding, and that provides a moist environment for wounds. And then one of the examples we found was Fetagel, which is made from plant polymers, and it works with the body's natural healing mechanism to clot blood on target.
And then some properties of the polymer wound dressings include high porosity, which is kind of necessary for like band-aids and stuff, and then swelling ability and flexibility. And then we also found that natural polymers and synthetic polymers are used for aiding wounds, and they're used like bandages, gauze, and all those things, and it's able to protect the wound from contamination and infection.
Some of the stuff that actively that stops bleeding, that triggers the coagulation cascade, there's a lot of cool chemistry and cool science that's gone into that. Dr. Hudson, who just retired from the college not that long ago, he and I had a student that worked on this, and she was using different types of chemistry to try and make polymers that would clot blood faster. So it's really important in medicine to have materials that'll cause things to clot and that will not cause things to clot, right? You want to store blood in a bag, it better not clot, right? You want to use something needs to be blood contacting, like a catheter or a heart valve or something like that. It better not clot your blood. But especially in emergency situations, the ability to stop bleeding is life-saving. Absolutely life-saving. And that's why the first thing you learn in first aid, right? Put pressure on the wound. You have to stop the bleeding before anything else matters.
Is there a reason that like most first aid kits don't have Fetagel or like quick clot?
I don't know if Fetagel is FDA approved. Quick clot is only approved for certain things, and it wasn't cheap. So,
my cousin had to do like military training for something. He wasn't I think he was like one of the reserves or something. So he had to like do all of their first aid training, and like apparently they have something that I don't think it's like
yes.
consumer that
yes.
like you
There,
just, like,
yes.
and it clots.
Mm-hmm. Surgeons hate it. Okay, it gets the patient to the surgical table, which is hugely important. But the stuff I know about that the military was using was almost like vermiculite, like it was like so then the surgeons have to get it out, and it like there's little pieces and particles, and they've got to get it out because you don't want it to. They can't close the wound until it's all gone, and it can attach, and so then it can be hard to. When you're taking it out, the bleeding can start, and anyway, there's issues. So, but yeah, stuff that is for severe traumatic injuries, usually it will get approved for military use because maybe it'll save somebody. And soldiers, I don't believe, have the ability to sue the way consumers do. So, yeah. There was something else I was going to say, and it's gone. Is that everybody now? Yeah. Dr. Hudson was a really good storyteller. And when he was working on quick clotting materials, he had some guys come and talk to him. And they said that they were like, worked for some pharmaceutical company or something, and they wanted his expertise. And he's looking at him, and he goes, he's like an old-timey guy, right? You guys aren't from wherever, like XYZ company. And they just sort of smiled, and they're like, uh-huh. We're not going to confirm or deny that kind of thing. He said that it was like talking to two Navy SEALs, or, they had that sort of build and persona, and they were some kind of, according to Sam, some kind of military medic elite, embedded with SEALs or Rangers or something. He always had a story about something like that. But there's also some clotting materials that are approved for veterinary use, but not human use. Oh, I was going to tell the super glue story. Super glue, crazy glue, whatever you want to call it, was originally intended for medical applications. Some were for dental cements and for military, right? Where you got to do something immediately, you can't get somewhere. And I can't remember. And then others for like gluing a wound closed. And there's reasons why it's not the greatest idea, and there's, but a lot of, I used to whitewater kayak a lot more than I do now. But my daughter's getting into it too, so I'm nowhere near as good a paddler or in as good a shape as I used to be. But I have and still have a lot of friends that are pretty serious paddlers, and then when you're paddling out, in more remote areas and you're camping and that kind of thing, it can be really dangerous to have a big open cut on the river. And I actually know a woman who got cut on the river and got flesh-eating bacteria and had to have major surgeries and a couple skin grafts to deal with it. So, you know, this was a pretty good solution. So this guy, he got a pretty good gash on his shin, and he's like, well, if I was at home, I'd go to urgent care, but, you know, I'm out in the woods, we're on the side of the river, what am I going to do? And so they super glued it shut and then put bandages over it and then duct taped the whole thing. And that's how he paddled the rest of the day. And then I think the rest of the group paddled the second day, and he was smart and didn't go back in the water, and then got to, urgent care a couple, it was like the third day or something. It was 2 days or 3 days after it happened, and it was already healing, and it was like healing underneath the super glue, and eventually it just popped out the super glue, right? And the doctor that saw him in the urgent care was like, yeah, we don't recommend this, but this was really a good idea. He's like, we're not allowed to say that, he's like, but based on where you're telling me you were and how you decided to treat this, it's going to be fine. He's like, don't pull it out, because that was, it was only 3 days later. It wasn't, he's like, don't pull it out. It will eventually just come out on its own. It'll pop off. So.
I can't recommend this personally. I agree.
Yeah. And he was like, and we're not gonna touch it. He's like, just leave it alone. Keep it covered if you need to, and so. Yeah, there's lots of things, to do that you can do that aren't necessarily recommended. But if you're out in the middle of nowhere, or you're in combat or that kind of thing, you do what you have to do. Mm. But
I thought that was interesting that they use glue rather than stitches.
Yeah, cuts like that, they always hurt. So they weren't using straight up off the shelf super glue, but it was damn close. Yeah. So one of them.
Why did they have it? Were they just in case?
Yeah, it was in their med kit.
Okay.
Yep. Just it's a common wilderness thing that nobody who's teaching you wilderness first aid can officially tell you, but everybody does it. And there's a lot of uses, right? Something breaks or something like that. 15 minutes. All right. Well, fun. I enjoy this day, and I think you guys, for the most part, do as well. It's sort of neat to hear what other people are interested in class. I think. Hopefully, you agree with me. Why did the other thing not download? Okay, so we are finished with Module 1. So we are into Module 2. Okay. We are going to, in Module 2, we are going to talk about microstructure, chain microstructure. And again, all these slides are in Moodle already, okay? And if they're a slightly different version, it's fine. They're not substantially different. So we're almost towards the end of class. We won't do very much today. But so we're going to talk about the difference between linear chains and branch chains. I already drew you a dendrimer today. We're going to talk about cross-linking. And there's two ways we can have a cross-linked material. We take existing polymers and cross-link them, or we can polymerize trifunctional monomers or anything higher than that, and make a cross-linked network. So Bakelite, that these guys told us about, is a cross-linked. That's a trifunctional monomer. We're going to talk a lot about isomerism. We're going to learn about 3 types of isomerism. In Moodle, there are 3 course presentations, course H5P course presentations. That's the H5P type that are all about isomerism. And then we'll just a few minutes talk about copolymers and blends. Anybody remember which one is 2 or more polymers mixed together? A blend. And a copolymer is made from 2 or more monomers. Okay, so this is what we're going to cover in Module 2. And we're going to talk about, start talking a little bit about crystallinity and how crystallinity impacts properties. And we'll talk about that at the beginning of the semester. Then we won't talk about it so much in the middle. And then at the end, we're going to come back and really talk about this. So this Module 2 stuff will be important, sort of throughout the whole class, but we won't talk about it nearly as much when we're talking about synthesis and kinetics. So, okay, so when people are talking about amorphous polymers, they almost always say, oh, it's like cooked spaghetti. It's all tangled up. And then they're like, oh, well, crystalline is sort of like uncooked spaghetti. But you need to, attach all the noodles. So, a crystalline polymer folds back and forth and back and forth and back and forth. So it's a little bit different. I actually don't like thinking about polymers in the amorphous state being like spaghetti. One, spaghetti's way shorter. Spaghetti would be like candle wax as opposed to a polymer. So you would need spaghetti that's meters long, several meters long, to have more of that right length to diameter ratio. So you need really fine angel hair or capellini, and you need it to be 2 or 3 meters long. That'll give you a better picture. And then, is this going to play? Oh, it's not going to play. I had Indiana Jones saying snakes. Why did it have to be snakes? These are fake. That's ball snakes. So I really like the mental picture of, think about a nearly infinitely long snake. So there's not much of the scary parts of the snakes. But you look at this and think about how snakes have to slither past one another. And what happens if they're warm and happy, they move more. And if they're cold, they move less until they don't move at all. That's a lot like polymer chains. Okay.
Here it goes. I talk to my plants like they're babies.
Hey, you don't need to get that personal to get the State Farm Personal Price Plan. It just helps you create an affordable price. Like a good neighbor, State Farm is there. Call or click to get a quote today.
People come from all over the world just to see the snake dens here. A lot of children are a little more willing to hold the snakes and to interact with them. Sometimes the adults are a little more apprehensive, which I think is kind of odd, that it's almost like the fear of snakes has been built into people as they grow up.
And I like snakes.
Here in the Inner Lake of Manitoba, Canada, is by far the largest aggregate. So plentiful are those winter temperatures. So that here in the Interlake region, the limestone bedrock is very close to the surface, and so that allows the cold and the water to crack and fissure the limestone, and it makes great big sinkholes, and that enables the snakes to get below the frost line during the winter. There's a very limited number of these den sites. So all the snakes in an area have to go to that den site that's in their region.
Video. They show you how what happens when the female snake comes through, because most of those are males. It's a big ball of snakes and stuff. Anyway, they're not scary. I was never afraid of snakes growing up in Maine because there are no venomous snakes. And these are just garter snakes. They're not scary. Down here, I'm afraid of every single snake because I don't know which one's which. Ugh. Yes. And then the rat snakes sort of look like copperheads. Ugh. Anyway. So this is what I usually have in my whatever bag I'm carrying for my work bag, so that I can always talk about the 3 things that make polymers different. And I left it on my table when we did that day. So my daughter took this and completely straightened it out and had it all coiled up nice and neatly, and it was in my little plastic box, and I tried to uncoil it and it turned into this. Okay, so this, I did a back of the envelope calculation for saying one of these seed beads was a CH2 unit. If one of those seed beads is a CH2 unit, here's like a typical polyethylene, not even super high molecular weight or anything. And so I have since lost all, I used to have some little other colored little loose seed beads that I have, they were a nuisance, so I got rid of them. But so solvent molecules would be the size of 1 to maybe 6 of these beads. That's what a solvent, that's what a typical small molecule would be. Something like a sugar or a steroid might be the size of 7 or 8 of these beads. But look at this, right? You think this is going to behave differently than something that's made from 8 of these beads? And most small molecules are going to even, that's a lot of the solvents and stuff would be smaller than that. So even though this was all untangled and coiled up nice and neatly, it like tangled instantly, right? Because of the length and the flexibility and all of that. And this is, this is what a real polymer would be like. Then I got my 2 Velcro pieces here. Okay, these are just like to make cords. Keep your cords nice. There's no way for me to pull these apart, right? And if I could somehow, like if they were both glued to 2 flat plates or something, I couldn't have pulled them apart this way. There's no way. I have to peel, right? They're easy to peel apart. So remember when I said there's a lot of summation of intermolecular forces? And that's why polymers don't have a boiling point. They don't vaporize. And they really have a high cohesive strength, right? They stick together. And that's because even weak van der Waals forces, like one single hook and eye, make something super strong, right? So every hook and eye in this Velcro is very, very weak. But you start summing them up over a decent surface area, and you get something that's very strong. Strong enough to hold a spacesuit together, right? And then the other one, I've been sort of slowly letting this, that's the one that's in my videos. But I've been slowly letting that flow. It takes about 5 minutes for it to actually turn into a puddle. But if I bounce it, it will end up on the carpet. But right? If I bounce it, it's acting like a solid. Short times. Like what's the time scale that's important in the bounce? Not long. Less than, way less than a second. But on the time scale of tens of minutes, it acts like a liquid. So that's one of the things that makes polymers different is that time scale of motion, the time, your frame of reference, the time you're observing it. It'll behave like a solid or like a liquid. And we say that's viscoelastic, right? Viscoelastic. So first one, they entangle. Second one, you sum up all those weak intermolecular interactions, it's really strong because there's so many. Third one, they're a solid or a liquid, depending on how you look at them, right? A time scale of motion.
I almost want to see like a time-lapse video of a ball later.
I have one. It's in Moodle. It's this exact one. I used a tripod and set up a camera and took a picture every 5 seconds for 10 minutes or something. So it's there. It's not supposed to do that. Okay. So that was the review from last week when I forgot my toys. This week that was at the end of Module 1. We are in Module 2, and we sort of talked about what we're going to start talking about at the end last Thursday after you guys did your slides. There's, I can't talk today. So after you guys did your presentations, we took just a few minutes because we had extra time, and we went and started talking about the beginnings of Module 2 and how we're going to talk about microstructure and that kind of thing. And we're not going to get into the details of crystal microstructure till the end of the semester, but we're going to talk about how crystallinity changes polymer properties, okay? And this is not the right slide. This is the right slide. Okay, so we're going to be thinking about how crystallinity impacts strength, stiffness, toughness. That one's a little counterintuitive, so we'll talk about that. Barrier properties, that means like how gas can flow through the container. Okay, so can oxygen go through this plastic? Yes, probably pretty easily. What is this one? Polypropylene. Yep. Couldn't put something carbonated in here. It'll go flat. Solubility behaves very much like barrier properties because if the gas molecule can get in and diffuse through, then the solvent molecule probably can get in and make the polymer dissolve. Transparency, we've talked a little bit about that, right? Transparency, whether you can see through it or not. And thermal properties, just a little bit. Okay, so I mistakenly already had the answer up, but I think you guys already would. Everybody knows this. This is fairly intuitive, right? Hopefully. So if we have two types of polymer, we have linear polyethylene, which is shown in the top cartoon. And this gentleman is Professor Coleman. So he taught me when I was a graduate student. And they had, they used to have these CDs that they sold instead of a textbook. So they were really early in trying to get away from a paper textbook for cost reasons, and so they sold these CDs. And so that was before Bitmoji and stuff, but I don't know how they got their little cartoon versions, but it looks like him. It's pretty good. Okay, so that's Professor Coleman. And there's our linear, right? No branches. Here we've got some little branches hanging off our polyethylene. Which one do you think can crystallize more easily? So that means it's got to be able to fold itself into a regular repeating ordered three-dimensional crystal, okay? Which one, the linear or the branch? Who's linear? Yeah. Right. What makes something crystallizable? What do you think? Pattern? Yeah, it's got to be able to fit together, right? You've got to be able to make a pattern in the crystal structure. Did you want to add something?
I was saying order, but
order, yeah, right. So you've got to have something that has a very regular structure. If you have randomness, it's not going to be able to crystallize, right? Does that make sense to everybody? So if I have randomly scattered around branches, it's not going to crystallize because you can't fold it into a nice, neat structure that can pack together and make a crystal. There's just no way to do it if you've got a lot of randomness. Okay. So, linear polyethylene is going to have a higher crystallinity than branched polyethylene. Most branched polymers are probably going to have no crystallinity, but polyethylene is an oddball. It loves to crystallize. So it will crystallize less, and it might even be transparent, like a sandwich baggie, but it's going to have some crystallinity. Okay. So which one do you think is the high-density polyethylene? The linear, more crystalline sample, or the somewhat branched, less crystalline sample? Which one's going to be high-density polyethylene?
More crystalline.
Yeah, the first one, HDPE, right? It's going to have HDPE is going to be mostly different in the fact that it has a higher density. It has more crystallinity than LDPE, right? The low density is because it has less crystallinity. Go ahead.
I don't know if this question is like too early, but what are some ways that we make those chains more aligned?
So getting to make polymers crystallize, we will really talk about that at the end of the semester, but you've got to sort of get them to line up in some way, right? Now, polymer crystals, they're not lining up very long. They fold back and forth. It's like holiday ribbon candy. So polymer crystals, the crystalline domains tend to have dimensions sort of like a sheet of paper. The chain direction is this way. It's folding back and forth, but it might have a decent sized surface area. It's really thin. And so processing, so you can do it with the structure, right? So with polyethylene, if we put some branches in, we're going to inhibit crystallinity. If we're talking about something else, like maybe PET, the way we process it can change the amount of crystallinity because we do things to make it crystalline. And since we're in the College of Textiles, a classic example is drawing a fiber, right? You're trying to get more alignment and you're going to improve the tensile strength by increasing the crystallinity. So it comes in from that processing side if it's not from the structure. So if you have the same polymer, the higher your degree of crystallinity, typically the higher the density, right? Because you have less free volume in the crystal than you do in the amorphous phase. Right? Empty space, so your density is going to change. So this is polyethylene. So we got 2 bottles made from polyethylene in an oven, not very high temperature. One collapsed and one is still standing. Which one's the low density polyethylene? Yeah, the collapsed one, right? You have less crystallinity. It's going to flow more easily. It's going to melt sooner. And so a lot of this stuff, I think we sort of know it, but we don't maybe know why we know it, right? But yeah, so the crystallinity improves the mechanical properties. It helps at a molecular level hold all those chains together. And so it's going to be more temperature stable. So this person supposedly is squeezing, you know, these two bottles with the same amount of force. It's one hand, he's squeezing them. One collapsed, and one really hasn't changed. Which one's the high density one? Yeah, the top one. Yeah. The one that's not squished, right? So if we want a bottle that holds its shape, well, maybe we want high density polyethylene. If we want a squeeze bottle, the low density might be a better choice, right? So that we can really tailor this and use this to our advantage. Maybe you're using a plasticizer to make those changes. There's other ways to do it besides just crystallinity, but we're focused on crystallinity, okay? Okay, so we've got a milk jug, and we've got cling wrap or sandwich baggies. So the polyethylene that goes into milk jugs is stronger, stiffer, more opaque, less optically clear, less transparent than the type of polyethylene that's used to make film wrap and sandwich baggies. It has greater optical clarity, more flexible, less strong. Which is which? Which type of polyethylene is used to make the film wrap? Low density. Absolutely. Right? So, we can already think of that list of properties. As I increase the crystallinity of my sample, do I increase or decrease the strength? Increase. As I increase the percent crystallinity, do I increase transparency or decrease transparency? Decrease. I increase opacity. However you say that word, right? It becomes more opaque. That is a rule of thumb. That is not true for every polymer. Okay? Because the refractive index of the crystals has to be different than the amorphous. And that's not true for every polymer, but it is true for the vast majority, and it's always a good assumption to make, right?
Does the crystalline structure mean it also gets more brittle?
It does get more brittle. So as we increase crystallinity, we increase the brittleness. Say that again? Decrease the toughness. Yes, it's really, I struggle, right, with toughness because how we use it in general language and how we use it scientifically are not exactly the same. They're sort of similar, but they're not exactly the same. So if you say, oh, does increasing the percent crystallinity, does that increase or decrease the toughness? I always have to stop and be careful.
Depending on the type, like glass,
not very strong. Right, but glass is not a crystal. It's amorphous. Okay. So, but if you think about...
When people think crystal,
yes,
glass.
Right. Yeah.
I'm talking crystal, I'm talking...
Yeah. So, but if you're thinking about, like, if you think about, like, a quartz crystal, you can shatter it, right? It's very brittle. So... what I have to do when I want to think about toughness and crystallinity in polymers is I have to think about the fact that toughness is almost the inverse property of brittleness because it makes sense for my brain. Oh yeah, it gets more crystalline, it gets more brittle. But yeah, the toughness. So as we increase crystallinity, toughness goes down because the brittleness goes up. Okay. So, structure property relationships are a big part of polymer science and engineering. And I wish we had more time to focus on that in this class, but we're going to talk about it in the first third of the class and then come back to it at the end. And in the middle, we're going to learn some synthesis and kinetics. So, structure property relationships are really important for like the science of polymers. How do we, if I need this property, what do I need to do with for the, what polymer do I need to use? How do I need to process it? So again, it's really structure processing properties, right? It's really more of a triangle than just a back and forth. So when people just say structure property relationships, you assume that they're processing the polymer in exactly the same way, right? Otherwise, it's not a fair comparison. Okay. So at the end of the semester, we're going to talk a lot more about morphology and crystalline morphology. So we've talked about, okay, amorphous, no long range order. There's, it's a random structure, amorphous. In the crystalline, I've talked, how these polymer chains fold back and forth. That's crystalline. And then our polymers are semicrystalline. And so when we start talking about crystalline morphology, we're going to talk about how do the crystal parts, how are they arranged and dispersed and that type of thing. And we'll do that at the end of the semester. And that depends on it, like it's very different from a fiber than from something that was a melt, than from something that was extruded, right? That microstructure of this semicrystalline polymer is going to be very different. Okay, so there's no 100% crystalline polymer like there are for small molecules. There's 100% crystalline. Right? If we're talking about salt or sugar or other small molecules, it can be 100% crystalline. But with polymers, even if we have a polymer single crystal, we've got like the chain ends, we've got the folds and stuff like that, and so not 100% of the material. So all polymers that are crystalline are to some degree semi-crystalline. And so when we're talking about polymers, we are usually going to talk about the percent crystallinity. So is there any crystallinity and how much crystallinity do we have? And then we need to talk about the crystal morphology. What's the size, shape, distribution of those crystals? And all of that can impact properties. Right now, we're just going to talk about, do we have crystallinity or not? And if we increase, so we're going to talk about how crystallinity impacts properties just like we just did, right? So if we increase crystallinity, we increase strength. We increase crystallinity, we decrease toughness. That's the sort of level we're going to be talking about now, okay? So you'll see this chart, table, over and over, right? And this is in Moodle. You don't have to copy all this down. So we've already hit strength, stiffness. Oh, we didn't say stiffness, but stiffness makes sense, I think, right? You increase the crystallinity, you increase the stiffness. It sort of goes hand in hand with strength. We covered toughness. Optical clarity. Again, this is a rule of thumb because this is all predicated on if the refractive index of the crystal part is different than the amorphous part. If that fact is true, then as you increase the crystallinity, you are making the sample more and more opaque. Okay? Go ahead.
So, like, just as a rule of thumb, most of these either have, like, what are the two terms in math? And it's, like, the relationship that's, like, either inverse or yeah, proportional.
Yeah. So so it's not, it increases, you got to think about how you're saying it, right? So if you increase crystallinity, you're going to decrease the clarity. Yeah. So for barrier properties, that's like, can gas molecules go through the plastic? Okay. And you have to think about the tortuous path. I need to remember the pink one worked really well. Okay, So like if I have, here's the wall of my soda bottle, right? I care about the CO2 going through or oxygen, nitrogen, whatever. But usually we care about the oxygen because it can make things, it's reactive. It can make things go bad. Right? So if this is just amorphous, it can it's transport, the time it goes through, you're really talking just about the thickness, right? That's the path. It's going to go straight through if it's amorphous. But if we have a semi-crystalline polymer that's in there, right? So you got all the amorphous chains that are just sort of all over, right? But I've got all these little crystalline domains. Well, now, when my gas molecule, my CO2 molecule, okay, it's going in, it's diffusing, it hits this one. So now it's got to go up here, it hits this one, and then it's got to go around here. And then if I've got that, I got another one. Now it's got to go around, and maybe it's going to hit another one before it can get through. So the path, the diffusion path through just the amorphous parts is way longer. Does that make sense to everybody? Way longer. So the more crystalline, the longer the path for the diffusion. So the more crystalline, the better the barrier properties, right? Make sense? Okay? That one's one that people usually have never thought of. So that one, I like to spend a little more time on that one. Solubility is the same thing. Solubility, the solvent molecule is going to start dissolving the amorphous domains first. So if the solvent molecule can get in there, it can start swelling and dissolving the amorphous domains. But essentially, the crystalline domains usually don't dissolve. You have to the polymer has to uncrystallize, right? It has to unfold to go into solution. So the more amorphous, the more the solvent molecules can get in, the easier it is to dissolve. Does that make sense? Those of you who are chemists are more used to thinking about molecules moving and that kind of thing, and that's sort of what we need to do here. Okay. Branching and network formation. So we've talked about how branching can impact properties, right? We've already talked about that. We can have short chain branching or long chain branching. They both are going to have impact properties in different ways. So the classic example of that short chain branching is the difference between low density polyethylene and high density polyethylene. Long chain branching also happens in polyethylene. And if I have long chain branching, the entanglement becomes crazy, right? It's just super hard to get something with long chain branching to unentangle. So it's going to change the mechanical properties and that type of thing. If I have a star polymer, essentially that's a core with a bunch of branches coming off of it, it's going to behave way differently. So if I think of all of these, I have the same molecular weight. This one might be where we start talking about, is it a polymer or not, right? So some people like to define, how big does it have to be before it's a polymer? And people will be like, oh, it has to entangle. So that works really well for flexible polymers. But if we have a rigid rod polymer or a really stiff polymer like Kevlar or Nomex, they don't really entangle because they're too stiff. What's going to happen with the star polymer?
like not the star breaking between it, but the star to star connection with that break.
I think you don't want to use the word break, but right, it's not, they're not going to be entangled really, right? The arms are shorter. So the arms would have to be really long to get really good entanglement. So this, you can have really high molecular weight, but it's not going to really be entangled the same degree, right? So the mechanical properties, the flow properties especially, are going to be very different between these. Okay? So very, very different. So if our linear version of this blue circle polymer, if our linear version can crystallize, do you think this one can crystallize?
Yes.
If it's polyethylene, if it's not polyethylene, probably not. It's too irregular. Structure is too irregular. What about the long chain branching? Yeah, it probably can crystallize. But it's going to have a lower degree of crystallization. It's going to have more defects. The crystals are going to have to be smaller, right? Because it's got some branches. What about the star polymer?
No.
Yeah. I mean, I don't want to say it never happens, but it's going to, if I'm going to rank these on how I think they can crystallize, well, the linear polymer would be first. The long chain branches would be next. This one, I would hedge my bets and be like, oh, it's polyethylene. Yeah, maybe a little bit. And then this one, I'd be like, yeah. It really depends on how long those arms are. But I would be thinking that one probably couldn't crystallize. Why did you pop up? Okay. So, what's the difference between a side group and a branch? Getting into semantics a little bit. None of these markers are great. Let's try this one. This keeps going. All right, if this is a methyl group, I've got polypropylene. Is this a side group or a branch? It's a side group. It's on every other carbon. It's part of the monomer. It's a side group. Okay. So that's really the easiest way to think about it. Did the monomer have something hanging off of it? Then it's a side group. If it's not, if it's from, if I've got 1, 2, 3, 4, 5, 6, right? If I've got this hanging off, it could have been a side group. If it's on every other carbon, it's a side group. But otherwise, if it's just in 1 or 2 spots, it's probably more likely a branch. Okay. So let me not get that. So if this was made from CH2, CH3, right? That's the propylene monomer. This is, no branches, just side groups. Could be a ring, okay? So there, my bottom example, I've got polystyrene. Every other carbon has a styrene or a ring, benzene ring hanging off of it, phenyl ring. Okay, so the top one, the circles is is showing you a branch. I gotta get some better graphics there. Okay. I put that slide in because in the past students have sort of used the words, have called side groups branches and confused the two a bit. So, but keep improving that. So hyperbranch polymers and dendrimers. So this isn't a star polymer, right? We got a core, It's not a four-armed star because each time I come out, it splits. And so I started with a core of 4, and then now here I'd have 8 functional groups if I hadn't polymerized again. And then here I had 16. And here, if I count all those alcohols, I'd have 32, right? And if I did it again, I'd have 64, right? It's going out and out. And so this is called a dendrimer. They're not easy to make. If you just polymerize a trifunctional monomer, you're going to get a cross-linked network, right? Does that make sense to everybody? But if we are controlling the polymerization, we're like protecting and deprotecting, this is like hard synthesis. You can make these things. They're extraordinarily expensive because of the way you have to make them, and you have to do it step by step. They're very expensive. Mm-hmm.
What's their purpose? Like, why is it worth making them?
So I think they've been commercialized in 2 areas, and one I'm not totally sure they've hit the consumer market or not. Look at the outside of this molecule. All those OH groups, very hydrophilic. You can design it so the core is very hydrophobic. And there's some empty space in that core. You can stick hydrophobic drugs on the inside of that. Then you got this hydrophilic ball, and you can use it as a drug delivery system. And drugs, we have a really hard time with hydrophobic drugs that need to get into our bloodstream because our bloodstream is water-based, right? So a lot of drugs are very hydrophobic, and getting them where they need to go is an issue. So that's one area. And so I know dendrimers have been studied for drug delivery for a very long time. I do not know if they are commercially available or not. They are in synthetic car oils. You know why that's so expensive? It's because of these, right? Synthetic oil. Why do you think these might be so good in synthetic oil? Well, okay, so the chemistry is designed so it meets the needs of the oil. So this one would not work, right, with all those OH groups on the end, probably. So the chemistry is controlled by what is needed for the oil. Okay, it has to be really temperature stable. But what's the operating temperature range for a combustion engine? What's the temperature in Maine where I grew up in the winter?
Oh, like -30, probably somewhere where I grew up.
Yeah. So, yeah, it gets way below 0 Fahrenheit. Right?
Freeze.
So, but then the operating temperature of a combustion engine is very high, right? You want an oil that is going to protect your engine at very low temperatures when it's cold and at very high temperatures when it's operational. Most things and most polymers, their viscosity changes a whole lot over that kind of temperature range. These are like little molecular ball bearings. They might expand and contract a little bit with temperature, but they're just like a little molecular ball, so they don't change a whole lot. So their viscosity is not changing a whole lot with temperature, and so that makes them really useful in synthetic oils. Go ahead.
Is natural car oil bad for cars and me? Like, is synthetic oil much better?
Back when I was a kid, you would use a different oil in the winter than you would in the summer. So you would change out the oil when you did an oil change. So synthetic oils, you don't have to do that.
So whenever we fill up our windshield wiper fluid, we always have to buy the like anti-freeze ones.
Yes.
So it doesn't freeze during the winter. Do you think that they like also apply
No.
using this?
No. This is way too expensive.
Okay.
They're using glycol. And that's really bad because it's sweet and it's not bad, but like you never want to leave windshield washer fluid out because animals sometimes will get into it because it's sweet to them and it can destroy their kidneys. So you don't want animals drinking windshield washer fluid.
One of our like machines in the tiny finishing lab uses like antifreeze like that to like agitate the beakers so that the actual like instead of using like water so it doesn't get heated up or freeze or anything. But I guess the company like doesn't make that machine anymore because it's not like environmentally friendly and everything. So they just we have
The circulating bath is yeah. So and that's like there used to be chlorofluorocarbons, which are really bad for the atmosphere, and they used to be in a lot of coolants, and they've been phased out, and so there's issues with a lot of different molecules like that. But they're not dendrimers, because these are not going up into the atmosphere. No way, right? Way too big. Okay, network formation. I'm stopping and writing myself a note because I want to do something in class on Thursday that I usually do later in the semester, but I'm thinking it'll be more meaningful now. Okay. The pen doesn't work. It's all right. Oh, look, there's another one. Oh, so hopefully on Thursday I'll come in with my bag of toys. Okay. Okay. So I want you to think just about geometry. Okay? Just about geometry. If I have difunctional, that one's not going to work. If I have, we've got the cheap Amazon markers. They're not the Expo markers, so I can't use them the way I usually do, right? But if I had Expo markers, right, I could get them to stick together, right? They're bifunctional. I can make a chain. That's all I can make because they're only bifunctional. Does that make sense to everybody? Okay. I have a pop bead, like for toddlers, you know, the big pop beads that I would bring in, and you can only make a chain because they're bifunctional. But something happens, and I don't know, they're like sticky and gross. I don't like to touch anyone. Go ahead.
When you say bifunctional, you mean like they can stick to the beginning and end?
Yeah, so like I have an A that fits into a B, so they can link together, but only the A can fit into the B, and B can't fit, right? So they're bifunctional. For this example, right? If they were trifunctional, I can make a network. Can you guys start to visualize that? Right? When it's trifunctional, I can make a network. If it's tetrafunctional, meaning 4, I can make a network. Doesn't really have a whole lot of difference, right? So any functionality greater than 2, I'm not making a linear chain. I can make a huge molecule, I can make a huge macromolecule, but it's going to be what we call a network or heavily cross-linked. It's not going to be a linear chain that has the potential to be soluble. Does that make sense to everybody? Okay. So we've got functionality of 2, I can make a polymer, a linear polymer. If I have a functionality of greater than 2, 3 or greater, I'm going to make some kind of network. Okay. So bifunctional monomers, we're just going to make linear chains. If I have something that's trifunctional, okay, so that is phenol. Okay, the ring with the OH, that's called phenol. And next to it is formaldehyde. The phenol doesn't necessarily look like it's trifunctional, but where you see the little red stars, those carbons are activated by the OH group. This is you are not responsible for this chemistry. Okay? I'm telling you, the phenol is trifunctional. When it reacts with the formaldehyde, it starts making a network. And then you can keep polymerizing it and it makes a bigger and bigger network and more highly interlinked network. This is Bakelite, guys. This is the first fully synthetic polymer. Okay? Was a network. And so they would start to polymerize it like this, and that was still moldable. So they would start polymerizing it so it's behaving a little bit plasticky, right? Like you can mold it and stuff. It's not just a mothball, right? So then they'd get it in the mold and they'd keep polymerizing it to get it to be stable and cross-linked. So these phenolic resins were the first fully synthetic polymers, and we called them Bakelite. So we can make a network just like this. We can make a network by reacting a trifunctional monomer, polymerizing a trifunctional monomer. We can also make a network by taking an existing polymer and cross-linking it. That's what we do with rubbers. Okay? So natural rubber has a double bond in its backbone. That double bond is reactive. Where you react it with sulfur, we call that process vulcanization. And now you have a cross-linked rubber and you can make a car tire out of it. Okay? That's how you take gooey tree sap and make it into a car tire. You cross-link it. Okay? So 2 different ways to get to networks. We can polymerize a monomer with a functionality greater than 2, or we can take already formed polymer and cross-link it. 2 different ways. So let me change a cross-link density. So as we adjust the amount of cross-links, what do you think happens? I'm going to show you a video made by a really talented graduate student. But yeah. So what do you think? As I increase the cross-link density, am I able to stretch it more or less? Less. Is it stronger? Yeah. It is stronger. It doesn't stretch as much, so it's less tough, right? The area under the stress strain curve is the toughness. Okay. So this is fun. Caitlin, it's a really good science.
I think we can all agree. Slime is pretty cool. But if you've ever made slime yourself, then you probably know that you have to mix together a couple of kind of weird ingredients to get this fun stuff. The 3 ingredients are water, glue, and a type of soap called borax. They may seem kind of weird, but each ingredient has a purpose. Glue includes a compound called polyvinyl alcohol, or PVA, which is a type of polymer. Polymers are made up of long chains which can slide against one another, which is what makes it easy for glue to flow. But when you add borax and water, little compounds called borate ions attach to those chains and link them together, which scientists call cross-linking. Cross-linked polymers can't flow over one another like they did before, and that's where you get slime. Glue is normally pretty sticky and liquidy. If you pour it, it flows nicely out of the bottle. Now, if you mix it with some water and food coloring, and then add a mixture of borax and water, you can see that it instantly changes to a slimy blob. In other words, its viscosity changes. It goes from a liquid to something known as a non-Newtonian fluid. The really cool thing about non-Newtonian fluids is that the way it flows, or its viscosity, changes when you touch it. That's why when you tear it apart, it breaks like a solid, but when you gently stretch it, it flows like a liquid. So let's do a little experiment. An easy way to see how borax affects slime is by adding more and seeing what happens. For this pink slime, I added 4 times more borax than what I did for the blue slime. You can see that this slime is a lot firmer. This is because more of those crosslinks were able to form, holding all of those polymer chains together. So instead of flowing across one another, they break. In these sped up videos, you can see that if you leave the slime out, the blue slime flows much faster than the pink slime. And that's just because the pink slime has more crosslinks than the blue slime. And there you have it. Slime is an example of a non-Newtonian fluid that changes viscosity when you play with it. Glue includes a polymer made up of long chains, and borax forms little bonds called crosslinks which hold together those chains and make slime. Oh. Ah. Oh dear me.
Okay. So, hopefully, makes you remember that if you change that crosslink density, you're going to change how strong and tough the material is. And then when I have this putty that isn't cross-linked, or it might be lightly cross-linked, but if I pull it slowly, flows, right? I'm giving the chains time to disentangle. If I pull it fast, and this particular one, it's hard for me to pull it fast enough. If I pull it fast, it fractures, right? So it's behaving like a solid. Okay, you get a clean fracture. So that's related to that viscoelasticity, right? And so you can dramatically change the properties by cross-linking, and that's literally how you go from tree sap to a car tire. Bunch of additives too, but so when we have natural rubber, which is shown here, right? Backbone, this is cis polyisoprene. The sulfur will react with the double bonds and cause these crosslinks to form. And it might be one sulfur or it might be several sulfurs. That's why it has this N. And so you can go from like a natural rubber eraser, it's pretty soft, right, to a natural rubber car tire. I don't think they're not made out of natural rubber anymore, but we can go to a car tire that's, I can't stretch it. I can't make it behave like an elastomer in my hands, but it is one. But it's highly cross-linked, and so it's much stronger and stiffer than, something that, like an eraser, which is going to behave more like this and less like a car tire kind of deal. It's made from the same material. Go ahead.
Is cross-linking at all related to crystallinity?
So, if you have a cross-linked material, it probably can't move enough to crystallize. So usually cross-linking is, when you're talking about a cross-linked material, it's usually amorphous, okay? But changing that cross-link density is a structure-property relationship, just like increasing the amount of crystallinity, right? So one of the nice things about what we call thermoplastics, right? You guys have heard that word, right? A thermoplastic versus a thermoset. What's thermo? Heat. Do you know what the root plastic means and why we call polymers plastics? Why do we say plastic surgery? Changing. It's changeable, right? It's changing. So if it's a thermoplastic, what's that mean? Well, I can use heat to change it, right? So I can take a thermoplastic and I can melt it and I can make this chair.
Thermoplastics are the ones that you can heat them up and they can be reshaped again versus, I think it's thermosetting, where you can heat it and shape it once.
Right.
And then it just melts.
Right. Oh, no, it won't melt. It'll decompose. So a thermoset is going to be a cross-linked material. So thermoplastics are the ones that you can readily recycle. A thermoset you would have to take back to monomers. You'd have to unpolymerize it, depolymerize it. So we usually say it's not recyclable. Like you can't just melt and reprocess it, but you can recycle it. It's just way, way, way harder. It's chemistry. It's not just a melt and reprocess. We really need a new word, a different word. So like this is more than likely a thermoplastic because this was molded. So I can see it's molded, like the back is one piece and the seat is another piece, and the seat is made from more than one piece, and then we've got the cushion on top of that, right? This is probably extruded. So a thermoplastic you can melt and reprocess. A thermoset is set. Okay? You can't melt and reprocess it. Go ahead.
So if you were to put a thermoset plastic in like a really hot oven, would it just catch on fire instead?
It's not going to melt and flow. It might catch on fire. It might like burn, right?
Yeah.
And you've probably done this cooking. Okay, right? So like if you've burned a steak or something like that, right? That's not all of it depends on, I guess. So you've burned polymers, you've decomposed polymers when you've been cooking, but you haven't necessarily. They weren't necessarily cross-linked polymers. That may or may not have been cross-linked.
So like some containers, they say, oh, you have to remove the cap, and that's not recyclable, but the bottle itself is recyclable. Is that anything to do?
So the caps are probably not thermosets, but they're probably not a material that the recycling facility takes. And then it might be that it's too small for the recycling facility to sort. And then it also might be like the labels, the plastic labels on soda bottles, like if they tear off, they can gum up the machinery. So plastic bags are thermoplastics. You can melt and reprocess them, but they can't go in the recycling stream because they gum up the machine. It's really bad. Go ahead.
I can't remember. It wasn't the. Did we call it the melting point for these, or do we not call it the melting point very specifically?
So
I was trying to remember what it was.
So the melting point is when what melts, crystals melt. Okay? If we have an amorphous material, we have the glass transition temperature. So all polymers have a glass transition. But not all of them have a melting point because not all of them have crystallinity.
My question was, what has a higher glass transition point? The thermoset or the thermoplastics?
So I visualize this by, if you think about how much energy do I need to put in to make the molecules move? If they are all tied down with crosslinks, do they need, in between the crosslinks, do you need to put more energy in to get them to move or less? More. So as you increase the crosslink density, you're also going to increase that glass transition temperature. Does that make sense? That's the thing we're going to talk about at the very end of the semester. And that's something I'm very likely to ask you about at the very end of the semester. And so a lot of this stuff I think is pretty intuitive if you can think about, well, how much energy do I need to make a molecule move? That's a way of thinking of temperature. It's a way of defining temperature, actually. Right? The amount of molecular motion is a way of defining temperature, which is a weird thing. But almost all of you are going to take physical chemistry or thermodynamics, and you'll have to think about that stuff. Okay. All right. Okay. So our next big topic is isomerism. And I'm working to build out all of these sections in H5P activities for a resource for this class, but really for the, and that's how the online section that I offer in the spring is going to be learning this content. But I've done it for the isomerism. So if you get confused by any of this, make sure you look at those H5P activities in Moodle. So sequence isomerism. We're going to talk, okay, so isomerism, you guys remember what an isomer is from freshman chemistry? Right? We got it in the box, right? Two molecules are isomers if they are made up of the same number and types of atoms, but you change the arrangement. So in polymers, we're going to talk about 3 types of isomers. And I'm, again, missing my expo markers because I used to use them to talk about sequence isomerism. So the 3 types of isomerism we're going to talk about is sequence isomerism, stereoisomerism, and structural isomerism. And the second 2 we're really going to talk about in terms of vinyl polymers, and then the third, structural isomerism, we're going to talk about in terms of diene polymers. Okay, but there's lots of other examples. And you can start mixing and matching these and like having multiple types of isomerism in a single polymer, but we're going to look at them separately. Okay, think about them separately. So we'll talk about, we can probably get through sequence isomerism today, and then we'll wait and talk about the others on Thursday. Okay, so sequence isomerism. I used to have the expo markers, and I'd line them up, right? I'd get them all stuck together into a marker chain. I'd go marker cap, marker cap, marker cap. CH2, CH2 with a branch, CH2, CH2 with a branch, CH2, CH2 with a branch, CH2, CH2 with a branch. Sequence isomerism is when one of those monomers inserted backwards. So I've got CH2, CH2 with a branch, CH2 with a branch, CH2, CH2. Right? I flipped one of those over. Does that make sense? So when we're polymerizing, we can talk about, we've got the tail. The textbook and sort of the standard is that's the CH2. And then we've got the head, and that's the one with the side group. So we've got tail, head, head to tail. The next one, the next monomer adds, it's going to be head to tail. Here, we've got it adding head to head, right? This is the one where it's inserting backwards. That's this. The one with the branch with the R group is side by side. When you're polymerizing, you think the side groups want to be adjacent? They tend to get in one another's way. And if it's a big ring, it's really not going to want to happen. So usually monomers want to add head to tail, head to tail, head to tail, but they can go in backwards. Making some sense? Right? So if we add, so that's sequence isomerism. Addition usually occurs head to tail, head to tail, head to tail, but it can go the other way, and that would be a sequence isomer, right? Okay, so I'm going to show you a video that I made with my pop beads. Okay, went on AliExpress and ordered a whole bunch of like pop beads and then tried to make some monomers. Okay, so the blue bead is my tail. The pink bead has its little side group. That's the head. Okay, so now we're going to watch our video. Oops. monomer. There's our tail, there's our head. We're going to polymerize.
We just made a polymer that has all head-to-tail linkages. So we have one isomer that's fully head-to-tail. Now remember, the tail is the blue and it doesn't have the side group. So in a real polymer, that's representing the CH2 group of the backbone, and the purple is the CH with the side group. So that's the head. So we go from head to tail, 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 the whole way down the polymer. With the same number and types of atoms, we can rearrange these by just changing the sequence, and we can show sequence isomerism. So if we don't have 100% head to tail, head to tail, head to tail, we will have a different isomer even though we have the same number and types of atoms. They're just arranged differently. They have a different position or a different sequence. So let's take a look at that. Here we have another isomer. Instead of having completely head-to-tail insertions, we have some monomers that inserted backwards. So essentially the repeat unit is in there backwards. So we have the same number and types of atoms, but they're arranged differently. Remember, the blue is the tail, the CH2 group, and the purple is the CH with the side group if we're talking about a typical vinyl polymer. So here we go head to tail, head to tail, head to head, tail to tail, head to tail, head to head, to tail to head. So a different isomer than the last pop bead polymer we just looked at. And this is an example of sequence isomerism. Now, look, when we have head-to-head, the side groups are on adjacent carbons and they're very close together. What do you think would happen if those side groups were even larger than the yellow balls I have here? Do you think having a large side group promotes or hinders head-to-head insertion?
Okay, so what do you think? If I have a bigger side group, instead of a CH3, I'm going to have a ring on each one of these. If I'm polymerizing styrene, do you think it has more sequence isomerism or less? Less. Yeah, very little. Right? The bigger that side group, the more it's going to get in the way, and the less it's going to want this to happen. Right? It's not going to want to be on adjacent carbons. So if we look right here, where we've got that head-to-head, so if this was bigger, it couldn't both be pointed in the same direction. It would have to like flip and get out of the way, right? So if we have a larger side group, it's going to inhibit sequence isomerism. If we have this polymer where it's CH2CF2, polyvinylidene fluoride. I don't know why it has that name. I don't know why the monomer's named that. Okay, if we have this is going to have, the fluorine and the hydrogen are almost the same size. So this one's going to have a lot more sequence isomerism because it just doesn't matter. The size is almost the same. So very common for sequence isomerism. So there's where we're going to end today because I cannot talk about stereoisomerism in 5 minutes. So this is where we'll end. So again, we're going to talk about 3 types of isomerism, and we're going to start with stereoisomerism or tacticity on Thursday. But hopefully I'm going to remember to bring my toys, and we're going to we'll take a little break and we'll come back to it on Tuesday, okay? All right. I was going to say have a good weekend, but it's only Tuesday. It's only Tuesday. I'm looking at my slides because I'm like, I think I had something different. Okay. So at the end of class on Tuesday, we talked about our first type of isomerism in polymers. That was sequence isomerism, right? Today we're going to talk about stereoisomerism. Who remembers hearing the word chiral or chirality?
In your mistake in organic chemistry.
Right. Okay, so we need a chiral carbon to talk about stereoisomerism because a chiral carbon is how you get to a stereoisomer. Okay, so my right hand, I can in no way rotate to make it the same as my left hand, right? Even if they were, fake and exactly the same, but a mirror image of one another. They're mirror images. I can't rotate it to be the same. That's a stereoisomer. You can't rotate it. So there's just something going on, right? We cannot rotate around, but the atoms are essentially, they're all attached to the same atoms, but one's on a different side. So I can't keep track of which markers write in which classroom. It annoys me. Okay, so if I have a carbon atom, and it's going to be tetrahedral, right? So I've got A, B, this is going into the board, C, this is coming out of the board, D. It's attached to 4 different things. Okay? Okay. I'm making the mirror image of it. A, B, D, C. Those are really similar, right? Really similar. But I cannot rotate them from one to the other. And these molecules are going to have the same boiling point and freezing point almost always. But they're going to rotate light different ways. Okay? One's going to rotate it this way and the other's going to rotate it that way. Okay? So this is a chiral carbon. A carbon, a tetrahedral carbon, meaning it's attached to 4, it's got 4 bonds, and it's attached to 4 different things. Okay? We don't have to worry about light rotating or any of that. We just have to, can you find a carbon that's attached to 4 different things? That's the first thing. We can all do that, right? We can all figure out if a carbon is attached to 4 different things or not. If it is, and it's a backbone carbon, we only care in this case for stereoisomerism in polymers. We care about the backbone, the carbons in the backbone. So if I look, this carbon is attached to 2 hydrogens, not chiral. It's the same on both sides. This carbon is attached to this half of the chain, that half of the chain, a hydrogen, and the green ball. It's attached to 4 different things. So you can see this green can be on this side, can be on this side, it can be here, or it can go into the board, into the plane of the board. And I know that I have made new slides, and I'm not sure why they're not in this slide deck. That's why I'm like, what is, I keep thinking about it. Okay. So anyway, when you have two repeat units, you call it a dyad. I don't care about these words, meso and racemic. I won't ask you those. But what we need to look at is how we put those together. So we can have, when we talk about stereoisomerism, this is a lot of vocabulary, and it's not as hard as it looks like you're thinking it is, okay? Stereoisomerism refers to what we call tacticity in polymers, okay? So sort of stereoisomerism can also be for a lot of biological molecules. It's the bigger term. When we're talking about stereoisomerism in the backbone of a polymer, we call it tacticity. And that's the important word for you to remember, tacticity. So 3 types of tacticity. What's the prefix iso mean? Same. What's the prefix a mean? Without, not. It can mean different, yeah. But its root is not, without. Okay? So atactic is not tactic. That's the random one. Isotactic, iso means same, right? So it's the one where the side groups are all on the same side, the top one. Make sense? Syndiotactic, the weird one, is the one that alternates. Syndiotactic. So, I looked up what that root meant, and I can't remember exactly what it is. But this is the syndiotactic is the alternating one. Okay. So I gotta. Oh, I'm not in presentation mode. That's the problem.
So here we have a polymer chain that's representing an isotactic. And you can see, even if I rotate this, like this, now these are, you're seeing the backs, right? I can't rotate this in such a way that this ball is on the front. So this is like an isotactic polymer. And in just a second, I'll show you the difference between this one and a syndiotactic polymer. So here we have a model of a syndiotactic polymer. Might not look like a syndiotactic polymer until I point out this is upside down. We're seeing the back of the ball, the front, the back. So if I flip that, now I have front, front. So when I flip these so that all of them are facing up, the yellow balls are all facing up, you can see that it's perfectly alternating. So this is representing a syndiotactic polymer. Here we have a model of an atactic polymer. So the side groups are randomly distributed on either side of the chain.
Okay. Okay, let me try and log into Moodle. Okay. Now, if I hit 2, stereoisomerism. Okay. So this, those of you who have or will take organic chemistry, you probably should go through all of this. All right. So I spent a lot of time making all these new slides, and I don't know why they're not in my slide deck. Okay, so here's a typical vinyl polymer. If we've got a monomer where we got some kind of side group. So as it polymerizes, right, it's polymerizing, this can add this way, so the side groups are on the same side, or it can add so the side groups alternate. If it does it 100%, we've got that syndeo-tactic. If it does it 100% on the same side, we have isotactic, and if it's random, it's atactic. Okay? So there's our isotactic, and then if trying to show you, so when you have a chemical bond that's a single line, either they're not trying to show you any dimension, which is usually how we're writing things, but if you see like a wedge or a dash wedge, in that case, single lines are in the plane of the board or the paper. A wedge is coming out towards you, and the dashed one is going into the board. Okay? So if we take this side view and then look at it from the top, it's really easy. It's isotactic. It's really easy to see and visualize no matter how you draw it. And then syndeo-tactic. Here it looks like those are close together, but they're not. One's going into the board and one's coming out. And so this top view, I think, is maybe a little more helpful. Okay. Syndeo means two together. There we go. Atactic is random. There's the video we just watched. So if we want to control tacticity, we have to do something special when we're polymerizing. Okay? So what we have to do is we have to use a catalyst. We do coordination or a catalyzed polymerization to be able to control the tacticity. And what happens is the catalyst only lets the monomer insert in a certain way, and that controls that tacticity. Okay. And that is something we will talk about later. Okay. Why do we care about tacticity? What did we talk about in terms of crystallinity?
It changes its properties
Right.
quite a bit. So you would care about tacticity because that would determine how it would be able to bond with others. Meaning it would
Not bond, but you're totally right. How it can pack together, right? So if we have an atactic polymer, do you think it can crystallize? Somebody said no. You're right. If it's got a random structure, it probably can't crystallize. Okay? Random structures typically can't crystallize. So if we can't control the tacticity, then we might have something that's totally useless versus something that's really useful and dramatically commercializable. And the best example of that is polypropylene. Atactic polypropylene is goo. Isotactic polypropylene spins beautiful fibers. It makes Nalgene bottles. It's a nice material. Very, very useful. Heavily commercialized. But if you can't control that tacticity, it has no commercial use. Okay? So we care about tacticity because we need to know what the structure is and whether the structure is regular enough so it can crystallize, so we can have, useful properties. Now, not all. Sometimes you want things to not crystallize, and that's also important, right? Sometimes you want it to be amorphous. Okay. All right. And then there's all these nice review questions. So what is this one? Syndiotactic. Okay, so I got the little help buttons. Okay, that one's syndiotactic. What about this one? Look again. Isotactic. Yep, it just flipped over. What's it say? Try again. Yep. Okay, so there's a bunch of these questions. We can look at some of the pictures. There's that one. So try to do it a little bit differently. Okay, so those are in there for you. And so there's the sequence introduction to isomers and sequence isomerism, stereoisomerism, and then the structural isomerism. Okay. How many minutes do we have? Oh, yeah. So, in commercially important polymers, polystyrene is atactic. We want polystyrene, we mostly want it to be a clear, glassy. That's what we're using it for. Okay. Polypropylene is largely isotactic. It's sort of as isotactic as we can make it. Okay. PVC is essentially atactic, but there's some thought that it has some syndiotactic sequences, and that's just because the chlorine's big, probably. It's not because we've designed a catalyst to make it that way. Polymethyl methacrylate is atactic. That's plexiglass. So if you want something that's clear and glassy, you probably want it to be atactic. Go ahead. Whether it's glassy or rubbery depends on where the glass transition temperature is.
I was, oh, okay, so that's what keeps it, like, being stiff versus being gooey?
Yeah. Okay. So polypropylene's TG is way below room temperature. So it's not useful when it's just goo at room temperature. Polystyrene's TG, I think, is 105. So it's glassy at room temperature.
So are there like additives that they put in these polymers sometimes to like change the?
Absolutely.
Okay.
Because which one have you used as a soft material? One of these is pleather. It's the same as the water pipes. PVC. Yep, PVC, you add a plasticizer, and you can make leather, fake leather, right? Plastic leather. You can make really good leather dupes, right? Maybe you or someone you know has leather car seats. You know what's leather in the car seat? The front. Just the front that you actually sit on. The back and stuff that looks like leather, not leather. In almost all cars. You got to be in like high-end cars for the whole thing to be leather.
Why not make the whole thing leather? Do they do that in cars?
I would prefer that because I have dogs. Well, I only have one dog now, but yeah, I like plastic seats that you can just sort of wash off. But a lot of people don't. It's a sales and it's what people like.
Tesla uses vegan leather, is that what this is?
Yes. vegan leather is plastic. Come on. I love it when you see bags and purses and stuff advertised as vegan leather. I'm like, petroleum product. We don't call it that. But yeah, no, it's, I don't know. The vegan leathers are usually polyurethanes because people think PVC is bad. Where the monomer is deadly, but the polymer is not. So, yeah. Okay, you guys remember alkenes? Double bond, what their isomers are? Okay. I have this up here. That is from Giant Molecules. I hate that. If you write the C, you write the H's. It was drilled into me when I was an undergraduate, and now I'm inflicting it on you. Okay? You can do skeletal structures with no carbons and no hydrogens, but if you write out the C, put the hydrogens on. I will remind you that. I take points off for that, but I will remind you later. Okay? So I'll leave that there so that I remember to start telling you that. Okay, so we're going to look at butene because that is an important one. Cis-butene versus, I just drew the same one. So these two are not the same because you can't rotate here, right? That carbon can't rotate. Can't flip over. So those two are not the same. So cis on the same side, trans across, transcontinental. That's how I remember it. Okay, so for diene polymers, this we could polymerize. If we polymerize these two, they'd give us the same polymer, right? Because you take out the double bond. So it would be the same. But when we polymerize butadiene instead of butene, I've got 1, 2, 3, 4 carbons. Put double bond there. No, that's not what I want. That's what I already have. There we go. When I polymerize this, okay, so let me write it all the way out. Okay. So see why it's so much faster for me to use the skeletal structures? Okay? But double bond, double bond. So what happens when this polymerizes is the active site comes in and it attacks this carbon. This bond goes here. That one becomes the new active site. So it sort of cascades down. So when we polymerize this, we have N of them, and we polymerize it, we can get one, two, three, four. One too many. 1, 2, 3, 4. I always have to count. Okay? We get this. Or this. Trans, cis. If I stick a methyl group in the right place, got natural rubber. Okay, so here we go. We polymerize it, we end up with cis 1,4 or trans 1,4. These have dramatically different properties. This packs together and makes a hard plastic. This is latex. This is natural rubber. Then if we have isoprene, or I guess that's latex and this is natural rubber. So the cis form, cis-1,4, that's going to give you natural rubber. You cross-link it, you got all these useful things. So the other one is called gutta-percha. And I'm not sure if it has the methyl group or doesn't have the methyl group. I think it's this one, trans. So just flipping the connections around the bond dramatically changes the properties. From a low temperature goo that if you cross-link it becomes something wonderfully useful to a hard plastic. You see this a lot in biology. You flip one bond and you go from cellulose to a water-soluble starch. Flipping one bond in a repeat unit. Okay? So, structural isomerism, this is sort of the polymer version of what you spent the most time on in freshman chemistry or high school chemistry when you learned about isomers, right? You've got things are bonded in a different way. There's the same thing, but from Coleman and Painter. Any questions on the structural isomers? We can look at the I think the structural isomers are not, it's not as good, right? Butadiene, cis trans. Yeah. Oh, there we go. Okay, so it is isoprene. So polytrans 1,4 isoprene is a thermoplastic gutta-percha. So see, this is a cane. And it's hard. It's like a ebony replacement or something. It's like a hard plastic. And there's the tree sap. This was a walking cane that was used to assault a senator in the Boston Senate or the Massachusetts Senate. It's in the old State House Museum. Anyway. I was trying to find, it's not, gutta-percha was used as, but it was never commercially used that much, not like Bakelite where you can get images from everywhere. But so the example that came up that was, had a commons license was this cane. Okay, so 1,4 edition. Okay, so, and then this is going to go through and review all kinds of isomers. So make sure you check out these H5P activities in Moodle. And then copolymers. A blend is made from 2 or more polymers mixed together. And they usually phase separate, so they're not as useful as we would think, right? You can't make alloys like you do with metals and stuff like that. But we can polymerize 2 or more monomers to make copolymers. Polymers are formed from 2 or more monomers. So we can have a random copolymer, a perfectly alternating copolymer, right. Okay, so a perfectly alternating copolymer, we usually refer to that as a homopolymer. Why? Yeah, and we can just make the repeat unit be AB, right? So we don't have two different repeat units. We just have a repeat unit that is AB. Does that make sense? So if you look at the formal definitions of homopolymer, it would include that type, but it's also a copolymer, just to make things a little, the semantics, they can get confusing. But PET would fall under that, and we call it a homopolymer. All right. A block copolymer. It doesn't just have to be 2 blocks, it can be multi-blocks. Tri-block. Okay, so self-explanatory, right? Blocks. And then a graft copolymer. We could make a graft copolymer out of our squigs, right? So a graft copolymer, you either can make it all at once, but often what you have is you have the A polymer is made. And either there's some sites in the backbone that are active, or you do something to make active sites in the backbone, and then you polymerize off of those active sites. That's grafting from. So you've got A, and then you polymerize the B's off of it. The other thing is you could have the B's, and they've got the B chains are polymerized, and somehow they go and they attack the A and bond to it, and that would be grafting 2. Anybody have any ideas why we call it a graft copolymer? What's that word from?
I don't know what it's from, but you also say that when you like splice trees together.
Mm-hmm.
Like you're grafting plants.
Right. So it's the same kind of thing. You're sticking on a new arm, right? Sticking on a branch. So you're grafting. So agriculture, the word grafting is used a lot. And then I bet you've heard of skin grafts, right? Same kind of thing. You're adding to, right? And hoping it becomes one, right? So we can take polyethylene.
How did like a graph, like a bar graph, become a graph? If that's what graph means.
I'm sure they're not the same graph.
It's spelled differently.
And graft has a T.
I'm still dyslexic. That hasn't changed.
So we could take a homopolymer polyethylene, a homopolymer polypropylene, and we can copolymerize that. And if we have too much propylene, it's not going to crystallize, and it's probably not going to be very useful. But if we have a little, it can inhibit the crystallinity in the polyethylene, and you can use that to help control properties. That might be a reason why you want to do this. Block copolymers are super cool. This is how we have thermoplastic elastomers. Thermoplastic, what's that?
That's plastic that doesn't, it can withstand more heat, right? Yeah.
You can melt it and reprocess it. Okay, so a thermoplastic elastomer, can it have covalent crosslinks? Thermoplastic elastomer. Right. You can't have covalent crosslinks if it's a thermoplastic elastomer, because if it's a thermoplastic, you've got to be able to melt and reprocess it. Okay. How do they work? They work because they're block copolymers and they phase separate. So we have a hard phase versus a soft phase. So the hard phase acts like a crosslink, essentially. It makes the whole thing tied together through this phase separation. And And there's a lot of really interesting stuff with block copolymers. But since we haven't had thermodynamics or physical chemistry, we can't really go into a whole lot of details there. So, yeah. Graph copolymers, we already really talked about this. High impact polystyrene and acrylonitrile butadiene styrene, or ABS plastic, and HIPS. Those are two commercially important examples of graph copolymers. Blends, we already hit this. Miscible blends would give you a single phase material, where immiscible blends give you get phase separation. Most polymers end up being immiscible. And so you don't get a good blending of properties because they're not blending at the molecular level. Okay? And then we review. So we will review Module 2 and do our Module 2 quiz a week from today. Right? Tuesday is the wellness day. Okay? So use Tuesday to check out something on Task Human. See if there's something good.
Recording has begun.
Okay, so today we're doing our first pop quiz. You can put your name on it. You can even put the big check plus that gives you the 4 points, total points, before you even start, because you're here, you're taking it, you're going to get full credit. What we're going to do, am I hearing things? What we're going to do is you're going to take it. We're going to go over it. In the dark ages, I used to make you trade your papers like your little kids. And somebody's like, but I want to write notes on mine. I'm like, that's a really good idea. So I quit doing that. And what I asked you to do is to correct it in a different, make your notes in something other. If you're using a pencil, use a pen, or use a different color or something like that. For two reasons. I try and flip through and look at some of them in once you take a picture and put it in Moodle, so I can sort of see like how well you did on the first attempt. But it's also good for you to be able to look back and be like, oh, I didn't know that at first. I corrected it, but I think I know it now. So you guys can go ahead and get started on this. Okay, let's start going over this, and then don't let me forget to talk about Moodle. Okay, so we've got 3 polymers, A, B, and C. Anybody know what A is? Anybody know its name? Polystyrene. Anybody know B? This one's harder, I think. I think you see it less often. That's polyacrylonitrile. Sometimes you'll see it as PAN, polyacrylonitrile. You guys should know this one. Anybody remember what a carbonyl and an oxygen, what's that functional group called? Some of you have had organic chemistry. Carbonyl and an oxygen. What's this group called? No. Oh, right. If this group wasn't there, it would be a carboxylic acid. And so carboxylic acid reacts with an alcohol to make an ester. So any guesses what this is? It is a polyester. And when people just generically say polyester, they mean PET. Almost always. It's not 100%, but it's a good rule of thumb. I will never ask you to come up with the structure from the name or the name from the structure. Okay? You can look that up. I won't ask you to memorize any of that. I know there are other faculty in the department who will ask you to memorize that stuff. So I try and tell you, because eventually you'll recognize them and know them. And this is probably one of the first ones that you'll recognize and know. Okay. Okay. So let's look at the question. So question 1, which one or multiple are step growth polymers? How do we tell the difference between a step growth and a chain growth polymer? Go ahead.
Okay, so I see step growth as something that's like one by one, so it's like you do it as like 1, 2, 1, 2, and then a chain growth is just like spontaneous, so it just goes. So I would say A and B is chain because they just keep going, but C is step growth because it's 2 parts, and so you have to form the 2 parts, and then you form the benzoic sort of carbonyl group, and then you do the ethane, and you do that like step by step.
Exactly right. The rest of you who are like, I don't know any of that, it is okay. I'm thinking you've taken organic chemistry.
Yes.
Yes. Okay. See? All right. It is totally okay. You guys will be at that level in a month or so, but that's not the expectation right now. Do you remember when we drew all those structures and I put them on 2 sides of the boards? Yeah. So one of the things we did was we talked about how if they have a linkage, if they have any atoms that aren't carbon, they're probably step growth. If there's a functional group in the backbone, it's step growth. All this stuff that I'm saying as like there are exceptions, okay? We're not worried about the exceptions in this class, okay? We're looking for the majority, okay? So these 2 polymers have all carbon backbones. And guess what module 3 is? Module 3 is how to tell the difference between step growth and chain growth polymers, okay? So if this was hard, it's going to be easier after module 3. Which one do you think is the most expensive to produce? C. Mm-hmm. Why do you think that? Because it's step growth. Yeah, step growth it is almost always more expensive to produce than chain growth. And I think if you just sort of look at it, even if you didn't know those names, it looks more complicated, doesn't it? Typically, the monomers are more expensive for chain growth, and also the actual polymerization process takes a lot more energy, which makes it more expensive. Which ones can be recycled? Can be. I said, I should underline that. I said can be. I didn't say are.
I want to say A and B because they're like the chains. So that would be
Okay. So A and B can be, but so can. And only one of them is recycled commercially. See. Yeah, this is the only one that's recycled commercially. Okay. It's more expensive than the others, and so it makes economic sense to sort it and recycle it. And a lot of our fleece is made from recycled PET from soda bottles. Soda bottles are always what we say virgin PET. It might have some pre-consumer waste in the bottle, but it doesn't have any post-consumer waste. Post-consumer waste PET, recycled PET is going to go into fleece. I believe it goes into carpets. Yeah. 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 And so, and the other thing is it's, unlike some materials, recycled PET people like to be able to market that it's post-consumer waste. And sometimes there's even a premium on it because they want to have that marketing ability. So, do you think that the PET can crystallize? What do you think? Is its structure pretty regular?
Yes.
Yeah.
Regular enough. It may not be able to form as high a level of crystallization as some of the others, as some other things, like just polypropylene would be able to, but it can crystallize.
Yeah, so only, we learned a little bit about tacticity. So polypropylene, if it's isotactic, can crystallize. If it's syndiotactic, it can crystallize. But if it's random, it can't. And so there's nothing random about this. It's going to be repeating and repeating. And so it can crystallize. And you remember, what did I tell you about the optical properties if something is crystalline? Becomes opaque. But PET is clear. Yeah, it's an exception. It's an exception. Okay? So the short answer is yes, it can crystallize. And why or why not? It has a regular structure. So if it's given the right treatment, it can crystallize. Since we're in the College of Textiles, I'll give you a hint. If it makes a fiber and it's not fiberglass, it's semi-crystalline. That polymer can crystallize. Okay? The reasons why we make a fiber out of it is because it can crystallize. Elastomeric fibers would be the exception to that. They're cross-linked. Okay. Go ahead.
Wait, so like, can the other two crystallize? Like,
Yes, they can. But we don't know. Maybe they can.
Like, how do you know just by looking at it?
Okay, you can't. You don't know. Because you don't know from this is flat, right? Yeah. So, and you have no information about the tacticity. And there is a carbon right here and right here that's attached to 4 different things. Okay? Polystyrene is almost always atactic, can't crystallize. Polyacrylonitrile, I don't know what it is commercially. If this was polypropylene, it would most likely be isotactic. So if I would write the little I, PP, because that tells you isotactic polypropylene. So that can crystallize. If it said it's got the little A, atactic polystyrene, can't crystallize. So those two, the answer is it depends. Okay. So the why or why not is that it has a regular structure. Oh, and we've just answered the third question, right? Some polymers have tacticity, not all. Which of the polymers have some type of tacticity? Well, I just answered that for you. It's A and B. What am I looking for when I'm talking about tacticity? Chirality. How do I know if there's a chiral carbon? Yep, the carbon has to be attached to 4 different things. And when we're talking about tacticity, it's in the backbone. Okay? You could have a chiral side group. We don't care about that. Okay? You could do that. You could have something hanging off the chain that had a chiral carbon. What we care about is a chiral carbon in the backbone, and then we have to talk about tacticity. If polymer A is atactic, can it crystallize? I already answered that for you. Should have read the rest of the quiz. So that's a big no. And why?
Because the side groups are like, they're random. spacing is random enough that it means that they can't get close enough together to form to cross-link and form a strong enough bond.
So if the polymer's going from the front to the back of the classroom and the side groups, this one's here, and then I got 3 more this way and 2 that way, the irregularness of those side groups on what side of the chain they're on prevents crystallinity. It has to be regular or it can't pack together in a crystal. How's everybody feeling okay about that? Okay. So what you do is you take a picture and you upload it into Moodle. And so you go to section 2, module 2, okay? There's the study guide. And then we scroll down, and right here is the pop quiz. So you just click on it and upload the picture. Okay? This module 2 assignment is an H5P, and you can take it as many times as you want, and that kind of thing. I'm trying to figure out how to get it in the grade book. It's not in the grade book currently, but I put it down in the graded assessments because I want you to do it whether I grade it or not. Moodle and grading and H5P don't like each other very much. So anyway, it'll get figured out or it won't. But it doesn't matter either way. So, okay. So you have not. I haven't asked you to turn. We were talking about this before class started, but I have not asked you to turn in a whole lot of stuff. A lot of homework and stuff like that. I give you homework when I think you need practice. So far, most of what I've asked you to do outside of class is readings, right? And reviewing in Moodle and that kind of thing. So here's the quiz. You're going to upload that in Moodle. Module 3 that will probably get started today. It takes 1 lecture, and again, there's no traditional homework. There's only one of those H5P, bunch of review questions, and then module 4 is molecular weight. Molecular weight, we're going to have pop quiz, maybe a second one. We're going to have a traditional problem set. We're going to have all the things in module 4. Even though it's not a big lecture. It'll take me 1 lecture, maybe a little bit more than that, but then we'll go over all the problems and stuff like that. So, you need the practice on the calculations, so I ask you to do more traditional stuff. And then when we get into module 5, there's going to be all kinds of homework and quizzes and all the things, because the vast majority of you have not and will not take organic chemistry, and we're doing synthesis. And so you need more practice with the synthesis, especially step growth synthesis. That's harder. Chain growth synthesis is maybe more complex, but not harder. Okay? So anyway, so we have a very up and down relationship with homework, because I give it to you when I believe you need the practice. And I have figured that out because I've taught this class for a long time. And when I see students missing a concept on the exam and stuff like that, I go back and make an assignment. So there's been lots of previous guinea pigs to get us where we are, okay? So I try not to give you extra work where you don't need the practice. If you're coming to class, you're fine. And I try and give you enough work and enough examples that if when you do need the practice and that type of thing, okay? Makes sense? So we will be having more problem sets and homeworks coming up. So Oh, got the wrong syllabus there. Okay. Oh, I'm looking for the PowerPoint, and it's down here. Okay, so the end of Module 2, we've got some lecture questions. I'm like, how are we splitting the class? This side's more spread out. All right. Essentially, we're gonna do you guys. You're wolf. You guys. Back. Very complicated. One set is always easier than the other, but I don't remember which. So, all right, we'll just start with the wolf side. Okay, below is a depiction of two stereoisomers of a vinyl polymer. An NMR analysis of it's polystyrene. Okay, an NMR analysis of polystyrene showed the sample had close to 100% racemic dyads. This sample would be A, isotactic polystyrene, B, syndiotactic polystyrene, or C, atactic polystyrene. I'm hearing not A.
Yeah, not A. But do we know that it's alternating?
Yeah, we don't.
Yes.
On the bottom.
No, I mean, but how do we know that after those two it continues to alternate perfectly?
It's racemic, so it's gonna be like obviously it could switch, but like the idea is that when you're putting something like up, the actual like orientation doesn't really change. Like that formation right there is gonna look like that.
So it's gonna keep repeating that section?
Yes, well, for the most part. Because it's saying, because it's telling us it's 100% racemic dyads. So it's gonna be syndotactic. It's gonna have.
Okay, so your answer is B, right?
Yeah.
Yes, and you're right. Nice job explaining. Nice. Okay. Second sample has about half meso, the top ones, and half racemic on the bottom ones. What is the most probable tacticity of this sample?
C.
See? You guys good with that? Yeah, because he's right. And confident. Okay. Which of the following polymers, which one is least likely to be transparent? Least likely to be transparent. Most likely to be opaque. Oh, that's their turn. Okay, we got atactic polystyrene, isotactic polystyrene, an ethylene propylene random copolymer, a styrene butadiene random copolymer. What are you guys saying? B?
Why is it B?
Because it,
Yeah, it's what?
Because if it's atactic, doesn't that mean it's just gonna be super irregular, which means it's.
Which means that it's just ultimately transparent. So if it's transparent, then it has to
Least
crystalline.
likely.
Least likely.
It wants it to be
Least likely to
It wants
opaque.
it to crystallize.
It wants it to be opaque, which means it wants it to crystallize.
Okay,
which means
I did not break this question. I copied it from Paul Painter. So, which of the following polymers is most likely to be opaque?
Okay, that makes more sense. I was like really confused.
Oh, and I'm writing down the letters. That's not what. Okay, so you said, what's your final answer?
B.
There we go. Yes, that is right. Why?
Oh, are we answering still?
Anybody can answer because this one doesn't count.
It's because they want it they want it to not be opaque. And to be opaque means that it is most likely crystallized, which means that it is most likely they want it to be opaque, which means that it's most likely crystallized, which means that it is. And to crystallize, it usually needs an incredibly regular structure, which means isotactic
Yes. So isotactic, that's the only polymer up there that can crystallize, right? So it's the most likely to be opaque. Yeah, exactly. The other three are going to be amorphous. Okay. Consider the following copolymers. I got them written up there. Which of these is a schematic of a triblock copolymer? Ooh, this is a hard one. I was kidding. What's the answer? Yeah. Triblock. What's B?
Like the bi or like the
Die block. Die block. What is C? Random. What is D? Alternating or a homopolymer? I think either of those are very acceptable answers. We're over here. Consider the properties of the following two polyethylene samples. Sample 1 was produced by a high-pressure process. Sample 2 was synthesized using a catalyst. Okay. We have to figure out which statement is true. So polyethylene 1 and 2 have the same molecular weight. Polyethylene 2 has a higher density, a higher melting point, a higher stiffness by a lot, and a higher hardness. Polyethylene, CH2CH2. A is sample 2 is more branched than sample 1. B is sample 1 is more branched than sample 2. Sample 1 is more atactic. Sample 1 is more isotactic.
It's not. This is teamwork, right?
Mm-hmm.
Yeah.
Yep.
I don't think it's D.
I think it might be B.
Yeah, I was.
Sample one
B.
is more branched.
Well, like, why would the catalyst make more branches or less branches?
Okay, so what a catalyst does
But
basically.
you don't know that yet. It's just extra words.
Yeah, but the catalyst just works to help like move along the process.
So,
Well, if it had more
It
branches,
depends.
would it not
It
be?
really depends on the chemical reaction. Because like again, it depends on like what actual reaction is happening, but like because it's just a very empty catalyst thing, and like I can't say for sure what actually is happening if I don't know what type of catalyst it is. That's really hard to
So
explain.
you don't need to know any of
Well,
that.
we're because
Yeah.
more branches would make it would make it stiffer, wouldn't it?
More branches are harder to
Yeah.
crystallize, so it
Yeah,
will
that's-
be less true.
That's why
yeah,
I
it would
think it's
make it
B.
because but
Okay, we got a couple
but
people
C-
saying B. You're gonna have to come up with an answer.
C would also mean that it's not able to crystallize, which is why it's between B and C. Because we can't agree that polymer 1 compared to polymer 2 is clearly the one that is more random than the other one,
okay.
as it.
We're not talking about
But
like
if it's
we're not talking about
attacking,
randomness though.
if it's
I
attacking, it
mean,
won't
yeah.
crystallize.
I guess I don't mean randomness. I guess I mean more of the cooked spaghetti rather than like the layered uncooked spaghetti, I guess, is what I'm trying to say.
Okay.
Um,
You guys have to agree, come to an answer, because they're gonna steal it if you get it wrong. B. B. Yes.
yeah.
Because you don't
Is polyethylene? Does it have tacticity?
No.
No. The last two answers are just wrong. Yeah. Okay. So when you synthesize polyethylene, it's typically done free radically or with a catalyst. And free radical polymerizations are hard to control, and you get more branching. Sometimes that's what you want. You want to make a sandwich baggie? You want less crystallinity. You want to make a milk jug? You want to inhibit those branches. Okay? Oh. Well, I might have given you an answer. Which of these would be more appropriate for making bottles of detergent? What do you guys say?
I feel like she gave us a hint by saying that if we want plastic wrap, we use less branches. But here we want more branches, right? Yeah, which need.
No.
For less branching for opaque, you want it to crystallize.
So B.
There's fewer of them. That's why I help them a little bit.
Yeah.
Yes. Yeah, so for a bottle, it's got to be freestanding, right? We want more crystallinity than we do for cling wrap sandwich baggies. So we want less branching. So we want sample 2. Oh.
Sample 1. You gave us the answer.
Yes. Well, that was not so fair. Okay, guys.
I mean, it was one of those, if one's the answer, the other.
Yes, I know. I should take one of the questions out. Okay. Styrene butadiene triblock copolymer. A cross-linked styrene butadiene random copolymer. An ethylene propylene random copolymer, also cross-linked. An ethylene, a 50-50 ethylene linear atactic propylene block copolymer. Butadiene, just an FYI, butadiene does not like to crystallize. Okay, you can assume those blocks are not crystallized. Which of these copolymers is likely to have some crystallinity? It's their turn. They got a hard one.
Well,
Go through process of elimination.
if it's 50% atactic,
It's a block. Yeah. Okay, you just eliminated B and C. Butadiene doesn't like to crystallize, so you're choosing between A and D, so... What did you say? D. I thought you said B. I'm like, you already eliminated that one. D? Everybody's good with that? Yes. Okay. So this is something we haven't really talked about, but you can have a block copolymer or a tri-block copolymer. If one of the blocks can crystallize and the other ones can't, well, those blocks can still crystallize even though it's attached. So that the linear half of the block copolymer can crystallize in D. Does that make sense to everybody? Go ahead.
Why can't A, or why doesn't A have some crystallinity if you have a tri-block?
It could, but it tells you on the bottom that the styrene is atactic. Okay, so butadiene doesn't crystallize. Styrene can if its tacticity is controlled. And a lot of times you will have a tri-block where the ends can crystallize. So they go into the crystals, and now you've got something that's all tied together. It's a, that can act like a thermoplastic elastomer. Block copolymers are cool. There's lots of cool stuff that is possible. Okay. We're over here. We have 4 samples. There's going to be, I think, 3 questions on the 4 samples. So everybody pay attention. You're handed 4 samples by an Evro polymer science professor. I remember this when I was in graduate school. Coleman and Painter asked this question in class. Okay. Sample A is an opaque, regular shaped film that has some flexibility and appears to be tough. It did not break when one of the other students in your class went berserk and pounded it with a hammer. Sample B is transparent, fairly rigid, and brittle. Sample C is not transparent because it's been mixed with filler. However, it stretches to many times its original length, but does not return to its original length after stretching. Sample D appears identical to C, but it does return to its original length after stretching. We're over here. Which of these samples is most likely atactic polystyrene?
Toughness is like how it breaks, right? Like
Toughness is the area under the stress strain curve. So if it's brittle, it's not tough.
We want it to.
What are you guys saying?
Atactic is like random.
Uh-huh.
And so if it's random, it's going to be less opaque.
Uh-huh.
So more transparent.
Yep.
It's going to be less tough. So rigid or brittle.
Yeah, we don't want it to be A.
So between B and M. Because B
It's not transparent. Oh, but because
This also assumes some knowledge of polystyrene. What do you guys say?
So we know it's not A, but it's B is still pretty hard because it's rigid. So I want to rule out B.
I don't think it's B either.
Yeah.
Well, it just depends on what property would allow this turn to its original length.
Yeah. Does anybody remember which property it was that would allow it to return to its original length?
right.
You guys
Um,
deciding what they get wrong?
It's more crystallized, so it will come
So this is,
okay, so
I really think it's
So I'm thinking of the Marco Plato, and I'm thinking, right, because like, where if you gave it time, it could slide past.
I think it's D.
Yeah, I'm like gonna agree. I think it's D.
Because it can't be
Okay.
brittle and stuff like
Is that our final answer? D?
Mm-hmm.
You guys gonna steal it?
No!
It's polystyrene.
Totally A.
Yeah, so that's the reason why I say
It's not transparent.
So pick one. Be your thing.
more slimy but milk jugs. And milk jugs are typically opaque and strong.
You say C. No, you're also wrong. It is B. Okay? So you figured out that it had to be amorphous, right? You saw the atactic and you knew it had to be amorphous. What are the two types of amorphous polymers? Rubbery, which would be the bottom, B, C, and D, right? Rubbery. And
like fragile, like
glassy.
Yeah.
Right? So if you're below TG, it's a glassy amorphous polymer. If it's above TG, it's a rubbery amorphous polymer. Okay? So polystyrene, you know those the little glasses that are like they're round and they're shaped like this? You get them at weddings a lot because you can do fancier drinks in them. They look nice. You squeeze it too hard and it cracks. Yeah, that's polystyrene. Looks pretty. It's cheap. Squeeze it too hard, it breaks. And then you guys have all seen styrofoam. Styrofoam? That's polystyrene and air, right? If it was rubbery, it would not be a foam, it would be a goo, right? Okay. Okay. We're back to you guys. Which of these samples is most likely to be cis-1,4-polyisoprene, natural rubber that has been treated with a cross-linking agent? Mm-hmm. It's your side.
Is it C?
Cross-linking means it's going to be crystalline, doesn't it? No. It's
No.
exactly, it just means the opposite.
Yes.
So no crystalline.
It wouldn't be crystalline, I don't think.
No, because cross-linking is what takes it from like a rubber band to a tire.
Yes.
I don't remember which way.
Which is, well, if you think about cross-linking, that's gonna mean that there's more connections between strands, so it's gonna be stiffer. So
Yeah,
I'm
less
thinking it's gonna be
crystalline.
C, so, cause that means
What do you
that
guys
you
think?
can stretch it, and then it's gonna bounce back.
You say what? They're saying C. You guys are saying C? No. What do you guys say? They answered C. What do you guys say?
If it's natural rubber, at some point it can't be.
But it's not gonna be brittle. So it's probably more tough. So it could be A.
It's not breakable. How do we handle it? Yeah, I mean, yeah, it's not gonna break, that's true. Yeah.
No! No! It's D. D. It's identical to sample C, but it does return. You cross-link it so it snaps back. If I think of my silly putty, I stretch my silly putty, it doesn't return. But if I take a rubber band, which you can make out of a silly putty, you just cross-link it, you stretch it, the cross-links make it snap back. You were so close because you talked about the tire. Who talked? You talked about the tire. So close.
I was saying it, and I just had them confused. I just thought that D was C and C was D.
So.
I thought that C was the one that did return.
D returns.
So cross-linking to me sounds like it would make it as crystalline as possible.
No, cross-linking doesn't have anything to do with crystallinity.
It just seems like it would make it.
Yeah,
I don't know.
cross-linking ties things together. So if you have really high cross-link density, you might have, so for natural rubber, right, we can go from an eraser to a rubber band, well, maybe a rubber band to an eraser to a car tire. It can all be the same material with very different fillers, but mostly it's just a different cross-link density. Remember the video where we saw Caitlin make the slime? She used more cross-linker and it didn't flow the same way. It was a lot tougher. I mean, it was a lot stronger. I shouldn't say tougher, stronger. Okay. It's your turn. Tell me you're going to get it right. This is question number 4, folks. Are you going to get it right? Which sample is most likely polyethylene with a small degree of branching? Oh, I guess it is. It is question number 3, but you still should be able to get this one right after what you know about all the others.
I have no confidence in this.
Hey, you know it's not B and D.
Oh, yeah. I think it's A.
But isn't probably
It's between A and C. It's between A and C. Yeah.
Okay, are you gonna go with him? We're going? All right. Good. Finally, we got one. Well, finally.
We are going to nail the next one. I promise you that.
There isn't a next one. This is the last one. Okay. Why Why is it polyethylene? Go ahead.
I just started thinking about the pipes, like you know, like for, and I was like, well, that's opaque, and it's very regular, and if you pound it with a hammer, it takes a lot to break.
Yeah, so a PVC pipe, it's actually more likely to break than if you hit like a laundry detergent bottle or a trash can, like when we used to have classroom trash cans. We used to kick it and be like, see, it's, you know. So what this says, probably with a small degree of branching. That small degree of branching increases the toughness. Does that make sense to everybody? It makes it so it doesn't get too crystalline that it gets brittle. Most of the time you don't have to worry about that with polymers because they're hard to crystallize, but polyethylene loves to crystallize. So you've got to prevent it from getting too crystalline and getting brittle. So all of this can be a little confusing, right? Because glasses are brittle, but also highly crystalline materials are brittle. And it's, you know, you're coming at it from different ways. So, sample A, let's forget about the names of the polymers. Sample A is going to be semicrystalline or amorphous? Semicrystalline. It's tough. For semicrystalline polymer, it's tough. So do you think it's going to be above or below TG? So is are the amorphous domains going to be rubbery or glassy? Rubbery. Mm-hmm. Okay. Sample B is transparent, fairly rigid and brittle. So is that going to be amorphous or semicrystalline? Amorphous. Transparent. Okay. Is it going to be glassy or rubbery? Glassy. So is that above or below the TG? Below. Because it's like you heat it up, it turns to goo. Just like glass, right? You melt it, but you're not melting it because there's no crystals. Okay. But we say melt it, right? All right. Sample C. Not transparent because it's mixed with filler. So is that probably amorphous or semicrystalline? Amorphous. Okay. It stretches to many times its original length. So is it glassy or rubbery? Rubbery. Okay. It does not return to its original length after stretching. Is it cross-linked or not cross-linked?
Not cross-linked.
Not cross-linked. Okay, D is the same, but it returns. So is it cross-linked or not cross-linked? Cross-linked. Okay, see how the strategy sort of works for figuring out what you want to use? So then, if you're like, okay, well, I need a semicrystalline polymer above TG, you can go look it up in a table, right? There's all kinds of different ways you can, you know, I'm never going to ask you specific names and that kind of thing, because you can always look it up in a table. You guys got one more question, so you pulled it out. Okay, so we end at 1, right? Yes. I confused my two classes because one ends on the hour and the other ends at 45. Okay. So that is the end of Module 2.